Welcome to this Go programming course. In this course, you will learn all about the Go programming language, starting at the basic features all the way up to more advanced features like threading and concurrency and Go routines. This will cover a ton of aspects of the language, and by the end of this course, you'll be very comfortable to write code in Go. Now, this course is split into over 21 individual lessons. All of those are available to click into from the description down below or the video player in terms of the chapters on this YouTube video. Now, while you can go through this course as a complete beginner, I would suggest that you have some fundamental understanding of another programming language. So something like Python, JavaScript, any other language really will do, because this does assume that you have some of the fundamental concepts understood, like what a variable is, or what looping is, or what an if statement is. Of course, it will go over the syntax in the Go language, but it's not going to explain them as if you were a complete beginner, because this is meant to get you up to speed relatively quickly without going over some of the really basic stuff that I know most of you already know. Now, with that said, I will let you know that this course did used to be a part of a larger course that I was actually selling that was premium that you would have had to pay for. We've recently discontinued that course, and because of that, I'm going to be releasing some of the content for free on YouTube. So I hope you enjoyed this Go programming course. I'll be going over backend development with Go. We're going to learn a new programming language in this section, as well as how we can write some backend services and then deploy those and eventually connect them to the front-end applications that we were building in the first section. So with that said, let's dive into an introduction to Go, otherwise known as Golang. All right, so Go or Golang. So Go was designed at Google. It was actually designed by employees at Google to kind of combat some of the frustrations they had with languages that they were using, as well as keep the performance of those languages. You'll see what I mean in 1 second, but it was designed to have high performance, yet simple and easy to understand syntax. So the idea was at Google, they were using languages like C and C++, which are notoriously difficult to write code in and to understand. However, those languages are very fast and very performant, and they wanted to maintain that level of performance while having a new language that would be easier to write in and easier to understand. So that's why they developed Go. Now, Go is a statically typed compiled language, which will make sense in just a minute, and it's useful for running performant backend services. Go is used primarily on the back end. You're not going to be using it to build user interfaces or entire websites or anything along those lines. It's really mainly a back end language. It's also great for networking and multiprocessing and has some great features built into the language that makes it very easy to develop scalable applications. Okay, so Go use cases. Where would you use Go? Why are we learning Go? Well, Go is good for cloud and network services. It's good for command line interfaces, which typically need to be very performant pieces of software. For web development, when I say web development, I'm talking about back-end web development, so creating APIs, authentication services, anything that works in the back end. It's good for automation and DevOps, and for building utilities and standalone tools. So you can see that all of these use cases here are kind of low-level, back-end type features where you're not having a massive graphical user interface or anything along those lines. And typically what you'll do is connect Go with other languages so that Go is kind of responsible for all of the back-end performance-heavy tasks, and then you have a front-end language like JavaScript, which may be displaying a nice user interface and handling all of that. Now, before we go on to the next section, I'll quickly mention that the reason we're learning Go here is because it's a very different language from JavaScript, which will allow us to get a good appreciation for different types of languages and how you write code in statically versus dynamically typed languages, which we're going to get into in a minute. So even if you're not considering becoming a backend developer, this is a really good language to learn. It's going to make you a better programmer, and it's going to allow you to see a bunch of features that we didn't really see very much in JavaScript that now will be very prevalent in Go. So regardless, very good language to learn, hence why I've put it here as the second language, a little bit more challenging than JavaScript, but it just introduces a bunch of new things that you haven't yet seen, and that's why we're teaching it. All right, moving on, different programming languages. So there are various programming languages, each of which has its own use cases and language features. Now, one of the main features of languages we're concerned with is static and dynamic typing. Now, a language can either be statically typed or dynamically typed. Now, we also care about how languages are compiled and interpreted. Now, whenever we're looking at various programming languages, these all have different use cases, right? No one language is just the best programming language. It depends on what you're doing. So JavaScript, as we've seen, is very good for doing front-end web development where we're building user interfaces, whereas Go is going to be very good for back-end development. So there's all these different languages. They fit into many different categories and classifications. And your job as a programmer is not to say, oh, I'm only going to use this language. It's to use the best language for the job. And as you get better and better at programming, you'll learn many different languages and be able to switch between them very quickly and just use whatever one is going to be the best for the specific task that you're working on. All right, moving on, let's talk about interpreters and compilers. So when we humans write code, we write something known as source code. So all of the code you've seen so far, this kind of human readable code that's in a programming language like JavaScript, Python, Go, whatever it may be, this is known as source code. However, this source code can't be directly executed by our computer. The point of the source code is that it's easy enough for us as humans to write, but machines, computers, can't really understand that. So what we need to do is we need to take this source code and convert this into another form of code that can be understood by our computer. Now that type of code is typically called bytecode or machine code or assembly, okay? So before this code can be executed by our computer, it must first be converted into a language the machine can understand. Don't worry about the name of that language. That's not something you'll look at or have to understand, but we have tools that do this for us. So there's a tool called a compiler, and what this does is transforms our source code into something called bytecode. That can then be directly ran by the CPU. So when we say a language is a compiled language, what that means is that we take the source code, we compile it into this new type of code, which is our bytecode or machine code, and then directly from the processor of our computer, we can execute that code. Whereas an interpreter works a little bit differently. What an interpreter does is it transforms and executes our source code one line at a time. So the compiler takes all of our code, gives us a new file, and that new file is what we can actually execute. The interpreter takes our source code, and one line at a time, it converts that into code that can be understood by the machine, and it executes it at the same time. Now, there's different implications here for using a compiler or an interpreter, and some languages actually use both. Regardless, what you need to understand right now is that JavaScript is an interpreted language, whereas Go is a compiled language. So that means we're going to kind of run our code a little bit differently than we may have with JavaScript. So just to walk you through this again and kind of explain it a bit more in depth, what happens is we write our source code, and then we need some way to execute this. Now, we're either going to run this through a compiler, where it's going to be transformed into something that can then be understood by our CPU, or it's going to be interpreted, where we don't need to compile it first, we just give it to the interpreter, and then it executes the source code one line at a time. Now, using a compiler typically means that you're going to have stricter rules in your programming language. That means that you need to define things like the types of variables, which we're going to talk about in a second. And there's a lot of errors that can be caught at compile time. Now, what that also means is that the compiler can perform a lot of optimizations on our code that allow it to be ran a lot faster than if we're passing it to the interpreter. So imagine with our compiler, we're passing it this entire file, it's reading through the entire file, transforming it into this new format, and while it's doing that transformation process, it can optimize quite a few things and catch a lot of errors that we may not want to be caught at runtime. So compile time is obviously when you're compiling the code, and runtime is when you're actually executing the code. Whereas with an interpreter, what happens is since we're not first compiling our code, it can be a lot slower to run our language through an interpreter because we need to not only compile or transform that code into something that can be executed, but it then needs to be executed directly. That also means that a lot of times we're catching errors at runtime rather than compile time, which can make our programs a little bit more difficult to work with when they get larger and larger. So to summarize this a bit, compiled languages are typically a little bit stricter and are going to be faster to execute. Whereas an interpreted language is typically a bit more dynamic, a bit more flexible, but it's oftentimes going to run a little bit slower and catch a lot of errors at runtime, which means you don't actually know you have an error until you execute the code, which can be a big problem in a lot of different use cases. Anyways, that's kind of the summary here on interpreters and compilers. We'll talk about this a bit more when we start actually compiling and running our Go code. Moving on, we have dynamic versus static typing. Now, this is a property of all programming languages. They're either dynamically typed or statically typed, and we usually want to know that before we start learning a language or working with it. Now, dynamic or static typing refers to when and how the types of variables are decided. So in a dynamically typed language, by the way, JavaScript is dynamically typed, variable types are decided at runtime, while in statically typed languages, they're decided at compile time. Now, what that effectively means is that when we're working in a language like JavaScript, we can change the type of a variable. And you've seen this. We can have something like var x equals 1. and then later on in the program, we make it equal a string, or we make it an object, or we mutate it or modify it in some way. That's completely fine in a dynamically typed language, because the types of these variables are being decided as the code is running, which means we can change the types as we execute that code dynamically. Whereas in a statically typed language, we actually need to define beforehand what type all of our variables are going to be. That means if I define, say, x and I make it equal to 1, it can only ever store an integer, or whatever the type was that we declared when we first made that variable. I can't later on go in the program and change the type of that variable to be a string or to be a Boolean. That won't work, and that will cause an error. Now, if we continue here and kind of extrapolate this, we can imagine that since we know the type when we're compiling some code, like a statically typed language, that's actually one of the reasons we're able to perform a lot of optimizations on that code. If I know this variable is only ever going to be an integer or only ever going to be a floating type value, then that means that I can do a lot of optimizations and make my code a lot faster to execute. Whereas in my dynamically typed languages, if we're interpreting them, that means that we can't do those same optimizations because we're unsure of what the type of the variable is going to be. Now, this is a very high level, kind of dumbed down explanation, but hopefully you get what I'm saying here. So we have dynamically typed languages and statically typed languages, and that has to do with when the types of our variables are decided. JavaScript is dynamically typed and Go is statically typed. All right. So with that said, I'm going to wrap up the video here. That's all I wanted to discuss as a general introduction to Go. Go is a great language. You're definitely going to enjoy it. It's a really great thing to have kind of under your belt and just to know a little bit about. And it looks great in an interview and on a resume when you have more than just one language that you know. You know a statically typed language and a dynamically typed language, and that means that you are able to program in a variety of different languages and pick up and learn new things a lot easier than someone that only knows, say, a dynamically typed language or only knows a statically typed language. I'll be sharing with you how to set up your development environment for writing and executing Go code. Now, to do that, the first thing we need to do is download and install Go. So go to go.dev, click on download, and you'll see that we have a few options here at the top, which are the ones we're going to want to go for. So if you're on Windows, you're going to click on the MSI installer. If you are on the M1 or M2 Mac, you're going to go with the ARM64. If you're on an Intel Mac, this one, and then Linux, you'll go with this one. There's a bunch of different options here, but you always want to go with the installer option. So if for some reason this page changes later on and you only have stable versions here, go with the latest version and go with whatever is the installer. So in my case, I'm going to click on the Windows installer, so I can do that from there or from up here. I'll put that in my downloads, and then I'll run through the installer and show you what we need to do. All right, so I've just opened up the installer here. I downloaded it and then just double clicked on it. It's computing the space requirements right here. Once that's done, we'll walk through this and go through all of the steps. All right, so that's done. We're going to click on next. I do have a previous version of Go, so I'll actually uninstall that and just install the new version just so I can walk through this installer with you. So accept the terms. Where do we want to install it? The default location is fine unless you want to change that. Ready to install Go? Yep. I'm going to go ahead and press install. We'll give that a second to run and then be right back. All right, so the installer is now finished. So I'm going to go ahead and click on finish. And what we'll do now is open up Visual Studio Code. And we're going to start actually developing or writing a Go program inside of here and then seeing how we can compile and run it. Now, actually, the first thing we need to do here is make sure that we restart our Visual Studio Code if we already had it open during the Go installation. That's because Go should have added the Go command to our system path, which will allow us to type Go here inside of our terminal. Now, for me, that works because I already had Go installed, but if you don't, you might see this command doesn't work. So restart your Visual Studio Code. Once you restart it, kind of like reopen it, get into some directory where you want to write your first Go program, and then we're going to do that in just 1 second. All right, so I did just restart my VS Code just to make sure I had the latest version. And for all of you, what you're going to do in VS Code is you're just going to open up your terminal here, and you're just going to type in Go and just make sure that command gives you some output. If that command doesn't work, then likely what's happening is Go has not been added to your system path. Now, this is a little bit of a complicated error. It's actually pretty well impossible for me to explain how to fix it in this video. But what you'll need to do is just Google how to add Go to your system path or to path on, and then whatever operating system you're on. So on Windows, it's going to be different from Mac. On Mac, it's going to be different from Linux. For 99% of you, this should just work automatically. But if it doesn't, that means Go is not added to your path and you need to add it. So again, that's kind of the error. What you'll need to look up is how to add Go to path, and then whatever your operating system is, follow through a few tutorials, and you should be able to get that added. Again, apologize that I can't show that to you here, but it just depends on your environment and a million different factors. Okay, now that we have Go installed, what we're going to do is write a very simple Go program. To do that, I'm just going to open up a new file here in VS Code. I'm in a directory, by the way, called Go. You can do this anywhere you want. And for now, we'll just call this kind of demo.go. Now, the extension for Go is going to be .go. Now, that reminds me that what we can do here in VS Code is we can go and install the Go extension. So if you click the extensions pane here and go to Go, install this here, and it will give you a few more features in Visual Studio Code, which are nice. Let me close that. You can see I already have this installed. Okay, so now that we have the Go extension installed and we have a Go file, we're going to write our first Go program. To do that, we're going to begin by declaring a package main. Then after package main, we're going to say import fmt, and then we're going to create a function called main. And inside of main, what we'll do here is say fmt.println, and then we're going to print hello, comma world, exclamation point. This is our first Go program. Now let's break this down here, and then I'll show you how we can run it. So every time we create a kind of Go file here, we need to have an extension, .go, and then we need to declare package main. Now we can have different packages and modules. I'm not going to get into that right now, but whenever we're creating kind of an individual file that we're going to be executing, we always put package main. Then we're importing fmt. Now this package allows us to actually output things to the console. So you can see that I've used fmt.println or println, which stands for print line. Then I have a function. This function is called main. I open my curly braces, and inside of the curly braces, I put the body of the function. Now, it's important that you call this function main because Go is going to look for an entry point to your program, which is the function main. So anything I put inside of here is automatically going to run anytime I run this Go file. If I call this something like main with a capital M, then you'll see that we'll actually get an error when we try to run our code. Okay, so let's go ahead and see how we run and execute this so we can talk a little bit more about our Go program. So to do this is quite simple. We need to get in the directory where our file is. In that case, it's the Go directory. And we need to type go, run, and then whatever the name of the file is. In this case, it is demo.go. When I do that, you'll see that it's actually going to compile the code in the background and then execute that code. It takes a second and it spits out hello world. Now, the reason that took so long is because what this go run command is doing is creating a temporary compiled file of this program. Then it's running that compiled file using our CPU. It's kind of doing two steps in one. However, we have another command that can just build the compiled file, and then we can directly execute that file if we want. So most time we're just going to use go run. However, we have the ability to say go build and then the name of the file, which is demo.go. When I do that, notice it creates an exe file for me. If you're on Mac or Linux, you're going to get a different file actually, but on Windows we get an exe. And then if I want to run that exe, I just type the name of that file, which is demo.exe, and it executes it instantly, right? You can see how fast that's happening now once we've actually compiled that code. So let me just break this down a little bit for us because this is going to be different depending on operating system. So if you're on Windows, everything I just did will probably work for you. If you're on Mac or Linux, it's going to work a little bit differently. So again, what go build is doing is actually building a compiled version of this Go code. But that compiled version is based on the operating system that you're on. So if you're on Mac or Linux, you're going to get a slightly different file that can only be executed by the Mac operating system or the Linux operating system. So to execute that file, you're going to type ./ and then the name of the file, which is probably just going to be demo. It might have a .sh associated with it or some other extension, but most likely it's not going to have an extension at all. And it will just be something like that. So you'll see the file pop up here. In that case, you just run ./ whatever the name of the file is. It's then going to execute that file for you. So again, that's if you're on Mac or Linux after you ran that build command. Now, the great thing about this executed file here, or this, compiled file, is that I can actually take this file and I can give this to whoever I want. So I could give it to my mom, my brother, anyone else who's running a Windows computer, and they'll be able to execute it without having Go installed on their computer. So when we installed Go, we were installing some command line tools for Go that allow us to compile and build Go applications. Once we have them compiled, then anyone on the same operating system as us can execute these files without setting up their environment. So this is different than something like JavaScript. With JavaScript, if I want to execute that, I need to have a browser, I need to maybe have Node.js, depending on the script that I have to do a little bit of setup. Here with Go, all I need to do is just run the executable file that I'm given, and it will execute that program. So hopefully this makes a little bit of sense, but depending again on what operating system you're on, you'll get this compiled file. You can then pass that to anyone you want, and as long as you're on the right operating system, you'll be able to execute it without having Go installed. Okay, so now that we've talked about compiling and running our Go code, let's quickly have a look at some errors we can run into, and then we'll move on to the next video. So for example, let's see what happens here if I actually comment out this line. So notice if I comment this out, all of a sudden I start getting this kind of red highlight. It says FMT is imported, but it's not used. Now I'm just going to save my file, so save without formatting, and I'm going to try to run my Go code. So go run demo.go. Now notice it actually doesn't allow me to run this Go code. It says FMT is imported, but it's not used. Now, this isn't something that really would cause an error, right? Like typically we'd be able to import something and just not use it, but in Go, that's actually not allowed. We can't even get to a compiled file. If I try to even say go build and then demo.go, it won't even allow me to compile this. So the compiler is catching an error for me and telling me, hey, you imported this, but you didn't use it. So if you want to be able to run your code, you need to either remove it or actually use it. So that's why if I start using it here, all of a sudden that will work. Now we'll also see that if I change this to say capital M, for example, and we clear this, and let's actually do like main2, and then I go ahead and run this, we get an error. It says function main is undeclared in the main package. So again, same error occurred here. I tried to compile my Go program, but I couldn't do that because there was an issue where I don't have that main function. So you're seeing already that a language like Go is going to be a lot more strict than a language like JavaScript, and it's going to catch a lot of the errors or bugs that you have before you actually get to a runtime environment. So in most cases here, when you're working with Go, you won't actually be able to execute code that's going to have a bug or issue in it. Obviously, that can happen, and that will happen in some instances, but most times the compiler is going to be almost your friend here and catch all of those errors for you before you end up compiling that code. Just wanted to quickly demonstrate that to you. We'll obviously see more examples as we go and write real Go programs, but I just wanted to get you kind of familiar with Go, see how the compiler and the interpreter works, and get your first Go program up and running. I'll be giving you a quick overview of the binary numbering system. Now, the reason we need to do this is because in the next video, we're going to look at data types and variables, and it can be very confusing to understand the different data types in Go if we don't have some kind of fundamentals or basis of understanding of binary. Now, binary is just a different numbering system. It's not overly complicated. In about 10 or 15 minutes, I can actually teach you everything you need to know about it to understand the different types that we'll be using in Go. So let's start here, and I actually want to begin by talking about the base 10 numbering system, which is the numbering system that we're used to using. So in base 10, that's the numbering system we use. You might not know it as base 10, but that's really what it is. We know how to write numbers, right? And we can write numbers that have the digits 0 through 9. Now, the reason why we have these available digits is because the base of our numbering system is 10, meaning there is 10 different values that we can have for every single column in our numbers. So if I write out a number like 374, we see that this has 3 different columns. Now, I know you've learned this in elementary school, but I'm just going to go back to the basics so we can then apply this to base 2. So we have the first column, the second column, and the third column. You may refer to this as the 1, the tens, and the hundreds column. Now, what that actually means is that to determine the value of the number, what you'll do is you'll take each column and you'll multiply it by the base of the numbering system to a specific exponent. Now, in this case, we'll say this is ID0, ID1, and ID2, or index 0, 1, and 2. If I want to calculate the value of this number, I take my ones column, so I take 4, and I multiply that by 10 to the exponent 0, which is 1, right? If I want to calculate the value of this column, which is going to be 70, I take 7, and I'll need a bit more space here, so let's kind of draw this over here. I take 7, and then I multiply this by 10 to the exponent 1, because this is the tens column. That gives me 70. I then go here to 3. I do the same thing. 3 multiplied by 10 to the exponent 2, which is 100, and that gives me 300. And then to calculate the whole value here, I just add all these numbers together, and I get 374. Now, in our case, we can just read the number directly as it is because we're working with base 10 and we just know that numbering system, but the exact same thing I just showed you here can be applied to any base numbering system. So let's clear the whole screen here, and let me show you now with binary and some other numbering systems. So we have multiple systems. We have base 10, which is known as decimal. We have base 2, which is known as binary. We have base 8, which is known as octal. And we have base 16, which is known as hexadecimal. Now, I'm not going to get into the other numbering systems. We're just going to look at binary. But in a binary numbering system, we have base 2. Now, base 2 means that we have 2 digits we can use, 0 and 1. Whereas if we were working in, say, base 8, we'd have 7 digits, right? Or sorry, 8 digits, 0 through 7. 16 would actually be 0 through 9 plus A through F, where A through F represent the extra 6 here that we can't fit in our digits. So just want to quickly kind of show that to you. Okay, back to base 2. So with base 2, we can write numbers that include the digits 0 or 1. So if I write a number like 1, 0, 0, 1, 0, this is a binary number. Now, if we know that's a binary number, we can actually calculate the value of this number in base 10 quite easily. The way we do that is, again, we can label our columns 0, 1, 2, 3, and 4. And just like we do in base 10, kind of unknowingly, we'll do that here explicitly in base 2. So I take my first column and I raise 2 to the exponent 0, and I multiply it by the digit value, which is 0. I take my second column to the exponent 1, I multiply it by 1, then I have 2 to the exponent 2, multiply that by 0, to the exponent 3, multiply that by 0, and then 2 to the exponent 4, and I multiply that by 1. Now what that gives me is the following. So 2 times 1 is 2. 2 to the exponent 4 is, what is that? 2, 4, 8, 16. So we get 16. We take 16 plus 2, and that gives us 18. And that's the value of this binary number. Don't worry, I'll go through a few more examples, but you can see that all we're doing is we're looking at all of the columns from right to left. We're giving them some kind of index. We're just counting, right? 0, 1, 2, 3, 4. And then we're taking the base of our numbering system, raising it to the exponent of whatever the ID of the column is, and then multiplying that by whatever the value is. In this case, we're only ever having 1 or 0, which makes it quite easy for us. So here we get 18. Let's go through another example. All right, so we've got another example here. We'll begin by just labeling our columns just to make this nice and easy for us. Eventually, you don't need to do this, but for now, I'll just make it nice and visual. And now we know that any of the zeros, well, that's not going to result in any value, so we can kind of skip doing these ones, and instead, we'll just do where we have all of the ones. So we can start in this first column here where we have a 0. So that's going to be, and I'll kind of just write it from left to right here, 2 to the exponent 0 multiplied by 1 is equal to 1. Okay, so we have 1 for this digit right here. We can give that a check mark. All right, next we have this one. So we have 2 to the exponent 1 multiplied by 1 is equal to 2. Okay, that one's done. Now we know these 3 are done because they're all going to be 0. Now we move on to this one. All right, so now that's 2 to the exponent 5 multiplied by 1, which is equal to, and I believe that this is going to be 32. Then we can check these off. Now we go over to 6. So when we're at 6, we get 2 to the exponent 6 multiplied by 1, which is equal to 64. And then lastly, we have 2 to the exponent 7 multiplied by 1, which is equal to 128. Okay, so now we need to add all of these together. So we have 128 plus 64 plus 32 plus 2 plus 1. I'm not exactly sure what that's equal to off the top of my head, but I'll quickly sum it up and then let you know. All right, so that is equal to 227. So we can see this binary number means 227 in decimal, okay? So I've just showed you very quickly how you can convert from a binary number to a decimal number. Now that we've seen kind of the basics of binary here, I want to talk about a few properties of binary numbers and something known as bits and bytes. So let's erase all of this. So if we have a binary number, every single column in this number is referred to as a bit. Now, the bit can either be 0 or 1, but the more bits that we have, the larger numbers we can represent, whereas the fewer bits, the smaller numbers we can represent. Fairly straightforward. So we have bits. We also have bytes. Now, a byte is simply equal to 8 bits. So if you hear someone say, oh, I have 8 bytes, all that means is that they have 8 multiplied by 8 bits. So they have 64 bits, okay? So 1 byte is equal to 8 bits. Just make sure you understand that because that can become important. All right, so we have bytes. and we have bits. Now, the reason I'm telling this to you is because in Go and in many different languages, we'll be defining variables like int 32. Now, what this 32 component represents is the number of bits that we have in our number. So we need to know, by having 32 bits, what is the range of numbers that we can represent, and how many numbers can we represent with this value? Because we also could have int 8, int 16, int 64, and all of these variables essentially take up a different amount of space. And we want to use the least amount of space that we possibly can. All right, so let's begin here. If we have something like 8 bits, what is the maximum number of values that we can represent? So how many different numbers can we represent with 8 bits? Well, the answer is simply 2, so the base of our numbering system, raised to the exponent 8, which is 256. So if you want to figure out the number of values you can represent, you simply take the base of your numbering system, which in this case is 2, and you multiply it by the number of bits that you have. So in this case, we have 256 unique values that can be generated when we have 8 bits. If we had 64 bits, then we would get a very, very large number, right, for the number of values that we can represent. So that's the idea here when you're trying to determine, essentially, the maximum number of unique values. Now, my next question after this, though, is what is the range of values that you can represent? Because the range of values and the number of values are different. When I talk about number of values, I'm talking about the discrete number of unique values. The range means up to what maximum and down to what minimum. Now, the range of numbers with 8 bits is actually going to be 0 to 255. Now, you may notice that that's simply 1 less than the number of unique values. The reason for that is that we have this 0, right? So if we have 1 to 255, that's 255 values, plus the 0, that gives us 256 unique values. So if you want to determine the range of values, you're going to say the maximum is equal to 2 to the number of bits, which in this case is 8, minus 1, and then the minimum in this instance will just be 0. So max is 255, and the minimum is 0. All right, so hopefully that makes sense. Try to remember that because we're going to need to kind of use those properties as we get further into binary. Now I want to talk to you about something known as signed binary numbers. So far, everything I've been showing you is just positive numbers, right? That whole kind of equation that I walked you through only works when we have positive values. But we need to represent negative values in our computer as well. Now, when we use negative values, what we need to do is change our binary number a little bit. So let's say we have 11001. Now, I actually want to make this a negative value. Well, the way I do this in my computer program is I add an additional bit here, which is referred to as the sign bit. Now, that was a horrible way of writing sign, but you get the idea. The sign bit, if it's 1, that equals negative, okay? And if it's 0, that equals positive. So fairly straightforward. It does kind of change this a little bit. We're not going to get into all the details of negative and positive binary numbers, but the idea is you have this 1 bit at the beginning of the number, and that bit tells you if the number is negative or if it's positive. So in this case, this would be a negative number because we have the sign bit equal to 1. If it was equal to 0, then it would be positive. Now, when we have signed integers or signed binary numbers, what that means is that the range of values that we can represent changes. So let's say now, again, we have maybe 8 bits, okay? So something like this. Well, if this first bit is being used as the sign bit, that means that no longer am I able to represent a maximum of 255 because I've removed one of my bits that is used for the value, and now I only have 7 value bits. So what I need to do, if I want to figure out the minimum and maximum, when I'm using a signed binary number, non-unsigned binary number, is I do the following. I take my base, I raise it to the number of bits minus 1, and then I subtract 1. And that's going to be equal to my maximum. However, my minimum is going to change now. My minimum is going to be negative 2 to the exponent 8 minus 1, like this. So in this example, what that results in is a minimum value of negative 128 and a maximum value of 127. Now, keep in mind here that the total number of values we can represent hasn't changed. It's still 2 to the exponent 8, which is 256. So using 8 bits, I can represent 256 unique values, but if I use one of my bits as a sign bit, then that means that my range changes, and now I can represent negative values as well. So I get negative 128 to 127. If I went up one more bit, then that would be negative 256 to 255, okay? And you just keep kind of repeating this process here as you add additional bits. So hopefully that makes sense. I don't want to get into all the rationale for this, but essentially when you remove one of the bits from the value, then it changes the maximum value you can represent, because obviously now you are using a signed bit. So you need to know if you're using signed integers or unsigned integers, or in this case, signed binary numbers or unsigned binary numbers, to know what the value of this binary number is going to be, because again, you may have this signed bit. Now, just as a note here, throughout the rest of this Go section, I'm going to go a little bit faster than I went in the JavaScript section, just because a lot of this will be repetitive, and it will really just be showing you the new syntax or kind of new ways of doing things here in Go. Anyways, with that said, let's get into our data types. So first of all, let me just comment this out here. By the way, a comment is 2 slashes, just like in JavaScript, and to do the multi-line comment is the same as JavaScript, so that's not new. Anyways, let's go through the data types that we have. So we have, first of all, the uint data type. Now, uint stands for unsigned integer. Now, we have a bunch of different variants of this type. So uint, just by typing this, is going to default to the uint 32 or to the uint 64 type. Now, this depends on the value that you're storing inside of the uint. We can talk about that later on, but for now, understand that what will happen is it will automatically go to the 32 or to the 64 type. Now, remember I told you in the previous video that when we see something like a 32, that means 32 bits. So if we were looking at a uint 32 type, that would mean that the minimum possible value we can represent is 0, and the maximum value is 2 raised to the exponent 32 minus 1. And the total number of values is 2 raised to the, if we can type in this symbol correctly, 32, okay? So this is the unsigned integer. Now we have, starting at uint 8 to 16 to 32 to the 64 type, okay? And there's no 128 or anything higher than that. You can go 8, 16, 32, 64. Those are the only options that you have. Now, is there uint 4 actually? No, there's not. Okay, I just wanted to make sure. Anyways, that is our unsigned integer, and notice we kind of go up by bytes, okay? So we're kind of doubling every single time, a power of 2. Now, other than uint, we have the int type. Now, int stands for signed integer, meaning we can represent negative values. So unsigned integer, only positive, int, either positive or negative values. Now, just like our uint, if we just use the int type, then that's going to default to the int 32 or to the int 64 type. However, we can also explicitly set the type by saying int 8, int 16, 32, or 64. Now, if we're looking at something like the int 8, that means the minimum possible value we can represent is negative 2 raised to the exponent 7, and the maximum value is 2 raised to the exponent 7 minus 1, whereas the total number of values is 2 raised to the exponent 8. Okay, so that is it for our uint and for our int. Again, use uint when you only want to have positive values, and use int when you want positive or negative. The default types, int and uint, default to either 32 or 64. A lot of times you'll just type in int, you won't actually write out, say, the 32. Next, we have a float value. So we have float 32 or float 64. Now, the most common one to see is float 64 here. This is the one you're going to use most of the time. But what this means is that you have a decimal or floating point value. So in our int and uint, we can't store decimal values. It can only be an integer, which is a round number, right? Or a whole number, okay? Whereas float 64, I could store something like 1.23 whatever, or 12.342 whatever. And the 64 is the number of bits we're using to represent this value. Again, 32, same thing. All right, so that is our float. Beyond that, we have the byte type. Now, the byte type is equivalent to the int 8 type, okay? So 8 bits, 1 byte, meaning byte type is simply equal to int 8. So they're synonymous. There's certain instances where you typically will write byte as opposed to something else, but byte can be used to store a number, so 1 byte, or you can actually store a character with it. So if I'm going to use a character in my byte type, I use single quotation marks, so something like this, and I can store an individual character, which can be represented by 1 byte. Next, we have the rune type. Now, the rune type stores the int 32 value, okay? So rune is equal to int 32, and our byte is equal to int 8. Again, you can use them synonymously. We then have the Boolean type. This is either going to be the value true or false. Straightforward. That's what you can store in your Boolean. Next, we have a string. The string is going to be anything inside of double quotation marks. Note here that you're not using single quotation marks. You are using double quotation marks only, okay? So unlike JavaScript, where you can use either single or double, for strings in Go, it's only going to be double quotation marks. And then we have this nil type, which is kind of equal to undefined or null, okay? So really it'd be more equivalent to null in JavaScript, nil kind of meaning none, non-existent, etc. There's a few other types, but we don't need to look at those right now. All right, I'll recap the types in just a second, but for now, let's have a look at how we create different variables using these types. So just like in JavaScript, we have two types of variables we can make. We can use var, which will give us a variable that can change this dynamic, so we can actually update its value, or const, which is a constant variable that cannot change, all right? So let's actually start by just creating a variable. So when we make a variable in Go, we're gonna say var. We're gonna define the variable name, which follows the same naming rules as JavaScript, so we can do something like x. Then we're going to declare the type that we want this variable to be. Now, this is where the static typing comes in. So I say var x, and if I want this to be a string, I type string, and then I can say this is equal to hello world. Now, I actually don't need a semicolon here. Okay, there you go. We've just declared a variable named x. The type of this variable is a string, and then we can assign a value to it if we want. We don't need to assign a value. I can just put var x string, and then what will happen is that this will be equal to the default value for a string, which is going to be an empty string. Now we'll have a look at this in one sec. In fact, you can see here, if I highlight over x, it says x is declared, but it is not used. Now this is a compiler error, meaning if I try to compile my code right now, it's actually not going to work. It's going to error out because of this issue. So what I need to do is I need to use this variable. So I can say fmt.println, and then I can print x, and now our program should actually compile. Now, excuse me if I keep adding semicolons. You don't need them in Go, but I'm just used to it from JavaScript. Okay, so let me actually build this here. So go build demo.go. You can see it builds, and then we can run our program demo.exe, and nothing happens. The reason nothing happens is because I declared x as a string type here, and when I do this without assigning a value, what happens is x will be equal to, by default, the empty string, which means we don't see anything. But I could do something like hello. And now if I do this, let's go actually go run and then demo.exe, demo.go, you'll see that we get hello. Okay, so that's the basics on declaring a variable. Now, obviously, we can use different types. So I could do something like a uint32. Now, notice if I do a uint32 here, now all of a sudden we get an error, and it says cannot use hello as uint32 because hello is a string type. So instead, we need to use a value that's going to be a uint type. So in this case, I could do something like 12. Again, if I try to do -12, we get an error because we can't store a negative value inside of this uint type. Now, don't worry, there's easier ways to declare variables. You don't always have to do this, but for now, we're just looking at it in this way. Now, let's change this actually to be something like uint8, and let's try to store a value like 1,000. Notice when I do that, I get an error here. It says cannot use 1,000, untyped int constant as uint8 value in variable declaration overflows. That might not mean a lot to you, but essentially what this is saying is that 1,000 is too large to store inside of the uint8 type because we don't have enough bits to represent this value. But we can go up to something like 100. That'll be fine. And if we run here, we can print out 100. Okay, so that's the basics on declaring a variable. You do var, whatever the name is, then the type, and then you make that equal to whatever you want. If you don't set it equal to something, you get the default value for that type, which usually you can guess. In this case, for uint, it's going to be 0. For an int, it's going to be 0. For a Boolean, it's going to be false. For a string type, it's going to be an empty string, okay? And you can kind of go through the rest of those, and you'll see what the default types are. Now, as well as creating our variables here, we can create constants. So if I do something like const x uint8, and I can make this equal to something like, I don't know, let's go 2 here. And now if I run my code, you can see that we print out 2, and that's fine. All right, so that is the constants. I don't think we need to go through those. Obviously, that just means we can't change this value, whereas if we use the var keyword, then we are able to change x and set it to be equal to something else. Okay, I don't think there's much more for me to go through in this video. I just wanted to show you how you declare variables and the different types that we have here inside of Go. Don't worry if you don't have all of them memorized. We'll continue to learn more about them as we go through the rest of this section and see some more Go code. Now, this is a special operator in Go that allows us to declare variables more quickly without having to explicitly define their type. Now, let's talk about implicit versus explicit. So right now what I'm doing with this variable here is I am explicitly defining its type. It's explicit because I'm writing it out. You can actually see it here, right? I say var x uint8 equals 2. I'm setting manually the type of this to be uint8. However, we don't have to do that. We can actually use another operator in Go called the implicit assignment operator, which will assign a variable, and then it will decide what the type of that variable is, still at compile time, but based on the value that's being stored. Now, this can save you a significant amount of time when you're using more complicated types that we'll look at later. So to use the implicit assignment operator, you declare a variable, something like y, and then you say colon equal to, and then whatever value you want to store. In this case, I want to store 3. Now, I'll just print it out so that we don't get the error here saying we're not using it. So we can say x and y, but notice this is completely fine. Now, what happens here behind the scenes is when Go reads this line during compile time, it looks at the value that y is storing and says, okay, what is the type of this value? Well, in this case, Go will assume that the type is an int. So it will say that y is going to be the int type storing the value 3. Now, I'll show you how we look at that type in 1 second, but we are now implicitly defining this variable. So again, it still has the static type. If I go down here and try to change it, say y equals hello here, we're going to get an error. The reason we get an error is because we can't change the type to a string, right? It's going to be an int value by default, which is what it's saying right here. And if I highlight over this, you can see that it's saying int. So it's just implying what the type is by looking at the value that we have. Now, it's not always clear what the type is going to be, but again, you can just highlight over it and you'll see exactly what the type is. Okay, so we have x and y, and let's get rid of x here, which again is the explicitly defined variable, and let's just use y. Now I'm going to change this to say printf, and I'm just going to print something out that's not going to make a ton of sense. It's going to be %t, comma y. Now what this is going to do is simply print out what the type of the variable is. When I do this, you see that we get an int, okay? So it defined that as an int. Now let's set this to equal to 0, see what we get. Again, we get an int. Let's do something like 2.3. Here, we're going to get a float 64, not 32, 64. We can do something like false. Okay, we're going to get a Boolean. Now, what else can we do here? Not too much. That's pretty much all the types that I showed you so far. Anyways, you get the idea, okay? So we can implicitly assign variables using this operator. Now, you might be asking yourself the question, all right, well, when should I use this versus when should I use this kind of var declaration? Well, the only time you should be explicitly defining variables is when you want to not actually assign a value to them. So what I mean by that is we have a variable, say, var number, maybe this is an int 32, but you don't actually want to give it a value. If that's the case, you can just write the variable like this, and now you've declared, okay, I want to have a variable number, I want it to be int 32, and I'm going to assign a value to it later on. So then you could come here and say number is equal to 10, right? Now we'd still have to use this variable, that's why it's giving us the error, but you get the point, okay? We're able to do this with the explicit kind of declaration of the variable. Whereas I can't do that with a variable like y using the implicit assignment, because for implicit assignment to work, we need to have a value on the other side. Okay, so that's pretty much when you use explicit. Otherwise, just always use this implicit assignment operator. This is the one we're going to use 90% of the time. Again, a few scenarios where you need to do it explicitly, but in a lot of cases, you just do it implicitly using this operator. Now, we also have the ability to kind of set what the type is within the implicit operator. So for example, you saw when we did 0, we got the int type, but maybe we want to have the uint type. Well, if that's the case, what I can actually do here is something called a typecast. Now, a typecast is when I take whatever the type is that I want to convert a value into, and I simply write it, and then I kind of write the function definition here and pass a value inside. Now, when I do this, if I run my code, I get uint, okay? Now I can do this with something like uint32. That's going to work completely fine, and I can typecast different variables. I could even go here and say x colon equals to, and then something like int 64 of y. Now, as long as I use x here, so let's pass that in, even though that's not really going to work properly, you'll see that now we get uint32, okay? Well, actually, sorry, we should have got int64, but we weren't really printing out x. Don't worry too much about this statement. Regardless, just trying to show you that you can use this typecast syntax. Now, just as a note here, there's some instances in which our typecast is not going to work exactly as we expected. So to show this to you, I'm just going to change the example a little bit. We'll go print line. We're going to print x, y. We're just going to declare these in a different order. So x colon equal to, and let's go with -9. Let's say y colon equal to, and then we want to do the uint of x. Now, if I do this, everything might look okay right now. We're not getting any errors on the screen. However, when I actually go and run my code here and print out x and y, look at the values we get. So we get -9, and then we get this massive value here that is definitely not the conversion of -9 to a uint, right? You might think, oh, we're just going to get 9 here. No, that's not how it works. Now, the reason that's not how it works is because we're trying to squeeze a signed integer into an unsigned integer variable. And we can't do that, right? That's not going to work. What's going to happen is we're going to get the equivalent of this as an unsigned integer, but that's not going to be meaningful to us. So you have to be careful when you're doing these conversions, because sometimes you can convert from different sized variables or different typed variables, and you get an unexpected result. Now, we're going to look at this more when we get into arithmetic operations, but I just wanted to kind of hint at this to you and show you what happens if you do this. Now, another example could be trying to convert this to a smaller size int, like an int 8. For example, if I go here and change this to -1000, and then I try to convert this to an int 8, which isn't large enough to store this value, you see here that what we get is 24. We're getting a positive 24. That doesn't make a lot of sense. Well, the reason why we're getting that is because here we have 32 or 64 bits, and then we're going down to using 8 bits, so we just can't store the same information. So we get kind of this weird value of 24. Now, again, we'll talk about this in future videos, just trying to show you what happens here when you use these type conversions. Okay, so I think with that said, that's going to start to wrap up this video. As a quick summary, you have explicit and implicit assignment or declaration of variables. You pretty much only use explicit assignment or declaration when you're trying to create a variable that doesn't yet have a value. Again, the example is something like var number int, like that. If you do this, you create a variable number that has the default value of int, which is equal to 0, and then you can use it later on. That's pretty much the only scenario where you use that. Again, a few others, but they're not very common. Otherwise, use the implicit assignment, where you're going to imply what the type is based on the value you assign to. Sometimes you'll want to have a different type. If that's the case, you can do a cast. So I can cast any value, something like int 8, and then put 0 in here, and now this will be of type int 8. If I want that to be a uint, then again, uint 8, and then that type will be a uint. So what we're going to focus on here in this video is this FMT package. Now, this FMT package stands for format, and this is what we use to, well, format our output and to create specific strings. Now, we've already seen that we can use this println, and I showed you this printf previously. Now, println stands for print line, and it says print line formats using the default formats for its operands and writes to the standard output. Now, what this allows us to do is exactly what the console.log allows us to do in JavaScript. So we can place a string, something like hello, maybe 2. We could place a variable if we had one defined. So let's go x : equals to false, and it will print this out, and it will automatically move us to the next line. So if I run this, you see that we get our output. Now notice here that we get this blank line at the end of the output. The reason for that is print line will automatically print an escape character, which is this \n, which will force us to go to the next line after it's printed. And it will automatically add spaces between all of the different arguments that we place inside of here. So very straightforward, very easy to use. Now, as well as print line, we have something known as printf. Now, printf stands for print formatted, and this allows us to print out specifically formatted strings. Now, this is what we used in the previous video, but what I can do here is something like %t. Now, I'm doing a capital here, and the percent stands for essentially a special character. And then afterwards, I can pass arguments that will correspond to all of the different kind of percent characters or special characters that I have inside of my string. So view this first string here as kind of the template or the format string, and then everything afterwards is an argument that will be passed into that string. So in this case, x will be passed to this %t. %t stands for type, so it will print out the type of x, which in this case is a Boolean, okay? Straightforward. Now, if we want to have more than one character, we just add another one, and now I can do something like XX, and if I run this, I get bool bool. Now, if I add a space here, then we will get bool space bool, okay? So this is one of the many symbols, there's like hundreds of them that you can use inside of here, but I'll show you a few other ones as well. So other than %t, which gives you the type, which can be useful, we can also do something like %v. Now, %v just stands for value. This is going to be the default value. Whatever would be printed by print line, that's what this is going to do here. So I can put %v, and now I get false. And I could do something like the value of x is : and then %v, and you can see that this is kind of how I embed variables inside of my string, unlike the way we do it in JavaScript. Now let's continue. Other than %v, we have access to %b. Now %b is actually going to print out the binary representation of a value. So if we do something like 7, you'll see that we get the binary 111. Okay, not sure why you would want to do that, but that is an option. Other than %b, we have access to %e. So let's say we have a value that has a ton of different kind of decimal places here. This will actually print out the scientific notation of this value. So if I run this here, you can see that we get the scientific notation. Straightforward. Continuing, we have access to f. Now f stands for float. This is just going to print out the floating representation of the value, which is what it's doing right here. You can see it's kind of rounding it a little bit. Continuing, we have %s. This stands for string. So this will just be used to print out the string representation of something. In this case, if we do hello, you see that we get hello. We also have access to formatting some of our different strings here and values that we have. So for example, maybe I have 7.8762, and I want to format this and maybe only print out the first 2 decimal places. Well, I can actually do .2f. This stands for give me 2 levels of precision, or 2 decimal places of precision for my float. So now, if I run this, you can see that we get 7.88. So it actually rounds up for me. Now, as well as just .2f, we can actually add the level of spacing that we want. I know this seems a bit weird, but I can do something like 10.2f. And now what will happen is you'll see that it will actually move our number over such that this number takes up a total of 10 spaces kind of in the printed output or in the row here. There's a ton of other formatting options we can use. Last one I'll show you is what happens if we actually want to include a %. So maybe I want to have the % sign. Well, if I just do %, this isn't going to work. I need to do a double %. So if I do 2%, that actually gives me the % sign itself. Beyond that, we can also embed escape characters. So maybe I wanted to have this inside of quotation marks. Well, if I wanted to do that, I'd have to escape the quotation mark with my backslash, just like we do in JavaScript. So now if I run this, you see that that works. If this ever compiles, and we get the quotation mark appearing here. Okay, that's the basics on printf. Again, when you want to do any kind of special formatting, there's all kinds of options. Feel free to look them up. I'm not going to go through any more. All right, now as well as printf, we have another option here, which is sprintf. Now what sprintf will do is actually create a string for us, but not print it out. So sometimes we want to create a formatted string and maybe pass that to a function, print it out later on in our program, whatever we may want to do. Regardless, we don't always want to print it. So if that's the case, we can use sprintf and we can assign that to a variable. So I can do something like y : fmt.sprintf. And then maybe down here, I do fmt.println and I print y a few times or something. I don't know why I want to do that, but maybe I do. And then I come here and you can see after we give this a second to run that we get that printed out 3 different times. So you just use sprintf if you want to actually create the string, store it in some kind of variable, put in a parameter for a function, whatever you want to do with it, and then you can print that out later on if you want. Obviously, if I get rid of this, well, it's not going to compile anymore, but you would see that this wouldn't print. Okay, so I think with that said, that's pretty much all I had to show you related to the FMT package and to console output. There's a ton of other stuff you can do here with sprintf and printf, and there's a ton of other options in the FMT package, but these are the basic ones that you need to understand. Quick recap, we have printf, that's going to print out a formatted string. We have println, this is going to print out different arguments separated by a space and automatically add a \n. And actually, that reminds me, if I do 2 printfs here, so let's print, I don't know, %v, and then we'll put an x, and I do this a second time here, you'll see when I run this that we actually get the output on the same line. Now, the reason we're going to get the output on the same line here is because we didn't print a \n. So by default, that happens with println, but with printf, it doesn't. So this allows us to print things in the same row. If I want to add a new line, I'd have to manually print out this \n, which would then force me to go to the next line. So then for the next printf statement, I'm on the next line. Now, the arithmetic operators in Go are pretty much the same as in JavaScript. I'll quickly run through them, then we'll have a few examples of using them and how to do some more advanced type conversions. So in Go, let's just do a multi-line comment here. We have the same operators that you're familiar with in JavaScript, so addition, subtraction, multiplication, division, decrement, increment, and modulus. The change here is that we do not have the exponent operator. There is a way to perform an exponent, but I need to show that to you. And that's pretty much it. Now, the main thing we want to focus on when we're looking at operators in Go is not how, add, subtract works. You all know that. It's how we perform these on types that are different. So in this simple example I have on the screen, both x and y are going to be the same type. They're both ints. So that means when we perform this arithmetic operation here, everything works fine and we get 16. However, what happens when we start mixing up the types? For example, we might change this to be something like uint 8. And now notice when I have uint 8 of 7, and I'm trying to add that to 9, I'm actually getting an error here. It says mismatched types uint 8, and int. The reason for that is whenever I'm performing arithmetic, I need to have the same types on the left and the right-hand side. The reason why Go enforces that is because if we don't have the same type, then Go isn't sure what type we should be using for the resulting variable, right? So in this case, it's an invalid type. It doesn't know if it should be uint 8, if it should be an int, etc. So we need to actually tell it by making the operands the same type. So in this case, we have x and y. Now let's make y something quite large, like 1,000. What type would I convert to the other type to be able to perform this arithmetic? Well, in this situation, let's see what happens if we try to convert y. So maybe I go here and I say, oh, this will be a uint 8. Okay, now all of a sudden, this is fine. We can add this. This will be a uint 8 type. We're always going to get the same type back as the type of our operands. So now we have two uint 8 types that we're adding together. But when I run this, you see that we get a weird result. Well, let's give this a second to run. We get 239. Obviously, that's not the result of this addition, but the reason we're getting that is because we converted a larger value to a smaller value. We converted an int value to a uint 8 type. What we want to do whenever we're performing our conversions is we always want to take the smaller type and cast that or convert that to the larger type. So in this case, the correct thing to do will be to go and take our x variable here, which is a uint 8, and convert that to whatever type of y is, which is going to be, in this case, an int. So we would say int x like that. And now when we add these, we would get the correct answer of 1007 because we've done the type conversions correctly. So you need to be very careful when you're doing any arithmetic operations with the types that you're using for both the left and the right-hand side. And if you are doing a conversion, you need to make sure you convert the smaller type to the larger type so that you don't lose information in something called an overflow. What occurred in the previous example is we had a value that was too large to store inside of the container of uint 8. So we got an integer overflow, which means we lost a significant amount of data and we're left with whatever the resulting bits were, which gave us kind of a weird value, all right? So that's the first thing to look at with arithmetic. Now let's have a look at when we use, say, division. Okay, so same example here. We can take, actually, in this case, let's go y and divide this by x. Now, when I do this, again, I need to do my type conversion. So I could just actually make x a 7 here, and that'll be fine. But notice when I run this division here, that I'm actually not going to get a decimal value. What I'm going to get is an integer value. So remember, I always get the same type out as the types that I put in. So in this case, I get 142, which is essentially the math.floor of whatever the division of 1000 by 7 is. If I wanted to get a floating value and I couldn't convert these two types beforehand, then I would need to convert both of these types to be float 64. So if we go float 60, not floor, but 4, then you can see here when I run this, that now we will get whatever the floating point result is. Let's give it a second to run, which is this value right here, okay? So just keep that in mind. Always, you're going to get the same type out as the types you put in. You need to do the correct type conversions. If you're doing something like division, then you need to use float 64s for both of your values or float 32s, but I'd recommend 64 to be able to get a decimal value or floating point value. Okay, I think that's pretty much it. I guess we could quickly go over string concatenation. So if we have hello here and hi or something, obviously we can add these, so we can go x plus y. This is just a standard string concatenation. And if for some reason for our y, let's change this to be something like 2. If we wanted to add this to hi and we wanted this to be added as a string, then I would need to convert y to a string. To do that, I could simply use the string cast here. So what's the error here? It says conversion from an int to a string yields a string of 1 rune, not a string of digits. Did you mean fmt.sprintx? Okay, let's quickly have a look at this and then I'll go over that. So go run demo.go and you see that we actually get this kind of weird looking character. So the error that this is showing us here is that when I convert an int to a string using the string function, it actually gives me whatever the ASCII representation of that integer is as a string. So it's not giving me the string 2, it's giving me whatever 2 represents kind of in an ASCII format. It's not exactly like that. It works a little bit differently, but it's telling me here that what I need to do if I actually want to convert this to the real representation of that number is fmt.sprint, okay? So we'll use that instead, fmt.sprint here. And now if I run this, you'll see that we'll get high and then 2. Come on, let's give this a second to run here. There we go. That is now working properly. Hopefully that makes sense why that was occurring, but if you use the string function, you're going to get the kind of representation in an ASCII format or UTF-8 format, whereas when you use sprint, you'll just get whatever the literal string is of the number or whatever it is that you're trying to convert. Okay, now we've gone through the basic operators. Also just mentioned we have plus plus and minus minus here in Go, so I can do something like y plus plus. That's valid. I could do y minus minus, and we have the mod operator as well, so I can do something like y mod 2, etc. Okay, perfectly fine. Now let's have a look at another package here known as the math package. Let me get rid of all of this. So inside of Go, we can import the math package. By the way, if I want to import the math package as well as the FMT package, I can simply put a set of parentheses here, and then I can separate this, actually not with a comma, but with a new line, and I can import all of these things from the same import statement, okay? So it's kind of a weird syntax, but you can just write different packages that you want to import inside of quotation marks or inside of, parentheses here, as long as they're separated by a new line. And if you do that, you'll import all of them. Now, the reason I'm showing this to you is because there's a bunch of math functions that we can use from the math package, so I figured it'd be good to see them. So let's do the following, fmt.println. And then if we want to use the math package, we write math dot, and then whatever function we want. You can see there's a ton of different functions here. Obviously, I won't go through all of them, but you can probably just guess what most of them are. So in this case, we could use math.min. Notice we have a capital for the M here, and I could do something like 4 or 5. And then if I run this, it's going to tell me whatever the minimum of these values are. In this case, that would be 4. Now, as well as min, we have the max function, so we can use that. We also have the square root function, so sqrt. That'll give us the square root of an individual value. In this case, that would give us 2. We have access to the pow function. Now, the pow function will actually raise a base to an exponent. So this is how you implement an exponent in Go. I could raise 4 to the exponent 2. If I run this, you see that we will get 16. Let's give this a sec to run here. Okay, there you go. So if you want to do an exponent, you have to use math.pow. We also have access to round. So if I want to round a value, something say like 4.245, if I run that, you'll see that we will get the value of 4. And then we have access to the ceiling function. Okay, this is going to always round up, as well as to the floor function, which will always round down. Bunch of other ones, but those are the notable ones that I wanted to show you. Okay, so last thing to go over in this video is how we do a conversion from a string value to an integer value, because it's possible we may actually want to do that, and we need to see how. So let's say that I have my variable of 1, 2, 3, 4. Well, how do I convert this into a number, right? Or into an int? Let's try the naive approach where we go y = 2, and then we take an int and we wrap x inside of here. Notice if I do this, it says cannot convert x, variable of type string, to an int. So I actually cannot directly use a string inside of my type conversions here, inside of my type cas. What I need to do is use a special package from Go that will do this conversion for me. Now, there's a bunch of ways to do this, but the most popular way is to use the string conv package, which stands for string convert, okay? So now, if I want to convert this string into its decimal representation, I can go string conv, like that. If we spell this even remotely correctly, dot, and then there is a bunch of different options. Now, the first option is to use a to I. Now, what a to I is going to do is it's going to take a string and convert it to an integer. So if we have a look at it here, it says a to I is equivalent to the parse int. Don't worry too much about that. We'll look at that in a second. And what it does is take in a string value, and then it returns an int and an error. So we're going to say y, comma, error, := string conv a to I. We're going to pass x, and we're going to say fmt.println, and we're going to print y and error. Now, you might be a little confused here with the error. What's happening is this is returning 2 values. y, which is going to be the converted integer value, and then an error telling us if an error occurred when it attempted to do this conversion. So what I can do is print out both of these here, and we'll see that for our error value, we should get access to nil. So it's telling us, hey, there was no error, so we just have nil, and then it gives us the actual int representation here of 1, 2, 3, 4. You can see again, if we hover over this, it returns an int. All right, so that is A to I. Now let's see what happens if there's an error. So if I go 1, 2, 3, 4, and then hello, and then we run this here, you'll see that now we should get an error value being returned. So it just gives us a default value, of 0. And then it says string conv A to I, parsing 1, 2, 3, 4, hello, invalid syntax. It's not able to parse this because, well, this is not a valid base 10 number. Okay, that is A to I. Now, as well as A to I, we have access to this parse int, as well as many others. We have parse float, we have parse boolean, we have all these different parses, but the one we're mostly going to use here is parse int. What we do now is we pass some string that we want to parse, but we also need to pass the base, so in this case 10, and then the bit size, so the size that we want to use to store our value. So I could do something like 8, or 16, or 32, or 64. So what I'm really doing here with this argument, which is the bit size, is I'm saying how many bits does this number need to fit inside of? Okay, so I could do 64, could do 32, could do 8, don't need to worry about it too much. Most cases, we're just going to put 0. And if we put 0, that means don't worry about that. Just see if it fits inside of the int 64 type, which is what's going to be returned to us by default. So now if I run this, you see that this should work fine. And it gives us 1, 2, 3, 4, and then again, nil because no error occurred. All right, so that is parse int. If I wanted to get a binary number, right, I could do 2 here. And now if I'm doing this in base 2, you'll actually see that we get an error here. The reason we get an error is because this is not a binary number. So when we attempt to convert this, reading this as a binary number doesn't work. But if I change this to a valid binary number, and then I go ahead and run this, you'll see that now we should get a response. So this is actually the number 123 in decimal. We read it as a base 2 number. So hopefully that's making a bit of sense. Again, a ton of different options you can use here. You don't need to memorize them. Just trying to show you a few different things we can do here, because as you've seen, it gets very strict with the types. We need to be very careful what types we're using and how we're converting those different types. So quick summary, we have pretty much all the arithmetic operators we have in JavaScript. We're missing a few, but don't worry about those too much. When we're using the arithmetic operators, we need to assume that whatever types go in are the type that is going to come out, meaning we need to be careful about the types that we use when we're doing the arithmetic. Oftentimes, we need to do a type conversion to convert one of our types to the larger size type such that we can then do that operation. When we're using strings and we want to convert a string to an int, we can use the string conv package. We can use parse int or A to I. And we also have access to the math package, which gives us a bunch of helpful math functions similar to the ones we saw in JavaScript. All right, let's begin here with conditions. So just like in JavaScript, a condition is any expression that evaluates to true or false. When we're writing conditions, we're typically using our comparison and logical operators. The comparison operators, as a reminder, are the following. In Go, we do not have access to the triple equal sign. In fact, we don't even need the triple equal sign because we are statically typed, meaning if we're comparing different types, that's not going to work anyways. So we have less than, greater than, less than or equal to, greater than or equal to, is equal to, and not equal to. Again, no need for that triple equal sign or that does not and then double equal sign, okay? So now let's look at a few sample conditions. Let's say we have x colon equal to a uint of something like 8, and then y colon equal to something like 10, and then z equal to x less than y. And then we go, not console.log, fmt.println, and then we print out z. Now notice here we're getting an error. Well, first of all, we need to import fmt. But second of all, we have cannot compare x and y mismatched types, okay? So just like when we're doing our arithmetic, when we're using comparison operators, we need to have the same type on the left and right-hand side. So in this instance, what I would do is I would convert x into the same type as y. So I would need to make this an int for this comparison to work. Now, as a note here, if I did something like x less than, and then I did a value like -9 here, and we have a look at this, this is not going to work. Again, it doesn't work because -9 is an int type, and this is a uint type. But if I go with something like 9, this actually does work. Reason it works is because 9 can be treated as a uint type. Since I don't have an explicit value for 9, and I'm just writing this in here, even though if I were to assign it to a variable, it would get the type of int. Here, since I'm using it in an expression where the left-hand side operator is a uint type, this will default to a uint type. I know, seems a bit weird. You don't have to fully understand this behavior, but whenever you're using a literal value like this, Go will attempt to convert that value on your behalf to whatever it needs to be for the comparison to work properly. So in this case, it works because we can convert 9 to a uint and it will fit inside of that uint type. Maybe that makes sense, maybe it doesn't. Anyways, we'll move on now. So we have these operators. Of course, if we want to do an equivalence check, we can do the double equal sign. Again, if we're using different variables here, or different types, I have like an int of 5, and I compare x and y. Again, we're going to get this error saying that they're mismatched types. Okay, that is it for the comparison operators. Just make sure you use the correct types. Next, we have our logical operators. I don't need to demo them. We have OR, which is this, and which is the 2 ampersands, and the exclamation point, which is the not operator. Works the exact same way as in JavaScript. Again, we don't need to go through a demo. Now we can quickly have a look at how we can write an if statement inside of Go. So the if statement is going to look very similar to JavaScript. We write if, we write some condition. Notice I don't need the parentheses here. I can just write a condition. So I can have something like x colon equals 2, and say if x is less than 3, then go ahead and do this, which might be fmt dot print line, and then something like run. Okay, if we want to add an else if statement, we can write else if and then put the condition here, x is greater than 4, then go ahead and do this. And then if we want an else statement, we can tack that on at the end. Just like in JavaScript, we can have as many else if statements as we want. So if I add another one here and say greater than 7, then that is perfectly fine. Not sure why this is giving me the error here. It's because it needs to be on the same line. Okay, so notice you have your curly braces. You don't need the parentheses. And then again, anything inside of the body here is going to run if the condition is true. Just like other languages, you can nest other if statements inside of here, no problem, and do whatever you need to do. Now, the switch statement in practice works the same way as it does in JavaScript. There's just a few different features and functionality of it, so I want to show that to you in this video. So let's begin by just creating a variable. We'll say a is equal to 1, and then we'll switch on our variable a by creating our switch statement. Notice here I don't need my parentheses like I would have in JavaScript. Okay, so I have switch a, and then what I'm going to do is create some cases. So I'm going to say case, something like 1, and then inside of here I could do something like fmt.println, and then 1, and then of course I need to import the fmt package for this to work. So import fmt. Now I can make another case, so we can copy this and go case 2, and change this to say 2. And then if we want, we can add a default case here. We can say fmt.println and something like default. Okay, so if I go ahead and run my code here, you'll see that we will go inside of case 1 and we will only print case 1. Now notice here that I did not need to include my break keyword after my cases. In Go, you automatically will break once the case is finished. So essentially everything that comes after the colon before the next case will only happen. So you're not going to fall through automatically to the other cases like you would in JavaScript. However, there is a way to fall through, which I'm going to show you in 1 second, but now I quickly want to look at the naked switch statement. So usually you need to put a variable here, right? So switch on a, and then you're checking for all the different values of a. However, in Go, you don't need to do that. You actually can exclude the variable, and instead you can write conditions for your different cases. So I can do something like a is less than 1, a is greater than 2, and now I have what's known as a naked switch statement where I have some different conditions inside of the switch that I'm checking. So kind of just like an if-else if block, you're going to check the first condition. If that's true, you go into this case, and then you ignore the rest of them. If it's not true, you go to the next one, you check it. If it's true, go in here, ignore the rest, until eventually you potentially get to this default, which kind of acts like an else statement. So if I go here and I run, you will see that we get the default because a was not less than 1 or greater than 2. However, if I say less than or equal to 1, and let's do something like this, less than -1 just to show you here, you'll see when I run this code that we will only get 1 printing to the screen. Let's give this a second. We don't get 2, even though this case is true because we went into this case and we didn't fall through into the other cases. So this is a naked switch, just something useful to know. Now, as I was saying before, we do have a way to actually trigger a fall through. So what I can do is write the fall through keyword, if I write fall through, what will happen is it will automatically pass me down into the next case. Now, there's a variety of reasons you may want to do this. Sometimes you want to trigger one case, and if that case is true, you want to continue falling throughout the rest of the different cases. So let's write a slightly different example that will actually make sense with the fall through. So what I'll do here is I'll write a case, and I'll say case a less than -1, and then I'll say fmt.println, and then a is less than -1. And then I'm going to fall through. Now I'm going to write another case. This will be the same thing, except this time less than 0. And then we'll say less than 0. And then we'll have one last case here. We'll actually remove the fall through, and we'll say a is less than 1, and then a is less than 1. Now the idea here is that if a is less than -1, then it's also less than 0, and it's also less than 1. So I want to fall through into these two different cases here so that I end up printing the accurate information for whatever the value of a is. Now, if a was 0, for example, or if a was actually -1, then that means we're going to go into this case right here. So not this case, just this one. Then we're going to print a is less than 0, and we would print a is less than 1, but we wouldn't end up printing this one. So hopefully you kind of get the idea here of how we might use a fall through, but it allows us to fall through one case into another, and typically the order of your cases is going to kind of dictate how you're falling through. So if I run this with a at -2 here, so it should be valid for all of the cases, you'll see that when I run this, what happens is we fall through. Let's give this a second. And it says a is less than -1, 0, and 1. Whereas if I change this to -1, now we'll only go here. So if I run it now, we get a is less than 0 and a is less than 1. Just an example of how you can use this fall through keyword. Okay, so that's it for fall through. Now, another thing to show you with our switch statements here is that we can actually have multiple values we're checking for inside of the switch statement. So let's change a to something like a character, maybe h, okay? Then we put a here. And what I can do is write a case where I check for multiple values of this character. So I can do something like a, b, and then c. That's actually completely valid. What happens now is I check if a is either a, b, or c. And then I go ahead and run this case. So fmt.println, and I say a is a, b, or c, okay? Perfectly fine. I could also do this in a naked switch statement. So if I removed a here, then I could say a is equal to that, a is equal to b, or a is equal to c. That's completely fine. We can kind of write multiple conditions on the same line. Specifically, I'm going to talk to you about for loops, while loops, and then how we loop through strings, which actually isn't very trivial in Go. All right, let's begin here and look at the for loop syntax. So for a for loop, we write this very similarly to how we would in JavaScript. We write for, we create some variable. In this case, I can do idx. I'm going to use my kind of walrus operator here, or my implicit assignment operator, make this equal to 0. I'm then going to put a semicolon. I'm going to put idx less than 10. This is my condition for looping. And then I'm going to put my increment condition here, or increment kind of statement expression, whatever you want to call it, where I'm adding 1. Obviously, I could change this around. I can make idx equal to something else. I can have a different condition. I can change the increment. Whatever you can do in JavaScript, you can do the same thing here. The syntax just looks like this. So now if I go in here and say fmt.println and I print idx, if we can type that out, we'll see when we run this code that we're going to get 0 through 9 printing to our console because we start at 0 and we go up to but do not include 10, and that's exactly what we get. Okay, that's the for loop. Not much more to go through there. Now, though, I want to show you that inside of Go, we don't have access to a while loop, okay? So unlike in JavaScript where we have while, in Go, what we actually need to do is use the for loop syntax to create a while loop. So what I can do is write for, and then I can write some condition. So I could write, for example, true, and then inside of here, I can loop. So fmt.println, and then loop. Now, obviously, I don't want to execute this code because this is going to be an infinite loop. So what I would probably do is have some variable, something like a less than or equal to 1, and say, well, a is less than 10. And then we can say a++ like that. And now we have a while loop that we've implemented using the for loop syntax. I know, seems a bit weird. That's just how they did it in Go. So if you want to have a while loop, you use for, and you just put a single condition. You don't put the increment and all of that kind of stuff. Okay, so that is looping. Now I want to talk to you about looping through strings. The reason I want to discuss this is because it's not quite as simple as it seems, and strings are a little bit more complicated in Go than they are in something like JavaScript. All right, so let's create a string here. We'll say string is equal to, and the classic hello world. Now, I want to first start by showing you that we have index access on our strings, meaning I can do something like string 0. Now, I can't set that value to be something like s, but what I can do instead is I can access that value, okay? So I can do something like fmt.println, and then I can print my string at index 0. Now let's have a look at what happens if I do this. So if I run this code here, you'll see that we actually get the value 104. Now the reason we're getting 104 is because we're getting the integer representation of the character in our strings. Now this is where it gets a bit complicated, but in Go, our strings are actually slices of characters or slices of bytes. Now we haven't talked about slices yet. You can kind of just imagine they're an array. And what that means is that the actual representation of this string is some kind of data structure that is containing various different bytes. So really when I type hello world, what happens in the backend is we convert all of these characters into bytes. We then store those bytes. And that means when I access string at index 0, I'm accessing the first byte that is inside of my string. Now recall that a byte is simply the uint8 data type. And I can prove this to you if I go here and I type %t like this and run the code. You will see the type of this value here is the uint8 type, or sorry, this needs to be printf, my apologies, not println. And now you'll see that we'll get that uint8 type. Give this a second. And there you go, we get uint8. Now, the reason I'm explaining this to you is because that means if we're accessing the individual indices of our strings, we're going to be getting that byte type back, which means if I want to actually get the individual character, I would need to convert that into a string. So I take string, and then I convert my byte. So let's run this, and now you'll see that we should actually get that first character, which is h. Okay, so that's great. However, now we need to quickly talk about some different encoding formats for our strings and why accessing all of the individual bytes of our string is not necessarily what we want to be doing. So we have this ASCII format, and we also have this UTF-8 format. Now, ASCII is the American Standard Code for Information Interchange or something along those lines. Anyways, this is a standard encoding code that uses one singular byte or 8 bits to represent all of the different characters inside of this encoding. Now, for a very long time, that was sufficient. All of the characters we have, well, we can represent those with 1 byte, which gives us 256 unique values or unique characters. However, as we expanded the number of characters, we ran out of space in ASCII, meaning we can no longer use only 1 byte. We need to have more encodings or more bits or more bytes to represent our characters so that we can have more characters. And that's why UTF-8 came out. So UTF-8 is the standard encoding format. It's used pretty much everywhere. In fact, you can see right down here, it says UTF-8, which is the encoding we're using for these characters right now. And UTF-8 allows for characters like emojis, Chinese letters, and all kinds of other symbols that you've probably seen many times before. Now, UTF-8 actually uses 4 bytes, which allows a lot more possibilities of characters to be represented with this encoding format. That means that if I have a string here, and I have any UTF-8 character inside of this string, we can potentially be using up to 4 bytes to represent that character. If I were to embed an emoji inside of this string, then that emoji would use more than 1 singular byte, which would mean if I were to access all of the individual bytes of my string, I would only get a portion of the encoding for that emoji. I'm not sure if you see what I'm saying here, but it's possible that I have a single character. So I don't have a special character right now, but let's imagine the dash was a special character. I put that inside of my string, and what you'll see is that the length of my string will actually be larger than 1 character. It may be 3 bytes, 4 bytes, etc., because we need more space, more individual bytes to represent that special character. So if I wanted to actually be able to print out that individual character from my string, I would need access to more than just the individual index. So I would need more than index 0. I need index 0 through 3. I need to kind of combine those values together, and that would then represent my entire character. Hopefully this makes a tiny bit of sense what I'm explaining here, but with ASCII, we have 256 values and 1 byte. With UTF-8, which is what we're typically using now, we have 4 bytes and substantially more characters, meaning that I can't just access each index from my string because this is kind of an array of bytes. What I need to do instead is loop through my string in a special way. So let me show you this, okay? Actually, let's go back and have our string. I can, of course, loop through the string in the way that we kind of naively would do. So I could say for idx colon equals 0, and then I can say idx is less than, and there's this len function. Len gives you the length of an object, so like that, and then I can say idx plus plus. Then what I could do is fmt.print, and I'm actually going to print f. What I'm going to do is print %c, which stands for character, and then I'm going to pass here string at my idx, okay? Now, if I run this code, you'll see there's not going to be a problem. This will work fine because we only have ASCII characters inside of here. So let's make this a little bit larger, like hello world. And again, when we run this, there won't be an issue, and we'll get all of the characters printing out to the screen. So we get hello world appearing. However, if we had, again, a special character, this wouldn't work properly. That's why what we need to do instead is use a different syntax, which is known as the range syntax. Now, what range allows us to do is get access to the index as well as the character at a specific position, and range will handle all of our special characters for us. So what I can say here is for I, comma char, colon equals, and then I can write range and the name of my structure, which in this case is the string. Now what I can do is I can print out the char like that, okay? And then this is going to work the same way, except now we'll handle all of those special characters automatically. Now, range gives us the index as well as whatever the value is inside of the thing that we're looping over. In this case, it's the string, okay? So it gives us each character as well as its index inside of the string. Now, in this case, I don't want to use the index, so what I can do is just put an underscore here instead. That's going to get rid of that error that's popping up for this unused variable. The underscore acts as an anonymous variable that we can kind of put as a placeholder. Since I have two things that I'm extracting, well, I need to have two values here, but if I don't care about the variable I just put an underscore and I can kind of ignore that, okay? So now if I run this, you'll see that we get the same thing that we got before. Give this a second to run, and we get hello world. Okay, now just a note here, inside of our for loops, it's perfectly valid for us to use the break keyword, for us to use the continue keyword. Okay, that's valid, so we can use those just like we used in JavaScript. And last thing that I'll show you here is actually if I print out the %t of this char here, you'll see now that when we run this, the type of our character is actually an int32, okay? And the int32 is synonymous with the rune type, which is 4 bytes, okay? Whereas if we went back to that previous way of looping through our string, so we had idx, okay, and then idx is less than the len of the string, and then we have idx plus plus, and then we're printing out the type of string at the index idx, you're going to see now that when we run this, we get the uint8 type, right, which is different than that rune type. There you go. That's the main difference here. Hopefully you understand that. Just know that if you are looping over a string, you want to use that range syntax, not the syntax that I'm showing you here. Now, before I dive into arrays and get into this video, I just want to mention that kind of from now on in this section, a lot of the stuff we're going to be learning will be a lot different from what we learned in JavaScript. So even though we might have the same name, like an array, we're going to have a lot of different behavior. So just make sure that you're not making too many assumptions and assuming that because you know something in JavaScript that it applies here in Go. Some stuff is similar, but as I've said, a lot is going to be different. So make sure you're paying attention and kind of carefully noticing all of the differences here in Go versus JavaScript. Obviously, I'll try my best to point all of them out. All right, so let's start talking about arrays. Now, arrays are a fixed-sized data structure that can store values of the same type. Now, already this is different from JavaScript, and this is going to more closely resemble the arrays that we learned in the data structures and algorithms section. So let me show you how we make an array. So I can create a variable here, and I can say var, something like arr, and then I can define the type of my array. Now, the type of an array actually indicates its size. That's because in Go, arrays are a fixed size, which means I have to specify the size and the values that are going to be stored inside of my array. So what I've done here is that I'm having a variable, it's called array, and the type of this variable is an array that stores integers of size 2. Now, this type is different than this type, okay? Let's type this out, 3int. Yes, they both are int arrays, but this is an int array of size 2, and this is an int array of size 3. So this is the entire type, okay? It's not just int with the array. This whole thing is the type. I know it's a little bit confusing, but the size of the array is very important, and once we initialize an array, we cannot change its size. We can't grow it, shrink it, delete it, etc., and all of the values inside of our array will automatically be initialized. So if I type fmt.println arr here, you'll see that if I go and run my code, that the values inside of my array are going to be whatever the default value of this type is, which in this case are int. If I made this something like a Boolean array, and then I ran this, you'll see that we get false. So give this a second here. We have false, false. Okay, so very important, when we are initializing these arrays, they start at whatever size, and we cannot change that size later on. Now, there's a variety of different ways to go about creating these arrays. What I've done is initialized one using the var syntax, but we also can initialize arrays using the implicit assignment operator. So to do that, I can do something like array, colon equals 2, and then something like 2 int, and then I can actually set the values that I want. So in this case, if I run it, you see that we get 1, 2. This is known as an array literal, where I'm actually writing the values inside of my array. And notice that I use my curly braces here for the array, not my square braces, okay? Now, what I can also do is have a nested array. So I can do something like 2, 2. And now, inside of here, I need other arrays. And each of these arrays need to have 2 values. So if I go ahead and run this, you'll see that we now get a nested array. And the reason this kind of works here is because what I'm saying is, okay, I have an array of size 2 that contains integers. Then I have an array of size 2 that contains arrays of size 2 that contain integers. So you kind of need to read it like this, where you have a set of parentheses on this type here, and then another set of parentheses here. And you're indicating, okay, I'm going to have a nested array. I have 2 nested arrays, and the type of my arrays are this, okay? So the entire type of the structure we're looking at right here is 2, 2 int. And just to prove that to you, if I print out %t here, so let's change this to printf, you'll see that that's the type that we're getting. Let's have a look here. And you see that we get 2, 2 int, okay? That's the type of this array. Now, unlike in other programming languages, I can't go ahead and embed a string inside of here, right? All of the values inside of my array need to be the exact same type. It's not as dynamic as a language like JavaScript. Okay, now there is one more way to initialize arrays here that can make things a little bit faster for us. So let's say, for example, we're writing an array literal, and we don't want to count out how many values are inside of our array. Well, if that's the case, I can actually go here and write a ... Now, if I do that, what that means is that the compiler is automatically going to count how many values are inside of the array for us in this literal and initialize the array automatically with the correct value. So now if I go here and run this, you'll see that we get the exact same type, except in this instance, we didn't have to actually explicitly set it as 2. The compiler was able to figure that out by simply counting, oh, well, you have 2 arrays here, so that means the type must be 2, okay? Kind of just a shortcut that we can use that allows us to not have to count the values inside of our literal, and then makes it so I can quite easily go here and kind of change this right and write 3, 2, and now it will automatically be adjusted to the size of 3, 2. Doesn't mean the size is going to change, just means the compiler sets the size as soon as it reads this line so that we don't have to set it ourselves. Okay. So that is kind of the basics here on creating arrays. Now let's look at a few properties of arrays. So I do have index access to my arrays. I can do something like array 0. If I do that, that's going to be accessing this array right here. And then I could set this. So I can actually mutate my arrays just like I can in JavaScript. So I can set this to something like 10, 11. Now if we go ahead and print out our array here. Actually, what is the error here? Okay. So this is actually a good error to run into. Notice here that I'm trying to set array 0 equal to 10, 11, and it's giving me a red squiggly. It's saying expected operand found, and then this sign. The reason for that is since I'm going to be placing a new array as one of the elements inside of my array, I actually need to make that new array. So I actually need to write here 2 and then int like that. Now, if I write this, what I'm doing is actually initializing a new array literal that I'm then going to nest inside of here. So actually, that was a good error to run into, something that I mess up all the time. You think you can just write out what the array looks like, but no, you actually need to create a new array that's of the type that you're placing inside of here. So now if I clear and run, you'll see that this should work fine, and we get our 10, 11, 2, 2, and then 3, 2. All right. So that is how you access the array at the index. Obviously, you can access as well as mutate and change it. A few other things to look at. We have the ability to see the length of our array. So we can use this len function. So you wrap the array in len, and it's going to tell you the size. So let's go ahead and run this, and you can see that we get the size of 3. Okay. Just as a quick recap here, because this is super important, again, you cannot change the size of an array. It is a fixed size, which means when you initialize it, it's always going to be that size, okay? Can't add to it, can't delete from it. You can change what's inside of it, but that's about it. Very inflexible, and that's why in the next video, we're going to learn about something known as slices, which are a more flexible version of our array. Now, last thing to look at here is how we loop through our arrays. So if we want to loop through the array, we can do something like I value colon equals, and then the range of our array. Now what I can do is fmt dot print line, and I can print I and value. That's going to give me all of the nested arrays inside of my array. So let's have a look here and make sure that this works. There you go. We get the index as well as the value. Now, if I wanted to loop through the nested arrays, I could continue here and go with for j, comma, and actually we'll call this nested. Get rid of this. And then we'll say value colon equals range of nested. And then we can say fmt dot print line, and we can print out the value. And if we don't care about I and j, then we can just put an underscore here for those. Go ahead and run our code, and you will see as I do this that we get all of the different values inside of our array. Okay. Last thing to go over here is what happens when we use arrays inside of functions. Now, I know we haven't looked at functions yet, but I'll just quickly show you an example of what happens if we pass an array to a function. Then we can touch on this more in later videos. So let's say we make a function. Let's just call this function something like test. Okay, for this function, what I'm going to take is an array. So what I will do is actually write to int, and then we're going to call this our array. And I believe we put this before the parameter name. I always forget that, okay? So we have our array. All I'm going to do inside of here is say array at index 0 is equal to a new size2 int array that contains 100 and 100. Then what we'll do is inside of here, we'll pass our array to the test function, and then we'll say fmt.println the array, and let's change this to actually be the size 32. All right. So what we're doing is we have our array, we've initialized it, we're passing it to this test function. This test function is taking an array. Notice I had to specify the type of the array as an array that contains 3 nested arrays that have 2 integers inside of them. Then what I'm doing is mutating the array, and what I want to show you with this example here is that when I run the code, you'll actually see that we don't end up changing the original array from inside of this test function. So you can see that we passed the array. Inside of here, we made a change to that array, and if we were working in JavaScript, what would have happened is that would have actually mutated the original array. However, in Go, that doesn't happen. By default, when I pass an array to this function here, I'm actually passing a copy of that array, which means when I try to make a mutation here, I'm mutating the copy of the array, not the original array that I passed. Now, things change slightly when we talk about slices, and there is ways to modify this underlying array. However, we're not actually doing that. So I just wanted to quickly show this to you in case you were wondering. When I pass this to a function, I don't mutate the original array unless I pass what's known as a pointer to the original array, which we're going to talk about in future videos. Don't mean to confuse you here at the end, just trying to show some more advanced use cases of this. Okay, last thing here. This is 3.2, right? So if I change this to 2.2, notice that we actually get an error here. For this error, it says cannot use ARR, value of type 3.2 int as 2.2 int value and argument to test. Essentially, the point of this example is just to show you that the type of 3.2 int is different from the type of 2.2 int. That means the size of the array is associated with the type of that array. Now, slices are a much more flexible version of arrays in Go. We're almost always going to use a slice, but in order to understand how a slice works, we first needed to look at arrays. So let's discuss a slice and see what it actually does. First of all, a slice is a view of an array. So you always have an array, but the slice allows you to view a different portion of that array and then to kind of increase the capacity of that array or decrease it. You'll see what I mean in just a second. So to make a slice, we can either have an array that we take a slice of, or we can make a new slice and that will automatically create a new array for us. So let's do the first option here where we have an array. Let's say we have ARR colon equal to, and then we do something like, I don't know, 4 int, and then 1, 2, 3, 4. And in fact, let's go with size 5 here just to make this a little bit larger. 1, 2, 3, 4, 5. Okay, now let's make a slice of that array. So I'm going to say SL for slice is colon equal to array. Then I'm going to put a set of square brackets and I'm going to use the slice operator, which is this colon. Now, if you've worked in Python before, you may have seen this, but if not, don't worry. The way this works is you're indicating what portion of the array that you want to view, okay? So a slice, again, is a view of an underlying array. When I do this, it's going to give me access to the underlying array, starting at the very first index if I leave the left side here empty, and to the very last index if I leave the right side here empty. However, I have the option to specify different indices. So if I specify index 3 here, what I'm really saying is I want to view the underlying array up to, but not including index 3. So that means I'm going to view these first 3 elements. To show that to you, let's print out SL here and have a look at this slice. Okay, so when we run this here, we get 1, 2, 3. We've sliced from the beginning up to, but not including the third element, so we get 1, 2, 3. Now, if I were to do 1, 3, that means start at index 1 and include index 1, so we're going to view 2 and 3. So if I run this here, we get 2 and 3. Come on, hurry up here, let's run, all right. And then if I go 1 colon, that means slice from the first index up to and including the very last index of the underlying array, so 2, 3, 4, 5. We'll talk about a few more properties of slices, but first let's see how we have index access to our slices. So if I access index 0 of my slice, what that's going to give me is the first element in the slice, okay? So it's not giving me index 0 of the underlying array, it's giving me index 0 in the slice, which is 2, because that's the first element of the slice. I know it can be a little bit confusing, but when I use index access on the slice, it's referring to the elements inside of the slice, which are a part of the underlying array. Okay, now I also have the ability to mutate my slice, so I can do SL0 is equal to, say, 100. Now let's see what happens when we print out the slice, as well as the underlying array here. So let's clear and run, and see what happens when we modify the slice. Notice when we modify the slice, we also modify that element at the underlying array, okay? So here with the slice, we've said slice at index 0 is equal to 100. So for the slice, we get 100, 3, 4, 5. But really, the way that works is that we mutate the underlying array. We change whatever that slice index is referring to, which is this element right here, to be 100. And then that means as we view the slice, we then view that changed element. So any change I make to the slice affects the underlying array, and vice versa. Any change I make to the underlying array affects the slice. To illustrate this a bit more, let's have a look at what's actually involved in creating a slice. So when we make a slice, we have 3 properties, okay? We have a pointer, we have a length, and we have a capacity. Now let's start by viewing those. So we have the slice, we have the length of the slice, and then we have something referred to as the capacity of the slice, okay? Now to illustrate the capacity, I'm just going to slice up to the 3rd index here. Let's clear and run, and then I'll talk about what those are. So we can see here when we print this out, that we're going to get the length of the slice is 3. That's the current number of elements inside of the slice, and then the capacity. Now the capacity is how much larger I could make this slice. Now the capacity has to do with the underlying array. So when I create my slice, I have a pointer. Now this pointer is going to point to whatever the first element in my slice is in the underlying array. So in this case, I have array, and then I'm starting at the very first index of my underlying array. So I'm creating a slice of this, and that means that my pointer goes to array at index 0. If I change this to 1, then I go to array at index 1, okay? So then I'd be pointing to here. Now the length refers to the number of elements inside of the slice. So in this case, when we have kind of index 0 to 3, that means we have a length of 3. And the capacity is the number of elements that exist from the pointer, which in this case is going to be array at index 0, until the end of the underlying array. So in this instance, our capacity is 5. Now let's see what happens if we change this slice to go from 1 to 3. If I do this, and now I run, you see that my length changes to 2, and my capacity decreases to 4. The reason my capacity decreases is because now my pointer is starting at this element right here, index 1. So my pointer is array at index 1, which means I can only expand the slice 4 more positions, right? Or I only have a total of 4 positions after this pointer. So my capacity decreases, and in this case, so does my length. The reason why we have this capacity is because we can re-slice or expand the size of the slice. To do that, I can take a slice of the slice. So I can say SL colon equal to, and then slice, and then I can say colon up to, and then I can increase this to the capacity, okay? So actually, sorry, this just needs to be an equal because this variable is already declared. So now when I do this, you'll see that what happens when I print out my slice is that I get all of the elements that were inside of the underlying array, starting at where I first sliced this slice, or where I first sliced this array. I know it's a little bit confusing, but now we get 2, 3, 4, 5, a length of 4, and a capacity of 4. We're at capacity because we've increased the slice to go up to whatever the capacity of the array is. The reason why this is kind of important to understand here is because depending on where you begin your slice, that tells you how many more elements you could expand the slice by. So you can take what's known as, again, a slice of a slice, which is what I just did, and that allows you to expand the size of the slice. There's a lot more stuff we can do here, but I'm just trying to give you kind of the underlying information about how this works so that you understand this length and capacity kind of property of the slice. Again, a slice is a view of an underlying array. I'm viewing a certain number of elements. The number of elements I'm viewing is the length, and the number of elements I could view, so that I could increase the slice to, is the capacity. So what I did here is I now changed the length of my slice to go up to the capacity, which allowed me to view all of the elements that were from the starting position to the end of the underlying array. All right, so that's kind of the first thing to look at here in terms of slices. Now let's have a look at how we create slices without first having an underlying array, and then kind of what we can do with them, like appending to them, iterating over them, etc. So again, just keep in mind, very important, for the slice, you always have a pointer to the first element of the underlying array you're referencing, then a length and a capacity. If you know that, then you'll really understand how slices work. So to create a new slice without first creating an underlying array, we can do the following. I can say SL colon equal to, and then I can just do this kind of array syntax without specifying the size. So I can do something like string, and then I could say hello, comma world, and then fmt dot println, and then SL. Now this is different than an array. What I'm making is a slice, not an array, which means what will happen implicitly is an array will be created, and the pointer for this slice will point to that underlying array. Then the slice will have a length equal to 2 and a capacity equal to 2. So it seems like it's the exact same thing as an array, but this is a more flexible type that we can do some more stuff with. So when I print this out, we get hello world. And if I print out the type of this, %t, you'll see that it's not going to tell us to string. It's going to tell us slice of string, which is this empty set of parentheses, or empty set of brackets, sorry, okay? This type is different than the to string type. This is the slice type. This is the array type. So that means that now, again, in the background, we have an underlying array that has these two elements. We are then pointing to that array, and then we have our length and our capacity. All right, so now that we have this slice, I want to look at an example of appending to the slice. To do that, I'm just going to create a for loop here. And I'm going to say for x less than 0, and say x, sorry, not x less than 0, x colon equal to 0, x less than 10, and then x plus plus. And for every single value of x, we're going to append something inside of the slice. So we're going to say SL is equal to append. We're going to append to the slice, and we'll just append Tim, okay? Then we're going to say fmt dot println. We're going to print the slice. We're going to print the length of the slice and the capacity of the slice. Okay, I'll break this down because I know I just went through a few new things here. So we have our slice. Again, remember this points to an underlying array. We're then looping through x here. We're going to do this 10 times. And what we're doing is using this append function. Now, what the append function does is allow us to add an element to a slice. The way it adds an element to a slice is by doing one or two things. It looks at the slice and it says, okay, is there capacity in the underlying array for me to add this element? If there is, then it adds that element and it re-slices the slice and gives me a new slice that contains that view of the underlying array, okay? Which is why I need to actually say SL is equal to append. I'm reassigning whatever the new version of the slice is to this slice variable. So append is returning to you a new version that contains the original slice with this added element. That's how the append function works. Then what I'm doing is printing the length of the slice and the capacity, because you're going to see that things work a little bit differently than you may anticipate. So let me run this and we'll just kind of explain what's going on here. Okay, so let's, actually I need to run this one more time just so we have a bit more space. Okay, so we print hello world, 3, 4, hello world, Tim, Tim, 4, 4. And notice here that the length and the capacity are not always the same. So what happens the first time we call this append function is the capacity of our slice is 2 and the length is 2. That means that we don't have enough room in the underlying array to add this new element. So what we actually do is create an entirely new underlying array, and we double the size of that underlying array. So what happens was we had a size of 2, or a capacity of 2. We then doubled that size to 4, which is the new capacity, and we added our new element into the slice, which was Tim. Again, this gets added to the underlying array. Now we have enough room because we doubled the size of it. So again, in that append operation, we increase the capacity by creating a new underlying array, then taking a slice of that new underlying array that now has those 3 elements. Now we do the append operation again. This time, since there was capacity, we didn't need to change the underlying array. We just added this new element in the last index of that underlying array and took a new slice of it and returned that to ourselves. Continuing, we then did the append operation again. This time we saw that we didn't have enough room to add this 5th element, so we doubled the size of the slice, and then we took a slice of the first 5 elements and put Tim in that 5th position, okay? We then continue this. Notice here we didn't need to change the underlying array because we had capacity. Same thing here, same thing here. Then we get here and we again doubled the size of the underlying array by creating a new one, copying all of these elements inside of a new array, and then adding Tim as the 9th position, taking a slice of that array and returning it to ourselves. Now we continue this process over and over again, and the reason we constantly double the size of the array is so that we don't always have to create a new array. Because every time we have to make a new array, that's a big O of n time operation, whereas if we already have the array, then it's a constant time operation to perform this append, because all we do is return a new slice. I know this is a little bit confusing. I did warn you, arrays and slices are a bit more challenging than in JavaScript, but I want you to understand mechanically what's going on here. We have that pointer to the first position of an underlying array. We then have a length and a capacity. If I try to append, I first check, do we have the capacity? If we don't, we need to make a new underlying array, change the pointer of our slice, copy the existing elements into that new array, and then add the new element that we're appending. Then we now will have capacity for potentially more elements, so every new append, we repeat this operation. If we have capacity, we can just add the element. If we don't, we need to create that new array, which takes big O of n time. Okay, so that is append, and just as one more clarification, if you try to just write append here, you're gonna see this doesn't work. The reason it doesn't work here is because this returns a value to us that we're not using. This isn't gonna really mutate the slice. It's gonna return a new slice to us, which we then assign to this slice variable, which is perfectly fine. Okay, now that we've looked at that, let's see a few other ways that we can make some slices. So I can actually specify the size of a slice and the capacity of a slice when I create it. So I can say SL : equal to, and I can use this make function. Now what this make function takes in is the type that I want to create. You can use this for more than just slices, but oftentimes we do use it for slices. So I can do something like this, which means I want to make an int slice, and then I can specify the size that I want this slice to be. So if I want it to be size 10, I put size 10, okay? This essentially creates kind of an empty slice for us that has a length of 10, and the capacity will be the same as the size, which is 10. If I wanted to set the capacity, then I can pass an additional value. If I pass 20, now the capacity of my slice is 20, and the size is 10, okay? Or the length of the slice is 10. So length is 10, capacity is 20 if I use that make function, or I can just pass 10. There's a variety of reasons you may want to use make, but typically you use it when you want to dynamically create different slices that are different sizes. In this case, I just want to make a slice of size 10, so I can go ahead and do that with the make function. All right, last thing to look at here is what happens when we want to iterate over slices and when we pass them to functions. So let's go back to another slice here. So we can say string, hello, world, hi, something like that. If we want to iterate over this slice, we can do the exact same thing as an array. So I can say for I, comma, value, colon equal range SL. And then I can say fmt dot print line, and I can print my I and my value. And if I clear this and run, you'll see that we should get 0 hello, 1 world, and 2 hi. And that is exactly what we get. It's kind of cut off in my terminal, but you can see that's the output that we're getting. And now let's quickly look at what happens when we pass a slice into a function. So let's say we have a function test. This time I'm going to take in a string slice. And we will call this ARR, okay? So ARR, that is of the type a slice of string. Now, first of all, this will allow us to accept any length slice, right? Which is already more flexible than when we were using arrays previously. Now, though, I want to show you that if I go array0 is equal to change this, and we pass this into the function. So we say test at SL, and then we fmt.println the slice, you'll notice that in this example, something different happens than when we used the array. So if I run this, you can see that we actually mutate the slice when we pass this into a function. So in the previous example, when we were using an array as the parameter type for our function call here, what happened was we didn't actually mutate the underlying array. We made a copy of that array, and then we changed the copy inside of the function, meaning this original array was untouched. In this example, we're using a slice. Now remember, a slice has a pointer to the underlying array. So what happens here is I pass in the slice. Since the slice has a pointer to the underlying array, when I make a change here, I affect that underlying array. So I'm actually able to mutate the original slice by passing it through as a parameter into this function, whereas I couldn't do that when I was just using the array. Maybe that makes a bit of sense. I'm hoping it does, but for now you can understand that if you pass an array, you're not going to mutate it, whereas if you pass a slice, you can mutate that inside of the function. Now there's ways to avoid that, but for now I just wanted to show you this so you understand kind of the main difference here and can see how that pointer can affect some of the behavior of our slices. So if we're using the var syntax, we'd have something like var mp, then we'd write map, we'd put a set of square brackets here. In the square bracket, we'd put whatever the type of our key is going to be. In this case, that can be a string. And then we'd associate that with some value like an int. We then could initialize the map. To initialize the map, we could say map string int, and then inside of here, we would have to put strings associated with ints. So I have a associated with 1. If I tried to associate that with a string, notice we get an error because that's not the correct type of the map, okay? So this is how you create a map and then initialize it. Now, obviously, in this instance, we don't need to actually write the var syntax. I could simply say mp equal to the map, and then the type of this will be implied because we already have the type over here. Okay, so the var syntax is a little bit verbose. Just wanted to show you how that works. Okay, so we're going to say mp equal to the map, and then if we go ahead and say fmt.println, and we print out our map here, you'll see that we get a map that contains the key a, that is associated with the value 1, which is exactly what we get there. Now, if we don't include anything inside of this map, that's perfectly fine. We will just get an empty map. And notice that I do actually need to put the curly braces here, even if I don't put anything inside of them. Okay, so that is how you create a map. Now, there's a few other ways to make it. We can also use the make function. So I can write make, and then I can say map, and the same thing. I can do something like string int. In this instance, I don't need to actually put my curly braces. And now we will get an empty map. Let's have a look at this here. And you can see that we get our map. Now, as a note, we could have a more complicated map. So I could do something like map, and then I could have a string associated with maybe an int slice. If that's the case, this is perfectly valid. The type of my map is this, a slice of ints, okay? And then this is the map itself, or sorry, this is the key value, the string. All right, the entire type is this whole thing, and the value type is a slice of ints. If that was the case, I'd need to put slices of ints inside of the map. So I'd say a : and then I'd create a slice, something like 1, 2, 3. It's perfectly valid for me to write this inside of this map kind of literal here, or declaration, all right? Now, if we print this out, you will see that this will work fine, and we will have a, which is our string, associated with 1, 2, and 3, which is a slice. Okay, now let's look at how we add values into the map and some other features of the map. So if I want to add a key value pair, I can do something like mp at the character b is equal to, and then I can create a slice. Now, if I make a slice, I need to actually initialize the slice here because it's not inside of the map literal. So I'm going to say int like that. So this now makes a new slice that I insert at key b, okay? So if I write this here, you can see that now we get a map that has key A and has key B. If I decide to override this key, something like MP at B is equal to int, and I make this an empty slice, for example, you'll see that it will replace whatever was at that key with the new value here. All right, so that is how you add a key into the map. Now to delete a key from the map, you're going to use the delete function. So you write delete, you write the name of the map, and then you write the key that you want to delete. In this case, I want to delete B. If I do that, you'll now see that we no longer have that key B inside of the map. We have deleted it. Notice that I do not need to reassign to my map when I use this delete function. It will actually mutate the map in place, unlike the append function for our slices. Okay, so that is how you make maps, add keys, and delete keys. Last thing we really need to look at here is how we check if a key is present inside of the map. So to do that, we'll do the following. We'll say value, okay, colon equal to, and then we're going to say MP, and then this is going to be at whatever the index is or whatever the key is. So in this case, we could do something like B. Then I can fmt.println value and okay. Now what this is going to do for me is give me the value associated with this key if it exists, and a Boolean saying true or false. Now if it's true, that means the key did exist. If it's false, that means the key did not exist. So when I run this here, you're going to see that we get nothing and then false. The reason we get false is because the key B does not exist. And the reason we get an empty slice here is because we always get the default value of whatever the type is of our map. So if we change the map completely to be like a Boolean, so this is going to be a bit of a change, but if we get rid of this here, okay, so change this, let's say B is equal to false, okay, and then we run this, you'll see that now we're going to get false, false, because we get the default value of the map type, which is false, as well as false, indicating that this key did not exist. Now, if this key did exist, right, so if I run this here, you'll see that we get false and then true, indicating, okay, well, the value is false, and yes, this key actually did exist inside of the map. All right, so that is how you kind of do the main operations on maps. Now let's have a look at a quick example of using maps, just so that we can kind of see how to do this. So I'm going to keep my map up here, and I'm going to have a map of an int associated with a uint. And actually, we'll go map uint associated with another uint. Now, what I'm going to do for this example is I'm going to have some number n. Now, this is going to be equal to 100. And what I'm going to do is loop through all of the different values of n, so going from 1 to 100, and I'm going to see how many of them are divisible by 1, 2, 3, 4, and 5, and then place the number of divisible elements inside of this map. You'll see what I mean as I start going through this. We're going to say number colon equal 1, number is less than or equal to n, and then number plus plus. Okay. Now that we have the number, we're going to loop through 1 through 5. We're going to see if this number is divisible by 1, 2, 3, 4, 5. If it is, then what we will do is add that into the map under the key 1, 2, 3, 4, 5. Again, you'll see what I mean in 1 second. So we're going to say 4, and we'll say D standing for divisor. This will start out being equal to 1. We'll then say D is less than or equal to 5, and then D plus plus. We're then going to say if the number mod D is equal to 0, meaning it's divisible by 0, there's no remainder, then we want to add this into the map. So the way we can do this is we can say MP at, and this is going to be D plus plus, okay? Now what is the error here? It's saying cannot use D variable of type int as uint value in map. Okay, so actually a good error to run into here. The reason why we're getting this is because D by default is going to be int, whereas we have a uint type for our map. So that means that I need to convert this to a uint. Now I can decide to do that here, or I can decide to do that down here. Now notice we're getting another error here, and it's saying number mod D, invalid operation, mismatch types int and uint. What I can do to fix this is I can now come to my number, and I can say this is going to be uint. Now again, we get another error here, right? And it says number less than or equal to n, mismatch types, uint and int. So then that just means I need to go here to n and change this to be a uint. So now all of our types are the same. Okay, so what we're doing here is we're checking if the number is divisible by D. If it is, then we're looking at our map at the key D, and we are incrementing it. Now, some of you may be saying, well, is this going to work if that key doesn't already exist inside of the map? Now the answer is yes, that will work because the default value of every single key inside of our map is the default value of this type, which is 0. So if I say MP at D and I haven't put D inside of the map yet, when I increment this, it just means that the value for D is going to be 1 because the default value is 0. Now that doesn't work in a lot of other programming languages. In some other languages, you might have to do the following. You're going to have to say something like this: quantity, comma, okay, colon equal to, this is going to be MP at D. You're then going to say, if okay, then MP at D plus plus like that. Otherwise, you're going to say MP at D is equal to 1. That's what you'd have to do in some other programming languages, and you actually don't need the quantity. Okay, just wanted to kind of show that to you in case you see this pattern pop up. But in Go, we don't need to do this because we know if we increment the value here, MP at D plus plus, since it always has a default value of 0, then it will go up to be 1. And if it already has a value, then we'll just increase that value. So to make this more clear, let's just print out what the result is here of our map. And then you can see kind of what I'm aiming to do with this example. So let's clear and run. And you can see for our map here that we get 1, 100, 250, 333, 425, and 520. The reason for this is we have 100 values that are divisible by 1, 50 values that are divisible by 2, 33 values that are divisible by 3, 25 divisible by 4, and 20 divisible by 5. So that was kind of the goal of this example here, was to get a map that contained a key, which is the divisor, and then the number of values in our range that are evenly divisible by that number. Now we already know what a function is, but I just want to show you how we create them and use them in Go. So with that said, let's see how we make a function. So to make a function, I'm going to write func, and then I'm going to put the name of the function. So I could do something like add, then I'll put a set of parentheses, and then I will write the body of the function inside of curly braces. Similar to JavaScript here, except when we want to add parameters or return values, we need to actually specify those. So unlike in JavaScript, where we can just write out any parameters we want, we can have any number of return values, or we don't have to have a return value, in Go, we have to define the types of our functions. What I mean by that is we have to do something like num1, and then specify that this is an int. And then something like num2, and again, specify that's an int. And in this case, we'd want to return an int, so we'd specify that right here. Now, the reason for that is because Go is a statically typed language, so just like our variables, we need to specify the types for all of our parameters, as well as any return values. Now, you'll see that we're getting an error here, and the reason we're getting an error is because we don't have a return, and we've specified that we want to return an int. So now that we've done this, this means that this function must return an int value. So what I can do is write return, and then num1 plus num2, and now you'll see this function is valid. Now, just like in JavaScript, to call the function is straightforward. I can do something like value, colon equals 2, and then add, say, 1 and 2, and then fmt dot println, and I can print out my value. So go run, and then demo.go, and you'll see here that we get the value of 3. Okay, so that is how you write a simple function. You specify the name of the function, you write out the different parameter types, and then you specify the return value. Now, one thing with our functions is that we can return multiple values. So if we want to do that, we're going to put a set of parentheses here, and then we're going to specify the values we're returning. So I could return an int, and then something like a string. Then I could come here and return the string hello. And now what I would need to do is have something like value, comma, str is equal to add 1, 2, and then I could print out both these values, and you'll see that we're no longer getting an error. Now note that you always have to use the return values from this function. So I can't just write value is equal to this. I would have to have variables for every single return value. Now I could put an underscore in place of any of those variables if I don't want to use them, but it's just a note that you need to kind of specify those and write them out when you're calling the function. All right, so now let's look at a few more advanced uses of functions here. Obviously, this one is quite simple. So let's get rid of this, and let's make another function that accepts maybe some more values here. So we can say function, I'll call this call func. And what I'll actually show you here is that we can accept functions as parameters inside of our function. So what I can do is something like callable, and then I'm actually going to write func, and I'm going to put here int. Now what this means is that I'm accepting a function as the parameter, so the parameter name callable. This function will accept one integer parameter and return one integer value. Then what I'll do from here is I'll just return and then I'll call this function, and I'll just pass in, say, the value 10, okay? Then I'll come here, and I'll say value, colon equal to, and then this is going to be call function, and what I need to do is pass a function to this. So there's a few ways I can do this. First of all, I can write func, and then something like double number. This will take in an int, and return an int, and this can simply return 2 multiplied by, we need to give this a name, so we'll say num int, okay? Now we'll pass double number, and then we'll say fmt dot println, and then value. So what I've done here is, again, written a function that's going to accept a function, and we've actually done that by saying the type of the parameter is a function. So that's kind of the point of me showing this to you, is that our functions have types, just like slices have types, arrays have types, ints, etc. In this case, the type of this function is a function that accepts an int and returns an int. That's the type. So I can pass any function that has this parameter type and this return value type to this function. It then can call that function and return whatever the value is from it. So in this case, I have double number, but I could have another function. Maybe we call this triple number, and we just do 3 times num, and now this would be a valid function to pass to the call func function. Anyways, let's go ahead and run this, and you can see that we get the value 20. This is working correctly. Okay, so that is how you pass a function as a parameter to another function. Again, very important here that we know the types of the functions that we're writing. Now, just as another exercise here, I'll show you that if I do something like fmt.printf, and then I printf the %t, or the type of the double number function here, you'll see when I clear and when I run that we actually get the type of func int int, okay? So that is the type of this function. All right, now that we've seen that, let's look at how we would do this without actually declaring a separate function. So in Go, you can write things known as anonymous functions. Now, anonymous functions are essentially unnamed functions. What that means is inside of here, what I could do is write func, and then I could do something like x int, and then int, and then I can write the body of my function and have something like return x plus 1. What I've just done is written a function inside of kind of the call statement to this function. So this is a perfectly valid function. It just doesn't have a name, and I can pass this in kind of just like an arrow function inside of JavaScript. So now if I run this, you'll see that we should get the value of 11, and we do because this is a valid function definition. I write func, I write all of my different parameters, I write my return value, and then I can just write the function directly here. Now I could also take this and assign this to a variable. I could say f1 colon equal to this. We need to write this in the correct order, okay? And now I can pass f1 to this function, and the exact same thing would happen. I could also call f1, so I could say f1 like that, okay? Now, just like we can pass functions to another function, we can return functions from a function. So what I can do is get rid of all this and write another function here and say get func. Now, it's possible that what we'll take here is something like a string. Let's just call this str. And now we're going to return from this a function that accepts a string and returns a string. And what we'll do is we'll say return func. We'll say str2 string like that, and then this will return a string. Then here we're simply going to return the string plus string 2. Okay, now we can call this function. So we'll say f1 colon equal to get function. We're going to pass hello here, and then we're going to call f1. We're going to say value colon equal to f1, and then we'll pass world like that, and then we'll fmt dot print line whatever the value is here. I'll explain this in 1 second, but let's have a look at what we get, and notice we get hello world. Now what I've done here is I've written a function that returns to us another function. So I'm returning the function here, and what this function does is take whatever the value that was passed to this original function is and adds another string to it. That string is the parameter to this function. So I've now created a function kind of using this getFunc function that is always going to add whatever we pass to it to the string hello. So that's why when I called f1 with world, it gave me hello world. We could do the following. Value 2 is equal to space Tim. And now if we print value 2, And now when we print this out, you'll see that we're getting hello Tim. So we're using this original F1 function, but getting a different value back because we're passing a different parameter to it. Hopefully this is making sense, just trying to show you how we write these different types of functions and the type of these functions. Now it can get a bit more complicated than this because you can have functions, returning functions, so on and so forth. For example, if we actually print out the type of getFunc, let's have a look at what that is. So we'll say fmt.printf, we'll go here and go %t, and then we'll just write getFunc like that. If I run this, notice that the type of this function is a function string that returns a function string that returns string. So you can see that as we nest these functions inside of each other, it gets more and more complicated. All right, now a few more things to show you with functions. So it's possible that we may have a function, maybe say something like sum, where we want to accept a variable number of arguments. What I mean by that is we may want to accept 1 positional argument, 3 positional arguments, etc. We could accept a bunch of them. If that's the case, what we can write is something like nums, and then ... int. Then we can return here an int. Now what this means is that we're going to accept any number of numbers. That allows me to call the function, let's do that down here. We'll say sum or s : equal to sum like this. So I can call it with 1, 2, 3. I can call it with 1. I can call it with nothing. I can call it with 4, 5, 6. I can call it with any number of different numbers or integers for the parameters, okay? Now this is referred to as a variadic function. You don't have to remember that name, but in case you see it, that's what it is. Not sure if I'm pronouncing that correctly, but it's a variadic function where it has a variable number of arguments that can be accepted. So in this case, if I wanted to generate the sum of these numbers, what I'd have to do is loop through them. Notice here that this is actually going to be a slice, okay? So we don't pass a slice, we pass these individual values, but it gets kind of taken into our function as a slice. It's telling us what the type is right here. So what I can do now is say something like s : equals 0, and then I can say for I, value, equal to range of nums, and then I can say s plus equals the value like that. I can put an underscore here because I don't need I. And then I can return s, and now this will generate the sum of any of the numbers that we pass in. So now I could say fmt.println, we'll print out s, and if we run this, we'll see that we get the sum here, which is 15. And I could again extend this and pass another value like 10. Perfect. Now another thing you can do with this ... operator here is kind of similar to the JavaScript spread operator, where I could actually write a slice here. So I'll need to make a slice. I can say int, how are we going to do this? Slice int, and then I can write a few different values inside of here, but you'll notice it's telling me this is invalid. It says you cannot use this literal because we are accepting int values only. But what I can do is put a ... here after I write the slice, and what this actually does is break down the slice into all of its individual elements and passes all of those elements as individual arguments into sum. I'm not sure if that quite makes sense, but what really happens inside of this call here is I say, okay, I have a slice. Well, I have this slice, but I want to take all of the individual elements out of the slice and pass those as parameters to this function. Well, I can do that using ... So now you can see that when I run this, we get the correct sum of 15. Again, what this does is kind of break down the slice into its individual arguments and passes those to this function. Now, one thing to note here is that this ... only works when you're using a variadic parameter. So if I had, say, 5 different parameter values here, and I was trying to do this to pass each of these to each of those 5 individual parameters, that wouldn't work, okay? So if you have a variadic parameter, then you can use this ... on something like a slice, and that will then allow you to pass all of these values as those arguments into this function. All right, so that is variadic functions. Now let's have a look at something known as named return values. So what I can actually do here is I can put a set of parentheses, and I can label my return values. So when I do this and I say sint, what I'm saying is, okay, I want to have a variable called s. The type of that variable is int. So behind the scenes, what goes on is Go creates this variable for me, and then by default, that variable will be returned anytime a return statement is encountered. So what I can do is add to this variable, modify it, do whatever I want, because really what happens is we have var sint being declared in the background, meaning I can now use s inside of my function without redeclaring it. And now when I have a return statement, we'll just return whatever the named return value is, which in this case is s. So I could do return s, but I don't need to do that. And you'll see now that when I run this, the function's going to work the exact same way as before, and it returns 15. Maybe that's making a bit of sense. Hopefully it is, but you can name your return value. That then means you can omit returning the actual name of that, and you can just use that variable inside of the function. Now we can have multiple return values as well. So maybe we have s, and then we have s2 or something. And this is an int as well. And then what I'll do is say s2 plus equals 2 times value, okay? And now if we have s and s2, and we print out both of these, you'll see that when I run this, we get both of those different values, okay? So sum and sum2, we didn't have to write return s and s2 like we normally would. We just write the return statement, and as soon as that's encountered, whatever the value of these variables is will be returned. Now note that I could literally have a function that's just this. If I do that, what's going to happen is both s and s2 are just going to be 0 because they're initialized to the default value of int, which is 0. All right, so that is named return values. And I think with that said, that's pretty much going to wrap up everything I need to show you related to functions in Go. They're quite useful. There's a lot of stuff that we can do. Obviously, we just need to kind of understand the types of functions and realize that we can pass functions around our program just like we did in JavaScript. But if we're going to do that, we need to be careful of the types of functions that we're using and make sure we get that typing correct. That's really the purpose of this video, to just show you the more complicated typing and how you do that with, say, nested functions, returning functions, etc. Now, a struct is similar to a class. It's kind of the replacement of a class in a language like Go. It does work differently, but it allows us to do similar things to what we do with objects and classes in JavaScript. Now, a struct by definition is a typed collection of fields. When we create a struct, that allows us to create a new type that we can use within Go. So this is quite helpful when you want to have a type that allows you to have something like a string, an int, maybe a slice, or store information about some kind of entity or object. So you'll see what I mean here, but let's look at how we create a struct. So to create a struct, we write type, we write the name of our struct, and typically we start this with a capital letter. So something like not people, but person. And then we write struct because we're creating a struct type. Now, if you can't tell already, we say type, meaning this is going to be a new type that we can then reference in our program. Now, within here, what we do is we write out all of the different fields in our struct. So we do something like name, and then we specify the type of this field. In this case, we can have a string. Then on the next line, we can have any other fields we want. So something like age, and this can be an int, or actually more specifically, something like a uint. Okay, now we've created a person struct. How do we use this struct? Well, to use the struct, we need to initialize it. So I can say p1 colon equals to, and then person, and I put a set of curly braces like this. Now, if I do this, I've just initialized kind of an empty version of this struct. And I can go ahead and fmt.println p1. If I import the fmt package, let's go ahead and do that. And you'll see here that everything works. And what we get is a struct that contains an empty string for the name and the age 0. Now, typically when we initialize a struct, we want to actually set the values for the fields. So if that's the case, I can write them out. And I can do Tim and something like 23 here, and then go ahead and run. And you see that now we get the initialized values of Tim and 23. Now, in this case, I just wrote them in the order in which we had the fields. So I wrote the name first, and then the age, and that worked. However, if I tried to do this in the other order, perhaps something like 23, and then Tim, you'll see that doesn't work because that's not the correct order of the field names. But what we can do is actually label our different values here as we're initializing them. So I can do name colon Tim, and then age colon 23, and now it doesn't matter the order that I go in, and I can write something like age 23, name Tim, or I can just have one of these many different values. So let's clear and run, and you can see this works. We just have an empty string for the name. Okay, so that's a few different ways to initialize the struct. Now, what we can also do is access the different fields on our struct directly from the struct reference. So in this case, when I say p1 is equal to person, I'm creating a reference to this struct object, which allows me to do something like p1.name is equal to Tim. So now if I clear and run, you'll see that we get Tim and 23. And additionally, I can access the field and print that out. So something like p1.age, then that would give us 23. All right, so that is the basics on struct. I guess last thing I'll show you is if we were using our var syntax, we do something like var p1, and then the type of this variable would actually be person, okay? So we use the person type, which is the type of our struct. Now, similarly, if we wanted to pass this to a function, something like get name, and we take in a p person, and then maybe return a string, and what we could do is return p p.name, and now we've created a function that we can pass our person object to, or a person struct. So now if I wanted to call this, I would say get name with p1. I would want to store the return value, obviously, and then use that somewhere, but you get the idea, okay? So I can now pass this struct as a type into a function, or I could return a new person, right? So if I wanted to have this as the return value, then I would return a person struct. Okay, so now that we've looked at that, let's look at how we create different methods on our structs. Now, as we saw when we looked at classes and objects, and even when we just had objects in JavaScript, we can create functions that are kind of associated with that object. Now, we can do the same thing here in Go for our structs. So ideally, what I want to be able to do is something like p1 dot, and then call a function. So how do I do that? Well, first of all, I can store a function as a field value. So I can do something like f, and then I can make this a function. And I can maybe have string like that. Perfectly valid. Now what that means is that I can actually have a function f associated with my struct. So I could do something like p1.f is equal to, and then I could create a function. This will take in x string, return a string, and we could just do something simple like return x plus s, okay? And now I could call the function with p1.f and then pass this something like hello, and that would be perfectly valid. Now, the only issue with this is that this function here is going to be different for every single instance of our struct. If I create p2, then this function is not the same for p2, okay? So this is one way that we can do it. We can add the function directly as a field value to our struct. But typically what we want to do is have some function that works the same for every single instance of our struct. If that's the case, what I can do is create a method. So the way that we make a method here in Go is the following. We're going to write func. We're going to specify what type of struct this method is going to act on. So I'm going to say p person like this. This is kind of equal to this keyword. You'll see what I mean in 1 second. Then I put the name of the method, so something like get name, okay? This will return a string, and then what I can do here is return p.name and have access to the person struct that this function or method is acting on. So now this function is usable for any single instance of this person struct. And the way it works is I write my person struct, so p1, dot, and then the method name, which in this case is get name. And then if I wanted to, I could say value : equals to, then fmt dot print line will print out the value. And if we clear this and run, you will see that we get this person's name. It's because I didn't initialize the name. So let's say name, Tim, like that. And now run, and we should get Tim appearing on the screen, and we do. So this is working. Okay, so just to clarify how this works one more time, we write the function. We then write the struct we want this to act on. In this case, I want it to act on a person struct. Now I put a name p here. You can name this whatever you want. You could do self, you could do this, whatever you want to put there. And this is referring to the struct that we are acting on. So that refers to whatever we call it on. In this case, it's p1. If it was a different struct, then it would be that other struct object. What happens is we pass a copy of this struct to this parameter right here, and then we can access different properties or field values on it, okay? Then obviously this is the name of the function. We could have different parameters if we want, and then we can have return values. Okay. Now, one thing to note here is that if I try to do something like p person, and then maybe something like set name, and I take a new name, and I call this a string, and then all I do here is something like p.name is equal to new name. Well, let's print this out inside of here. So fmt.println, and then p. And now let's try to call this setter function where we try to actually modify one of the properties or fields of our struct. So how would we do that? Well, I'll simply say p1.setName, and we'll set this to Joey, and then we'll say fmt.println, and then p1. Now, the purpose of this example is essentially to see, are we going to modify the original struct here when we have this setter type method where we're saying p.name is equal to new name? Yes, that's going to change it inside of this function, but will it change it outside of the function? Well, let's have a look here and see. When we run our code, notice it actually does not. So what happens is when we call this method, we pass a copy of this person struct. So kind of a new version of the person struct. It has all of the same values, but it's a copy of the original is used inside of here. So now when I say p.name is equal to new name, well, I do end up changing the name inside of this function, But when we come outside of the function and we look at P1 after calling this method, we don't actually change any of the properties on P1. Now, there is ways to do that, and to be able to do that, we actually need to pass what's known as a reference or a pointer to the struct. If we have that, then we are able to actually modify the different field values, but I'm not going to show that to you in this video because we're going to talk about that in a future video. Regardless, for now, understand when we use these different methods, what's happening is we're getting a copy of that struct, and then we can use the different field values, but if we mutate them, that's not going to affect the original struct object. Okay. So that's the basics on structs. Now, one thing to mention here is that inside of Go, we have something known as an exported name. Now, an exported name is anything that's going to be accessible outside of this Go package. So right now, we're inside of the package main. However, it's possible that we would have other Go packages that wanted to use the code inside of here. And if that's the case, we'd only be able to use that if we had exported values or exported names. So anything that starts with a capital by default is going to be exported. So in this case, person would be an exported struct. But inside of our person, we have these different fields. Now, since these fields are lowercase, that means that we actually can't access them from outside of this package, or in our case, outside of this Go file. So here it's fine for me to access the name, to set the name, etc. But if I try to import this person struct from another package and then try to use the name field, that's not going to work. So what I need to do if I want to allow that to be usable is set this to be a capital. So I have a capital name and a capital H. I know it seems a little bit confusing, but I just want to show this to you because you may see some Go code that has capitals for things like the field names or the function or method names. And the reason for that is that they're exporting those different values. So it's kind of similar to having private or protected values in JavaScript when we're talking about a class. By default, this is going to be private, okay? But if we make it capital, then it will be public, and then kind of anyone can access it. Now, same with our method names. So I would want to make this get name or set name if I wanted these to be exported so we could use them outside of the current Go package. Won't go too much further into that, but just wanted to quickly explain to you the difference between exported names and non-exported names. Okay. Now let's have a look at how we work with embedded structs. So I'll get rid of these methods here in this example. Okay. So let's say that this person struct actually wanted to have another struct inside of it. Well, that's perfectly valid. So we can create a type here. I'm not sure what really makes sense. Let's do something like sport, okay? And this will be a struct. For the sport, we'll have a name, and we'll have a position that this person plays, okay? So name, position, that's fine. And then maybe inside of person, we want to have a slice of their favorite sports. Well, what I could do is the following. Something like sports, create a slice, and then make that a slice of this sport struct. What I've just done now is I've embedded a slice of structs or embedded structs inside of this person. Now, I also could have just done fav sport and just made that equal to a single struct. For now, let's do this, then we'll have a look at the slice later. So the point of me showing this to you is that we can do this. We can embed structs inside of other structs. But how do we access the different values of the embedded struct or initialize those values? Well, if we have our person here, first of all, let's get rid of this var syntax because we don't really need this. And we'll say p1 colon equal to person. We have our age, we have our name, and then let's have our fav sport. Now this fav sport is going to be equal to a sport struct. So we need to create a sport struct. So we'll say sport, and then we'll put our two curly braces here. Now we can either initialize the values or not. In this case, I will. And we'll say the name of the sport is soccer, and they are a defender, okay, which actually is my favorite sport. All right, now let's clear the screen and print this out, and notice that we get Tim, 23, then we have an embedded struct that has soccer and D for defense. Now, how do we access the field values on this embedded struct? Well, I would say p1.favsport dot, and then any of the values I want to access. So in this case, I want to access name. Okay, I can go ahead and have a look at the name. I also could have a look at the position if I wanted to do that. All right, now same thing if I wanted to change those values. Again, I just write p1 dot whatever the name of the embedded struct is, and then any of the values or fields that I want to use. Now, if we were to change this to be a slice, so fav sports here, how I would change this is the following. I would need to create a slice of sport, and then inside of this slice here, I would be able to pass any of the different sports that I want. And this needs to be fav sports. Then I could do fav sports at say index 0 dot position. Now, as soon as I do this, notice what's happening is that I have a slice of sport structs, And then it says that I have a redundant type literal from the array. That actually means that I can remove this when I'm creating the different structs inside of this slice. The reason for that is it's implied already that these structs are going to be of the type sport, so I don't need to explicitly write out sport before I define them. So what I've done is, again, just create a slice that has one sport struct inside of it, and then down here I'm accessing that by accessing index 0 from the slice of my fav sports. Okay, so let's run this, make sure that works, and you can see that we get defense. All right, so I think with that said, I'm going to wrap up the video here. Now, we'll have a look at structs more in future videos. You'll see some more use cases of them, but I wanted to show you how you created structs, embedded structs, access all of the different field values, and then how you can write methods for those structs. We'll look more at methods again once we get to pointers and references, but for now, you should have a solid understanding of how these work and how you can use them as different types. Now, an interface is a way for us to abstract on top of structs. What I mean by that is that we can create an interface, and this interface will define a series of methods that various structs must implement. If a struct wants to implement the interface, it must have all of the different methods that interface defines, and that then means that we're able to view that struct as the type of the interface. I know this seems very abstract. Let me show you a few examples. So I'm going to write type, and then for our interface, again, we're going to have a capital first letter. So I'm going to say shape here. And this will be an interface this time rather than a struct. Now, our interfaces aren't things that we're going to instantiate. I don't create an instance of an interface. Nothing is going to be kind of the shape interface. But my various other structs will implement this interface, allowing me to treat them as if they were a shape. So inside of my interface, what I do is I define a bunch of different methods, okay? These methods are things, again, that structs that implement the interface must implement. So I'm going to write here, get perimeter, if we can spell perimeter correctly, and I'm going to specify that this is going to return a uint value. So what I'm doing is writing out all of the different methods. I put the name of the method, I put a set of parentheses. If I had any parameters, then I would place the parameter types inside of here. I don't need to label them or give them names. And then I place any return values for my methods. If I don't have a return value, I just don't include it, and that means we're not returning anything. Okay, so we've created a very basic shape interface. Now that we have this new type, that means that we can actually use this type inside of our program. So I could do something like var s shape, okay? This is perfectly valid. I've just created a new variable that's going to store something that is of the shape type. However, we can't instantiate shape. So I can't do something like shape and then list out field values. In fact, I don't specify any fields on my interface. I'm just specifying different methods. That means that for my interface to be useful, I have to have different structs that implement the interface. So to implement the interface, the struct simply has to have the same methods that the interface defines. So what I can do is the following. I can say type triangle, and this time it's a struct. Now for my triangle, I'll have three sides. So I'll have a side A that has a uint length, side B has a uint length, and side C has a uint length. Now at this point, I've just created a triangle. This triangle does not implement the shape interface. The reason it doesn't implement the interface is because it doesn't have this getPerimeter method defined. However, if I define that method and that method has the same parameter types and return values as the shape interface, all of a sudden triangle will now be able to be viewed as a shape. Now, it doesn't matter what the struct actually does if it has other methods. So long as it has all of the methods defined in the interface, it will be treated as a shape. And that means if we had another method in here, it would need to define both of these methods, okay? Not just one of them. Don't worry, I'll continue to make this more clear. So let's write a method here. We're going to say func, and then we'll go here and say t triangle. Okay, and then this will be get perimeter. And then we're going to return the same return value here of uint, and we'll simply return the t.a plus the t.b plus the t.c, which will be the perimeter of this triangle. We just take the three side lengths and add them together. Okay, so now our triangle implements our shape interface. What that means is that I can do something like this. I can say s, or actually, let's do this, var s, which is of type shape, is equal to, and then I can actually put a triangle here instead of a shape. For my triangle, I could initialize this with side lengths, say 1, 2, 3, and I could say fmt dot print line, and then print s. So first of all, let's just run this program to prove to you that this is going to work. And you see that we get 1, 2, and 3 showing up. Now, the reason why we were able to assign a triangle to the type shape here is because triangle implements the shape interface. However, what that means is that on my shape now, because this is type shape, I can only view any of the properties of my triangle that are on the shape interface. So if I write S here, notice that it's not showing me the autocomplete for A, B, and C. And even if I went and wrote another method here, so something like get sides, and maybe what we return here is a uint slice, okay? So let's just return a new slice. So we can go int, and then go t.a, t.b, and t.c. This needs to be uint slice, sorry. You'll notice that, again, it's not giving me the autocomplete for get sides. And in fact, if I try to call get sides here, it's giving me an error. It's saying get sides is not valid. I can't call that on the shape. The reason why is because as soon as I make the type of my variable here shape, I'm only able to access whatever is on the shape interface, which actually a lot of times is what you want. By using the interface, you're allowed to hide or abstract away different functionality of a struct that you may not actually want people to use or be able to view. So I'm saying, okay, I'm going to view my triangle as a shape. I don't need to know anything about the implementation of my triangle. I just need to know that it has this getPerimeter method, and I can call that method. So I'll show you that I can use getPerimeter. So if I call s.getPerimeter and we run this here, that will work fine, and we will get our value of 6. All right, so hopefully the interface is making a tiny bit of sense, but it makes even more sense when we add multiple structs. So let me make this a bit smaller just so we can have some more space on the screen here. And let's create another struct now and just make this something like a square. So we'll say type square struct. Okay, for our square, we'll just take a width, and this width can be a uint. Now, similarly to our triangle, for our square, let's implement the shape interface. To implement that, we need to write the method for our square. So it doesn't really matter where we write it, but I'll write function, and then we'll say s square like that. And this will be getPerimeter. And then for getPerimeter, we're going to return a uint. And all we need to do for the perimeter of our square is just multiply the width by 4. So 4 times s.width. And there you go. Now our square struct implements the shape interface. What that now means is that this variable here could store either a triangle or a square. Or we could go even a bit further and we could make this a slice, for example, that stores multiple shapes. So now I'm going to say shape, and inside of here we'll have a triangle, and now we'll also have a square. And the square can have a width of, say, 10. So now, hopefully you get the idea here. What I'm doing is saying, okay, well, I want to store multiple shapes. I don't know if I'm going to have triangles, if I'm going to have squares, if I'm going to have any different type of struct. However, the only thing I care about here is that they implement this shape interface. If they implement the shape interface, then I know that on all of these different structs, regardless of how they're implemented, they have the getPerimeter method. So that's the method that I can use if I want to get, say, all of the perimeters. So maybe I have something like perimeters is equal to 0. Let's do colon equal to 0. Okay. And then I go down here and I say for, and we go underscore, comma. Actually, yeah, we'll go underscore, comma shape, colon equals to range of s. And we can actually call this shapes because that's going to be a little bit better for us. Then what I will do is say perimeters plus equals shape dot get perimeter. Now we don't need to convert that to an int. We can just write here that this will be a uint, and then we can go and say fmt dot print line, and we can print out the perimeters. Okay, so what I've done here is said, all right, I have a bunch of different shapes. What I want to do is calculate the sum of all of their perimeters. Well, the best way for me to do this is to use this shape interface. So I create a slice of all of my different shapes. Again, knowing that since they implement the shape interface, I'm able to call getPerimeter on all of them. So I don't care if I have 7 triangles, 3 squares, doesn't matter so long as they're all shapes. I then go and loop through all my shapes, and I call getPerimeter on all of these different shapes. Again, I don't need to do anything different if it's a triangle or a square because we know it implements the interface. So now if I come down here and go run demo.go, you see we get the total perimeter of 46. So this is quite useful because what I can now do with this interface is I can start using it as a type and create much more flexible functions and logic for my code. For example, I might create a function, and this function might do something like say is, and maybe even perimeter, okay? I know this doesn't make a ton of sense, but I'm just trying to come up with things that we could possibly use here. So is even perimeter, and to determine if a shape has an even perimeter, what we'll do is we'll take in a shape of type shape, and then we'll simply return a Boolean value. Here, I can just return shape.getPerimeter mod2 is equal to 0. And now, what I can do is call this function with anything that implements the shape interface. I don't need to specify that this is a triangle or that this is a square, even though both of those will work. I can instead just use the shape. And that allows me to make this much more flexible because the only thing I care about inside of this function is if it has this getPerimeter, method, right? Now, there might be another method that we want. If that's the case, then we would add that to our shape interface. However, now we have the ability to view our triangle and our square as shapes, or if we want to use something specific to the triangle or specific to the square, then we can go ahead and do that as well, right? So if I create a triangle, I say t equal to triangle, now I can just go t.a, t.b, I can use my t.getSides or getPerimeter, right? I can use whatever's specific to the triangle, and then later on I can view that as a shape and allow this to be viewed more flexibly in different functions, methods, etc. Hopefully this is making a tiny bit of sense what I'm showing to you here, but that's kind of the point of the interface. Again, allows us to view different structs as the same type, which makes it much more flexible for us when we're doing things like grabbing the perimeters of all of our different shapes. There's a million other examples of using interfaces. I don't want to get too complicated here, but a lot of times what will happen is there'll be an interface and you'll be tasked with implementing that interface. And to implement it, you just need to implement all of the methods that are defined on it. As soon as you do that, now you've made whatever you've created more flexible to be viewed as a different type and used in combination with other things that implement that interfaces. Interfaces are all over the place, and again, the main goal of them is that we abstract away the implementation of our structs, and we say, hey, I don't care if you have 10 methods, 3 methods, I don't care what different side lengths you have or properties you have. All I care is that you have this method. If you have this method, I know how to use you, and I know what I can do with this type of object. Now, error handling in Go works a lot different than it does in JavaScript or dynamically typed languages. The reason for that is in Go, most of the errors we'll have will be caught at compile time, meaning we can't even run our code unless we fix a majority of these issues. However, there is still runtime errors. Now, a runtime error will occur when something happens during the execution of our code that we didn't catch at compile time. A great example of this is something like dividing by 0. This is a runtime error, and in Go, these errors are actually referred to as panics, okay? So in JavaScript, we have an exception or an error. In Go, we have a panic. And it's important to understand the difference between compile time error and runtime error. What I'm going to be showing you here is how you catch and deal with runtime errors, not compile time errors, which you need to fix before you can even execute the code. Okay, so let's look at a panic. First of all, let's just emulate a panic. I can go fmt.println, and then I can just do something like 1 divided by 0. Now, actually, it's going to tell me here that I can't do this, so the compiler is actually catching this error for me. There is ways to kind of cause this to occur. So I guess I can do the following: func divide. Okay, we're going to take a int and b int, and then we'll return an int, and we're going to return a over b. Okay, then I should be able to call divide with 1 and 0, and now it's not going to catch that. So the compiler is smart enough to catch a line where you actually have 0 as the literal after a division sign, but it's not smart enough to catch it when you have it inside of a function. So in this case, since we're dividing a by b, we're going to get a division by 0 error. So if I run this code here, you can see that we actually get a panic, okay? So when I go through, let's just run it one more time so we get the full stack here. It says panic, runtime error, integer divide by 0. And then it tells us exactly where this occurred. You don't need to worry too much about the rest of the error message, but the point is that we saw a panic. This was the first instance of a runtime error that we've encountered. So what I want to show you here is, first of all, how we actually manually trigger a panic, as well as how we deal with a panic if it occurs. So there is a function in Go called panic. What I can do is write panic and then place an error message inside of here and say, this caused a crash or something like that, okay? So in some instances, you actually want to invoke a panic. I won't go through why you want to do that, but when I run this code here, again, I need to run it again so we can see the full stack. It says panic, this caused a crash, and it tells me where this occurred. Okay, so you have that panic function. But how do we deal with this panic function? Well, before we can look at that, we need to look at a new keyword known as defer. Now, what the defer keyword does is defer the execution of a function until the end of some specific function. I know this seems a bit weird, but what I can do is put something like defer. I put a function, and that means that this will always happen after everything that occurs inside of this function. So I'm just going to say func, and we'll just go deferred func like that. And then here we can say fmt dot println and just say defer. Now we'll go and import fmt. I guess I didn't really spell that correctly. Either way, don't worry about that. And I'm going to defer the deferred function. Okay, so now let's get rid of our panic here. And let's just go with something like fmt dot println, and then we'll say run. And then we'll go here and notice that we get run, and then we get defer. So even though the defer statement occurred before the run statement, this function is going to happen automatically at the end of our function, okay? So the reason why defer is important is because defer will run no matter what. So even if a panic occurs, the defer statement will still happen. The reason why this is important is because we can use this defer statement kind of like a .finally block that we had in JavaScript, where this allows us to clean up some type of operation even if a crash of our program occurs. So as a great example here, what we might be doing is something like opening a file. We open a file and then we attempt to write to the file. Now, while we're writing to the file, something could happen. Maybe another program's using the file. We could have an error that occurs and a panic could be caused. If that's the case, I want to make sure I close this file before I exit out of this program. So what I would do is defer an operation that closes the file, and that means even if when I'm writing to the file an error occurs, we will still end up closing the file. Whereas if I didn't defer that, and I just put it, say, at the end of my program, what's going to happen is if an error occurs, we won't reach that code because the panic happened first. So you can see here, since I have this panic, it's telling me that this line is not going to run. It's unreachable code. It's unreachable because we have this panic. So anything after the panic that's not deferred is not going to run. And even actually, if I put the defer statement after the panic here, same thing, this won't run because the panic happens before we're able to defer this execution. So you defer operations that kind of clean up your code and that you want to happen no matter what. So just to illustrate this to you, if I run my code here, you can see that we get defer. So it actually prints this out, and then we get the panic, even though I put this statement before the panic occurred. All right, so understand how defer works and understand that we can defer multiple things. So I could defer the deferred function twice, and that just means we would now defer both of those and they would run in the order in which we deferred them at the end of our code or when a panic occurs. Okay, so that is defer and that is panic. Anything after a panic statement will not run. So as soon as the panic occurs, any code that's not deferred is not going to execute. Just make sure you keep that in mind. Now let's have a look at how we can recover from a panic. So we have in Go this function called recover. Now, this function can only be used inside of a function that is deferred. I'll talk about why that's the case in 1 second, but what this will do is this will essentially catch any error that occurs and then save that error message inside of this R variable. So what I can do here is say fmt.println R. Now, as soon as the recover is kind of hit, as soon as we get inside of this statement, what this will do is allow us to not actually crash the program. Now, the rest of the function that was executing will not continue to execute. So in this case, a panic occurs, but we have this deferred function that is recovering. We're not going to execute this print line run, but we will be able to continue throughout our program without kind of crashing it. I know this is very abstract. I just need to show you an example here, and then we can explain what's going on. So I'm going to say go run demo.go, and we get defer, and then this caused a crash. But notice that we didn't see a panic that occurred in our terminal. That's because the program was able to continue to run because we handled the panic with this recover statement. So what I did is I deferred a function. Inside of this deferred function, I put this recover function. What this means now is if a panic occurs, we will go inside of the deferred function. I go inside of defer and I start executing all of my cleanup operations. Inside of here, I see a recover statement. When I see recover, that tells Go, hey, don't crash the program. I'm handling this error myself. You don't need to crash. You can let me continue to execute. So that means we now recover we get what the error is, and then we can check the error. So I can say, hey, if the error is equal to this, I want to do this. If it's equal to this, do this. Or I can alternatively check and say, did I have an error? Oh, well, I don't have an error, so I'll just continue on. For example, you'll see that if we don't panic here, right, this deferred statement will still run. But now you see that we get nil for that error, because when recover ran, there was no panic that occurred, so there was nothing we needed to recover from, and we just print nil. So what we might do inside of the defer function is something like this. If r does not equal nil, then fmt.println and just say no error. Otherwise, we may print out what that error is, okay? So we can do that inside of defer. Now when we run this, we'll see that we get nil. Actually, why are we getting nil here? It's because if it does not equal nil, we print this. Otherwise, we print this. So if it is nil, we're printing this. Okay, so actually, sorry, this is the other way around. If r is equal to nil, no error. Otherwise, print this. Just had a quick brain fart there. Apologize about that. Okay, so now when I run this, we get run and then no error. And if I add the panic back in, you see that now we get this caused a crash, and we don't print this run statement. We just go directly inside of the deferred function. Okay, so quick recap here, then I'm going to show you another way that we can handle errors. We have this panic function, and we just have things that panic in Go. A panic is a runtime error. As soon as a panic occurs, none of the code below that panic is going to execute. So it doesn't matter if I wrote panic here or if I had like a division by 0 error that occurred inside of this function. So if I had 1, 0, this is going to do the exact same thing as what we just saw before, except now the panic will happen from the division by 0. Anyways, as soon as a panic occurs, we're no longer going to execute whatever is in kind of the body of where that panic occurred, or in the stack of where that panic occurred. We're going to immediately go to any of the deferred functions. Inside of those deferred functions, we're going to do any of the operations that exist as kind of cleanup or finally type operations. We are then going to look for the presence of this recover function. If we see the recover function, that means that we won't actually crash the program. We'll go into that recover statement and we will return any error or panic message to the variable that we're writing here for recover. That then allows us as the programmer to handle this error ourselves. Now we can decide to not panic. So in this case, we're not panicking, right? And we're just dealing with the error, or we could actually raise a panic ourselves. We could say panic error occurred. So if we want to look at the specific error message and say, okay, well, we don't know how to handle this one, so we'll still panic. Or alternatively, we do know how to handle this story, so we won't panic. We'll just deal with the error and clean it up. You have the option to do that. So recover is giving you, the programmer, the flexibility to deal with the runtime error yourself rather than using Go, where the default behavior is going to be to crash, okay? That is how that works. Keep in mind, you can only use recover inside of a defer statement, and that makes sense because if I tried to write the recover function down here, even though I could do this, we're never going to reach this recover statement because as soon as the error occurs here in divide, we're not going to go into this function because it's not deferred and it comes after the runtime error. So that's why you need to put the recover statement inside of a deferred function. If you don't do that, then it's just never going to run. It's never going to execute. Okay. So that is kind of the first way to handle errors. Now, as you can see, this is a little bit clunky, and actually in Go, we typically don't have runtime errors, and we're not dealing with these very frequently. What we can actually do instead is we can create or return an error from our function. So rather than panicking, we can just tell whoever called this function, hey, you called this incorrectly, here's the error related to how you called this function. And we've actually already seen this pattern in Go where we called a function and one of the return values from that function was an error. And it was telling us if an error occurred or if it didn't. So what I could do is I could modify my divide function here and do something like this. I can say if b is equal to 0, we don't need to put this in parentheses, sorry. Then what we'll do is return 0 and we can return an error. So what I'm going to do here is put a comma and put error. I'm going to put this in a set of parentheses. That's how you have to return multiple values. And now I'm going to return an error alongside this 0 value. So to do that, I'm going to import another package up here. So I'm going to say import fmt. Then I'm going to go down and I'm going to import this errors package. Now errors allows me to create a new error. So I can say errors dot new like this. And then I can say division by 0. So rather than panicking and allowing me to actually perform this division by 0, which will cause a panic, I'm going to return an error telling me, hey, you can't do this because if you were to do that, that would cause a division by 0. Then here If this isn't the case, so if we don't have division by 0, I'll return A over B, which will work, and then I will return nil, indicating that we don't have an error. Now, if we have a look at the error type here, this is actually an interface type, and we can see that all this is saying is that whatever we have as an error must have this error method on it that returns a string. Now, using this errors package, which is built into Go, we can use this new function, and this returns, as you can see here, an error, which essentially means it's giving us a struct that has a method on it that is this error method. So then we can call that to get what the error message is. So now if I want to use this divide function, what I say is the following. I say result, comma, error, colon equal to, and then divide, and then something like 1, comma 0. Now I can say fmt dot print line result and error. Then I can clear this, and I can go ahead and run, and I get 0 and then division by 0 because an error occurred. So rather than panicking and going into that defer and recover kind of block that we looked at, instead we're using this new pattern where we're actually returning an error object, and then we can handle that object how we please. So now if I don't have an error, so I just have 1, 1, you'll see here that we'll get 1 and then we'll get nil. So what I would typically do is I would now go and handle this error myself. So I would say if error does not equal nil, then I could do something like fmt.println and say error occurred, and maybe I change the value of result or something. I don't know. I can do whatever I want here. Otherwise, I just go ahead and say fmt.println, and I print my result. So now I'm handling this by just using a simple if-else statement and checking if we did have an error. So in this case, we get 1, but if we make this 0, then you'll see that we get that an error occurred. Okay, so with that said, I think I'm going to wrap up the video here. I just wanted to show you how we can handle errors in Go, the difference between defer, recover, panics, all of that, and then what's going to be the recommended way to deal with errors, which is returning this error object from your functions. Doing this avoids the panics, it makes your code a little bit cleaner, and this is kind of the standard pattern that we use in Go. So in case you see this, now you kind of know how it works. We're returning a separate object, again, just indicating if an error occurred or if it didn't, and then we can handle that error however we want to inside of wherever we called that function. Now, generics can be a complicated topic. There's actually a lot of details and nuances related to them. I'm not going to go through everything because this isn't meant to be an in-depth Go course, but I will show you the basics so that if you see them, you know what they are and you have some sense of how to use them. So what is a generic? Well, a generic is a way that we can have flexible types in a statically typed language. Now, it's best for me to show you an example of where we might want to use generics, and then you can see kind of what the purpose of them is. So if I make a function here, something simple like add, right? For this add function, it's possible we're going to have two arguments, so x and y, and then we'll return an int. We can just return x plus y. Okay, simple function. This works fine. However, as you'll see here, this add function only works for the int type. Meanwhile, we know that add can work for a uint type or for a float type. Really, so long as all of the values here passed to the function are the same type, I mean, like an int, a float, a uint, etc., we're able to add them. So right now, without knowing about generics, what I would need to do to accommodate an add function that worked with other types is just make another version of add. And for this version of add, I would need to change the name as well as the types. I'd have to have add2. Now this isn't ideal, and that means that now all of a sudden I have all these different add functions appearing in my program just to accommodate all these different types when really everything is the exact same inside of my function. So how do I fix this? Well, to fix this, I use a generic. Now the way we define a generic is the following. We put a set of square brackets here after we have the name of our function, and inside of here we define our generic type. Now we start by creating a name for the type. Typically this is going to be a single letter, and it's going to start with a capital. The most common is to use T, and then after this you specify kind of the constraint for this type. So in my case, I'm going to put int or union float, and in this case it has to be float 64. Now what I've just done here is I've said, okay, for this add function, I want to have a generic type T. Now this means that I'm going to replace all of my parameters here with T. Now this T type, based on the way I've written it here, can be either an int type or a float type. So this operator right here, which is the pipe operator, is known as the union, and that means that we are combining int and float64 together and essentially saying, hey, t can be any of int or float, all right? So really what we're kind of doing here is placing an interface that this type t has to adhere to. In this case, I'm saying it either needs to be an int or it needs to be a float. Okay, then for the types now, for my parameters, I've placed t. And notice, since I have t 3 times, what that means is that whether t is an int or a float, all 3 of the values that are passed to this function must be of type t, meaning they must be the same type. So I can't pass an int here and a float here. I need to pass either both ints or both floats. So just to illustrate the usage to here, I'm going to say value colon equal to, and then we'll say add, and we'll call add with 2 and 3. And then we can say fmt dot print line, and we can print our value. But we can also call value, or not value, sorry, add with a uint value. So we can say uint2 and uint of something like 7. And actually, sorry, uint doesn't work because I don't have uint here. But now if I add uint, you can see that this is fine. Then I could continue this, and I can call this with float values. So I can do 34.5 and 54.3. And now, as long as I name this something different and I print these out, so value 2 and value 3, you'll see here that when I run this code, so go run demo.go, that I get my results and there's no errors. Okay, so that is what happens when we add this generic type. I do the name of my type, which is t. I specify the interface this type needs to adhere to, or the constraint for this type. In this case, it needs to be an int, a float, or a uint, and then I can use this generic type inside of my function parameters for my return value and inside of the function. So I could also do something like var sum of type t is equal to x plus y, and then I could just return sum, and this is completely valid. And now again, t will be equal to whatever the generic type is for this function. So this now allows me to handle different types inside of here generically. So that's what a generic is. Now we can use generics in a lot of other places, and we can get pretty complicated with them. But I'll show you how we can use multiple generic variables now when we're doing something like viewing a map, okay? So let's get rid of this example, and let's make a new function. Let's call this get values. And what we'll do is we'll have a generic value k here, which implements the comparable interface, and a value v, which is any type at all. So if you just want to be any type, you can just write any. Okay, then I'm going to put my set of parentheses here, and I'm going to say that I'm accepting a map. So this is going to be mp map. The key of the map is going to be k, and the value is going to be v. And then what I'm going to return is a slice of all of the different values. Now inside of the function, what I'll do is I'll say values colon equal to, and then I'm going to make a new slice. So I'm going to say slice of v like that. Now I'm going to loop through my map. So I'm going to say for underscore comma value colon equal to the range of mp. And then I'm going to say values is equal to append, and then this is values and value. Then I'm going to return my values. Now what I've done is I've written a generic getValues function, which can iterate through any map and return to me all of the values inside of that map. So let's create a map here. We're going to say mp colon equal to, and then this will be a map. For the key, it can be a string. For the value, it can be an int. And we'll say that we have maybe a 100, b 5, c 10, d 5, something like that, okay? Then I'm going to call getValues. So I'm going to say values colon equal to getValues, and then we're going to pass our map here. And then we are going to print this. So fmt dot print line like that, and we'll print out our value, sorry, and just make sure this works before I go in and explain this more in depth. Okay, so you see that this worked, and this would work with any type of map that we have. Now, the reason why up here we had k being of type comparable is because for all of the keys in our map, they already have to implement a comparable interface. So you'll see if I actually change this to the type any here, right now we get an error. It says invalid map key type missing the comparable constraint. So Go has a constraint on all of the types for its keys in a map such that they implement the comparable interface, which is why I need to write this. And you can see that this is built into Go, right? We didn't have to write this interface ourselves. So hopefully that makes a tiny bit of sense why we need that, but this is a generic function that allows us to iterate over a map. Now I want to show you a few more use cases of generics here, just so we get a better sense of how they work. I also want to show you kind of a common practice when we use them. So for example, in the last function we had, let's go back to that actually where we had add. Okay, let me just get that popping up one more time here. You saw that we kind of wrote int, float, and uint here. Now, that's fine. However, this is not really the best way to be kind of using these types. In fact, what we should really do instead of writing all these unions inside of this kind of generic definition is go up here and create an interface. We're going to say type number interface. And then inside of here, I'm just going to write int union float union uint, and then I'm going to use the number interface as my generic type. So now this is just a little bit cleaner. It's easier to read, and I can actually specify, hey, I'm accepting any type of number. And in this case, we can kind of create this interface that contains int, float, or uint. I know it seems a little bit weird. You kind of have to memorize the syntax, but we can do this. We've created this interface that kind of encapsulates these three different types, and now I'm able to use anything that is a number as my generic type. Now, as well as using generics for functions here, we can actually use them for structs and for different types. Now, this is going to seem a little bit strange. Again, just bear with me here as we go through this. So what I can do is I can create a custom type here. I can do something like type generic slice. Now, what I'm going to do is put my generic syntax. I'm going to put t, I'm going to specify any, and I'm actually just going to put this kind of slice syntax and then t. Now, what I'm doing here is I'm defining a type that is neither a struct nor an interface, but is my own custom type here in Go. Now, all this says is that I'm going to have some type of generic slice kind of object here, and it's going to be a slice of type t. So I'm specifying what the type actually is, and this is kind of the name of my type. I'll show you another example in 1 second. But to create this slice, I can do the following. I can do g : generic slice, and then I could specify the type. So I can do something like int, and then I can write here, say 1, 2, 3. Okay, so now I've specified a generic type of type 1, 2, 3. So now I've created an instance of my generic type, which is really just a slice of a specific type. So this is another way that I could go about making this slice. Now, does it make any sense for me to do this? No, because I already have the kind of concept of generics when I build a slice by default. But this is just one thing that we could do. And then I could actually go and I could write a method on this generic slice or on this type. So I could say something like func g of type generic slice t, and then I can say something, say like print, okay? And then I could go in here, I could say for underscore comma value : to the range of g. And then I can say fmt dot print line, and I can print the value. And now I can say g dot print, and if I come here and clear the screen, well, actually we don't need to clear, we can just run this here, you'll see that we get all of the different values from our slice. I know, seems a bit strange how I've defined this here, but this is getting into some more advanced syntax in Go and creating these generic types. Now, if we wanted to make another kind of type here that is generic, we could do this. So we could say type, and what do we want to do here? We can actually make a generic struct, okay, of type t. T can be anything. This will be a struct, and then we can go in here and we can start specifying things of type t. So I could do something like name type t, or we'll just do something like values of type t. Now I want to create a generic struct. So what I can do is say st for struct : to generic struct. I need to specify my type, so I can do something like string. And now when I create my struct, I can say values, and then this will be equal to a string. Okay, then I can say fmt dot print line and print st. I'm just trying to show you here that we can use generics in more places. So in this case, I'm using it for a struct. I'm taking in some generic type, and then I can use that type however I see fit throughout the struct. I also could take in multiple types. So I could take in t and k. And now I need to pass another value, right? Maybe like an int here. and then I could use K here. So maybe now I have a map type that has T and K. Now that's not going to work because T doesn't implement the comparable interface, but you get the idea here. I can have all these different generic types. I can mix and match, and this gives me some more flexibility that we had in languages like JavaScript that we don't have in Go. Well, now we do have them in Go, but we just need to use generic types to be able to implement those flexible kind of operations. All right, so with that said, I'm going to start wrapping up the video here. Now, I know this isn't crystal clear, and you probably still have a few questions about generics. The point here wasn't to confuse you, but just to introduce you to this new topic and make you a little bit familiar with how this works so that if you see it, you're not completely lost. Feel free to look into this more. I'm not going to spend more time focusing on generics right now. Again, I just kind of wanted to show it to you, introduce it to you, and give you a concept of how you would kind of create some more flexible behavior and functions inside of a statically typed language like Go. Now, a lot of other statically typed languages have generics as well, so now you should kind of have this under your belt and understand this core concept here of this general type that you're passing into some kind of function, struct, etc. Now, pointers and references are more powerful language features in Go that we didn't have access to in something like JavaScript. This actually allows us to view both the memory address location of where something exists, as well as to modify what's held at that location. Now, you'll see what I mean as we go through this video, but before I can even explain pointers and references, I just want to give you a good basis and understanding for how RAM works in a language like Go. So on the right-hand side of my screen, we have this RAM diagram. Now, this is random access memory, and this is the location where your program is going to be stored on your computer. We've talked about this a little bit, but this is a temporary storage location where you have addresses associated with values or data. So on the left-hand side here, I have some different addresses. Now, these are binary addresses. Typically in RAM, we're going to have hexadecimal addresses. We don't have to worry too much about that, and they're not going to look exactly like what I have here, but for now, this is a fine representation. The idea is we have some kind of storage slot where we have an address, and that address is associated with some data or some value. So to give you a quick example here, if I go ahead and create some variable like x, so I say x : = 0. What happens is my computer in the background, or Go in the background, is going to allocate one of the addresses in my computer's memory to store this variable x. So it's pretty much going to say, hey, x is going to this address right here, and then I'm going to put 0 in the value column because that's what's associated with the address. Then when I go and reference x later in the program, it says, oh, where's the address for x? Well, this is the address for x. Okay, let me grab the value at that address. Now, when I make a variable y here, pretty much the exact same thing happens. So some people may think, oh, well, if y is storing the same thing as x, then maybe both y and x are going to be associated with this address. Now, you could do that, but that's not the case here. What will happen when I make this new variable y is I will allocate a new address, and I will put a new 0 inside of that address. Meaning, if I were to change y, so I say y is now equal to 1, well, that's only going to affect the value at this address, not the value at this address, meaning x will stay unchanged. Okay, fairly straightforward. Hopefully that makes sense. Now, let's have a look at what happens when we change the example slightly and we say something like y is equal to x. So when I do this, what happens is that our memory address diagram actually stays the exact same. When I assign the variable x to the variable y, what happens is we take whatever value is stored inside of the address at memory location x here, and we copy it inside of the location for y. Okay, so we just make a direct copy down here. So whatever is the value, we copy that into a new address, right, or a new location in RAM, and then we label this y. So yes, x and y are now the same value, but if I change x or I change y, that doesn't affect either x or y. Hopefully that makes a bit of sense, but I'm just trying to illustrate to you kind of a few things that occur here in our computer's memory. Now let's go back to the example here where we actually have nothing in RAM. And let's look at what happens now if we create something like a slice. So let's say I have s, and this is equal to a new integer slice. So we can say int like that. And actually, sorry, I realize I'm writing this the wrong way. We'll do our square brackets first, int, and then we make a slice like 1, 2, and 3. Okay, so now we have our slice. What happens when we create the slice? Well, when we make the slice, things are a little bit different. First, we create an array. This underlying array goes in some location. So in this case, we're going to have the array 1, 2, and 3 that goes in this address location. Then what happens is we're going to have another address in RAM that's going to be labeled as S, and this is going to store a length, a capacity, and a pointer to the location where this array exists. So our slice is really stored at 0, 1, 0, and it points to 0, 0, 1, which is the location where our array exists. Now that's why when I do something like S0 is equal to, say, 100, it actually modifies the underlying array because we have a pointer to this location. So what happens is I go to this location, I find this array, and then I modify it. Now that's the same reason why if I do the following, something like, let's say, t is equal to, so let's do colon equal to s, that if we modify t, it affects s, and if we modify s, it affects t. So if I create this variable t, what actually happens is the following. I now, again, have a new memory address location, this time labeled t, and I copy whatever was in the memory address location of s. So I take my length, my capacity, and my pointer, which points to 0, 0, 1. So since these both have the same pointer, like this pointer points to the same location, any change that's made to this underlying array affects both of them because they're storing the same pointer to the same underlying array. Hopefully this is making a little bit of sense here, but that's what happens. Whenever you say something like t is equal to another variable, or you create some variable and assign it to some other variable, you make a copy of whatever is stored in the memory address location for that variable. So when we're just using simple values, well, we copy the value. But in this case, we have a reference or a pointer to an underlying array, so we copy that reference, not the underlying value, which is 1, 2, 3. Okay, now let's have a look at what happens when we use slices or values inside of a function call. Then we'll talk about pointers and references, and hopefully this will start to kind of clear itself up even more. All right, so I've just come up with another example here to show you what happens when we pass values to functions. It's going to be a very similar thing, but it's important to understand this. So we have this change function. All this function does is accept some integer. In this case, we've called it x, and then it says x is equal to 7. Then we've declared a variable a outside of the function and passed that to the change function. So let's look at our memory when we have this type of code. So first of all, we have a. When we have a, what happens here is we allocate some space for a in our computer's memory. So we say a is going to be this location right here, and then we store the value 10. Now I come and I call this change function. Now when I call this change function, what I see is that we have this parameter x. Now x is a variable. That variable is within the scope of this function, but we still need to store that variable. So what we do is we allocate more space in our computer's memory, right? And we copy whatever was the value that we passed for the parameter corresponding with the parameter x. So in this case, we passed a. So we look at a and we say, what's the value of a? Well, it's 10, so I simply copy 10 here into this location. And now when I use x here and I say x equals 7, I go to the memory address location for x and I change this to 7. What that means is at the end of my program right here, after calling change, a has not been modified. It's still equal to 10. The reason that's the case is because when we passed a to x, we simply made a copy of a, and then when we change that, we're only affecting the copy. We're not affecting the underlying memory address location. So now let me quickly change the example, and we'll see what happens when we use something like a slice. All right, so I've just changed up the example now, so that what we're doing is we have this function called change that accepts a slice of integers. Then we modify the first value of that slice to be equal to 100. I've then defined a slice down here and passed it to this change function. So now, again, let's look at our memory and see what happens when we do this. So we have v. When we create v, the first thing we need to do is make the underlying array. So we create an array here, like 1, 2, and 3, and then we store that in some random memory address location. Doesn't really matter where it is. Then we create v. Now v goes to this memory address location. We have a length, we have a capacity, and we have a pointer that points here to the location for where the array exists. Perfect. Now what happens when we pass v to the change function? Well, just like before, s is a variable. We need to store that variable. So we create a new location in our computer's memory, or we allocate this space, and we copy whatever was inside of v, the variable we passed as the parameter, to s. So what I do now is I write len capacity, and then again, my pointer goes to this underlying array. So now, when I say s at index 0 is equal to 100, I access the underlying array, and I modify the value right here. I know it's a bit difficult to see, to be equal to 100. I can't really change it because it's going to mess everything up how I'm drawing it here, but you get the point. What's going to happen is we're going to have a new array here that's going to have 100, 2, and then 3 inside of it. I'm kind of running out of space there to be able to do that. Anyways, you get the point. So the reason why in this case we were able to actually modify the v slice here is because we copied the slice. And when we copied the slice, we had a pointer to the underlying array. So when we make a change to that slice, it affects anything pointing to that underlying array. So both v and s get affected because they both point to the same memory address location. Now, the reason for me showing this to you is so that now I can explain to you something known as pointers, which we can actually use on our own without creating something like slices. So let me go back to a fresh screen here, and now let's talk about pointers. So what I'm going to do here is create a variable x, and I'm going to say this is equal to 0. Same thing happens as always. We say x has the value 0. Now, though, I'm going to say y is equal to the pointer of x. Now, the actual symbol for a pointer is an ampersand, but since I can't write that symbol, what I'm going to do is just put an underscore here that indicates that we're talking about the pointer of a specific variable. So whenever you see an underscore from now on in this kind of illustration, imagine this is the pointer, okay? So I'm saying I want the pointer to x. Now, what is the pointer? Well, really the pointer is the location where x is stored. So what I'm going to do now is I'm going to create a variable y. It's going to be its own memory address location. But what I'm going to store is not a copy of x, but where x is stored. Now, x is stored at 0, 0, 1. So I'm really writing the memory address location of x in the memory address of y. So now y knows where x is stored because I have a pointer to x. That now means from y, I can modify x. The way I can do that is by saying asterisk y is equal to something like 100. Now, when I do this, what I'm doing is I'm using something known as the dereference operator. Y is equal to a pointer, which means that y is storing some memory address location. If I want to go to the memory address location that y is storing and perform some action, I dereference y, okay? So I'm saying asterisk y, which stands for dereference, which essentially means, hey, look at what y is storing, and then go to where y is storing, which is x, okay? So since we are storing x, we go to x, and then we change x to be 100. So this line here actually goes to the variable x and changes the value to be equal to 100, which now means if I look at the value x, we see that this is equal to 100. So we had a pointer to x we stored in y. We dereferenced the pointer, which allowed us to access the value that was stored inside of x because we knew the memory address location, and we could then change what was being stored inside of there. So this is how we use pointers to access different values. Now, a pointer, again, is really the memory address location to where some object exists. If we have that, we can then go to that location and make any change that we want. And we can get even more and more complicated here and have things like pointers to pointers. So before I kind of end this example here, imagine that now we go even one step further, and we have a variable z. Now, z is going to store the pointer to y. Well, y is already a pointer to x, but that's fine. We can do this. So I'm going to have variable z now, and z is going to store the pointer to y, which means it's going to store 0, 1, 0. So now, if I were to dereference, and that's a horrible star, but you get my point, if I were to dereference z, that would actually bring me to y, which means I could dereference z 2 times because dereferencing the first time brings me to y, dereferencing the second time brings me to x. I'm not sure if you see what's going on here, but we have 0, 1, 0, or z, pointing to y. We then have y pointing to x. So we have this kind of chain of pointers here, where as we go up the chain, we can access the underlying value here, which is x. Hopefully this makes a tiny bit of sense, but that's kind of what I wanted to show you in this illustration here when we're talking about RAM and seeing how values get copied and how we have pointers, otherwise known as a reference, to another value. Now, I might have confused you a little bit, but whenever I say pointer, I'm pretty much talking about a reference. Reference and pointer are kind of going to be used synonymously here inside of Go. That pretty much means that I'm just storing where this thing exists, okay? That's what a pointer or reference really means. Anyways, with that said, that's going to wrap up the conceptual part. Now let's look at how we actually implement this in Go in code. All right, so I'm on to the second part of the video now, where I'm actually going to demonstrate to you pointers and references in Go. So let's make a variable, x equal to 0, and let's make y equal to the pointer of x. Now, the ampersand here is how you access a pointer or get the pointer, otherwise known as the memory address location, to an object. Now, some people may also refer to this as the reference to something. Doesn't really matter. It's either the pointer or the reference, whatever you want to call it. Anyways, what I'm going to do here is just print this out to show you what they are. So if we look at x and y, we'll see that x is equal to 0, and y is equal to the memory address location of x. Now, this location can change, so don't concern yourself with the actual value here, but the point is that we're storing a hexadecimal location, which is telling us where the value x is stored. And remember, I told you that we can dereference this using the asterisk operator. So if I use asterisk y here, now what happens is I say, okay, go to whatever memory address location I'm storing, which in this case is the address for x, and then find whatever value is there. In this case, the value is 0, so we get 0, right? Obviously, if we change this to 2, then you can see that we get 2. Great. Now look at what happens when I start using my pointer to y to modify x. So I can actually say y, or asterisk y, sorry, is equal to something like 100. Now when I do this, and I print out my values here, you see that I get 100 and 100. What I've just done is I've modified x through the pointer to x. So y stored the pointer to x. I then dereference the pointer, which means go to the location where I'm storing this pointer. I've then dereferenced this pointer, which means go to the location that this pointer points to, and change the value to be 100. And through that, I've been able to affect what the value of x is. So that's the most basic usage here of pointers. Now, let's see what happens when we use pointers in things like functions, which is where they get quite useful. So let's go here and make a function, and let's say function change, and let's accept just a regular parameter. So let's say x int like that, and we don't need to return anything. We can just say x is equal to 100, okay? Very straightforward. Now, we're going to say a colon equal to 10, and then change a, and then fmt dot println a. We already looked at this example, but let's just repeat it one more time, and you see that we get 10, even though we set x equal to 100. However, we can actually change this now by accepting a pointer to x. Now, when I put in asterisks before a type, what that actually refers to is a pointer to this type. I know it seems a little bit weird, but the way that the pointer types work is that you're pointing to some underlying value. So if I put asterisk int, this means a pointer to an int value. So now what I need to pass to change is the pointer to a, which is ampersand a, okay? Then what I can do inside of change is I can say asterisk x is equal to 100. I can dereference my pointer, find the location where it's being stored, and then change whatever is inside of that location, which now means when I rerun this using the pointer, I do actually change x outside of the function. So to recap here, what's going on now that I'm using the pointer is I'm passing the reference or the pointer to a. So inside of my function here, I dereference that pointer. I'm just using x, but it doesn't really matter the name here, right? I go to the location where that pointer was pointing to, and I change the value to be 100. So now when I come here, a is now equal to 100 because I've changed what is being stored in the memory address location for a. So that's why pointers are quite useful, because this now allows you to actually pass in locations or pointers, and then you can affect variables outside of the actual function that the variable exists in, right? So in this case, we're affecting a outside of the main function. Now, we, of course, can use pointers in much more complicated scenarios, which I'm going to show you in a few minutes, but this also leads me to how we kind of modify structs using pointers. So let's have a quick example here. But let's say we have a struct, right? So we say type something like book struct, and then we say that this maybe has an int ID, and we got to do this the other way around, ID int, and title, which is a string. Now, remember I showed you that if we create a setter method for this, we're not actually able to modify the different properties. Well, we can actually change this now using a pointer. So I can say function, and we will do b book. This time, though, I'm going to take asterisk book, okay? So a pointer to a book struct. I'm then going to write set title, like that. We're going to take in a title, which is of type string, and we're just going to say b dot title is equal to title, like that. Now let's create a book struct. So we're going to say b colon equals to book. We're going to give this an ID of 10, a title of old, okay? And then we're going to say b dot set title, and we're going to pass to this new, and then we're going to say fmt dot print line, and then print out b. There's a few things that I need to go through here, but I just want to first start by showing you that this does indeed work, and you can see that now we are able to modify the different fields on our struct by using a pointer to this struct. Now you may be asking yourself, well, how did this just work? In previous examples, we've been able to just do this, right? B and not have a pointer to the book. And you see that if we have this example right here where we don't use the pointer, now all of a sudden this doesn't change, or this doesn't get modified. Well, when I add the pointer here, what happens by default is when I call this set title method, Go is going to implicitly pass the pointer to this book object. So I could actually go and write inside of a set of parentheses here, reference b, right? So the pointer to b dot set title. Now, if I do that, that's more explicit and verbose, and that's saying, okay, I want to pass the reference to this book object, to this method, right, which is what I'm doing, and then I'm going to call set title on it. Now, obviously, that's going to work, so if I run this, you can see that we get new. However, we don't have to do that in Go, because Go is smart enough to determine whether or not we want to pass the reference or the value based on what's specified here inside of the method. So in this case, since we have a pointer to book, Go will automatically take the reference of b and pass that to the method. We don't need to explicitly state that. And actually, same thing here when we're talking about the title. Go will automatically dereference our structs for us so that we don't have to explicitly write this, which is asterisk b dot title. Okay? So this is correct. Again, if we do this, this is kind of what you might expect, because if this is a reference, well, if I want to access the actual struct object, I would need to first dereference it, and then I can access the different fields on it. But Go, again, is smart enough to be able to do that directly for us. So when I write this and access the field name, it goes, oh, you're trying to access and change the field. Okay, I'll automatically dereference the book struct for you. Now, this only works on structs. It doesn't do it for other types, but I just wanted to show you with structs, Go will automatically dereference or pass the reference for you based on how you're using it, because it's such a common feature. Now, the reason why I've kind of been putting these inside of parentheses here, right? I've been doing like parenthesized asterisk b, is because if I try to do asterisk b dot title here, you'll see I actually get an error. It says invalid operation cannot indirect b dot title variable of type string. The reason I'm getting this is because what Go will do is it will read this dot notation before it will read this dereference operator. So what it's saying is b.title, and then it's attempting to dereference b.title, which is not a reference, hence why we get this error. So what I need to do is put this in parentheses. So I'm saying, hey, no, I want to dereference book, and then I want to access the title. Whereas, again, if you have it like this, it's going to read this whole thing first and then try to dereference that, which isn't what you want. Okay, so that's a quick example with structs. Hopefully that's clear, but essentially you use this pointer kind of syntax here, this pointer type inside of your method when you want to be actually modifying the different fields on your struct. Now let's have a look at a few more examples and some more kind of advanced pointer types here, just so we get a sense of how this works. So one of the best examples I like to use is pointers to pointers. So let's have x equal to 0. Let's have y equal to the pointer of x, and let's have z equal to the pointer of y. Now let's just print these out first of all. So fmt.println x, y, z, and see what these values are. Okay, so let's clear and run, and you see that we get 0, we get a memory address location, and then we get a different memory address location. All right, so both y and z are pointer values. Now let's dereference y, and let's dereference z, and let's see what we get for those. Okay, so if I run this here, you see we get 0, 0, and then we get another memory address location. Well, the reason why we're getting 0 for y is because when we dereference y, that gives us whatever value is stored in x. However, when I dereference Z, I'm getting the value that is stored in Y. And the value stored in Y is the memory address location 2x. What that actually means is that I can dereference this multiple times because Z is storing a pointer to a pointer, right? It's the pointer of a value that is storing a pointer. So I can go here and write a double asterisk and run this, and now I get 0, 0, 0. So from Z, if I wanted to access the value of X, I needed to dereference this 2 times, whereas from Y, I only needed to dereference it 1 time. So to continue this example here, I can actually show you that if I look at the type of something like Z, so I go printf and look at %t of Z here, let's clear and run, and notice that I get asterisk, asterisk, int. That's because I have a pointer to a pointer of int. So I guess I should touch on this a little bit more. When we're writing functions or when we're writing kind of structs or methods, we can accept pointers by using the correct pointer type. Now, I kind of already showed this to you, but it gets a little bit confusing with more complicated types. So let's say I have a function, and we'll just call this something like test, right? Now, inside of here, what I can do is I can have something like slice, or I can say pointer slice like that, and I can have a pointer to a slice that contains maybe int objects, and actually this could contain pointers to ints. So now if I'm looking at this type right here, what this type is a pointer to a slice that contains pointers to int objects. So if I wanted to actually create that type, which I can do, I would have to do something like the following. I would say, let's go values :equal to, and then I'm going to create the ampersand or the reference to a slice of int pointers. And then inside of here, I'm going to write a bunch of ints. So 1, 2, 3, 4. However, you'll see here that this doesn't work. It says that these aren't valid. They're not valid because 1 is not a pointer to an int. So what I would actually have to do is put the reference to these different values, but you'll see here that that doesn't work as well because I can't reference a literal. So instead, what I would do is create some variables, something like a : equals 1, b : equals 2, and then I would come here and do the reference to a and the reference to b, and now I have a valid type for values that is a pointer to a slice that contains pointers to ints, okay? And then if I was going to access the different values inside of here, I would need to do the following. I would need to say my values is equal to, and then I would dereference the pointer slice, and then I could say loop through the pointer slice. So I could say for underscore comma value :equal to range of values, and then I would have to actually say asterisk value if I wanted to see what that value is. Otherwise, if I didn't use the dereference here, what would happen is I would get access to a pointer, right? So this is a pointer to an int, which would give me the memory address location. Now, I might want to use that, I might not. I'm just trying to show you a few more advanced use cases here of pointers and these different types. Hopefully this is making a bit of sense, but whenever you see the asterisk as a type, that's referring to the fact that this is a pointer. If you see the asterisk before a variable, so something like asterisk b, you're dereferencing, okay? And if you see the ampersand before a value, you're getting the reference to a value, which is really giving you the pointer, okay? It's going to give you a type, which is asterisk, and then whatever the type of b is. All right, so with that said, I think that's all I have for you in this video. Now, I know this is a confusing topic. A lot of people do struggle with this. I hope that this was clear and that you're able to understand at least the core concept of what a pointer is, kind of how the memory works, and how you dereference and then access the pointer or the reference to a variable. If you understand that, you're well on your way to being able to write some solid code in Go. Keep in mind, all of these features I'm showing you are more advanced, and it's something that you might need to practice with a little bit, kind of go into your code editor and just mess around with to really make sure you understand it. So if you need to do that, please go ahead and do so, and try to mess with some more advanced types like the ones I'm showing you here, where you have, a pointer to a slice that's storing pointers. Maybe you have a nested slice that's storing pointers to other nested slices. You can do all kinds of crazy stuff using this new pointer syntax and type that I'm showing you. All right, so let's begin by just talking a bit about the CPU of our computer and how the operating system schedules different tasks. Now, I just want to put a disclaimer here that I'm not going to give you 100% accurate information when it comes to the hardware level implementation and all the small details that are going on. I'm just giving you a very high level kind of explanation that will allow you to think about this in the correct mindset such that you kind of know what's going on when you're creating something like a thread, which we're going to do in the next video. So please don't take this as absolutely 100% correct when it comes to what's going on at a hardware level. There is a few differences, and there's a lot of differences based on operating systems, types of architecture, CPUs, etc. Just want to make clear that this is not a computer engineering class. This is simply meant to give you a bit of insight into what's going on your computer on a lower level. Okay, so let's begin by just drawing out a CPU. So on all of our computers, we have a CPU. Now this CPU has a variety of different cores. Most of our modern CPUs in 2023 are going to have 4 cores. However, we could have 2 cores, 1 core, 8 cores, any number that's a multiple of 2. So usually 2, 4, 6, sometimes we have 8, sometimes we have 16, 32. We can have all different numbers of cores. Now, each one of these cores here, which is kind of what I've drawn, is a physical device, something that you can actually see on the CPU. So if you were to take off the heatsink of the CPU, you'd actually be able to count and view all of the different cores. Now, these cores all are capable of executing different operations. Really, you can think of each core on the CPU as its own mini CPU that makes up the entire CPU as a whole. Now, the reason it's important to understand that is because the number of cores will dictate the number of operations that your CPU is capable of handling in parallel. Now, parallel means that you're doing something at the exact same time. So really, at the exact same unit of time, you can have 4 different operations if you have 4 cores happening, right? If you had 8 cores, you could have 8 operations. So obviously, the number of cores is important, and the more cores, typically the faster the CPU is, because the more things it's capable of actually doing, right? The more tasks it can perform. Now, on the core, we also have a speed, right? That speed is typically measured in gigahertz. I'm not sure about the capitalization for this, but you know what I mean. We'd see something like 4.4 gigahertz, right? Now, that's actually telling you the clock speed of the CPU. The way that a CPU handles operations is it does something called cycles. That speed that you see is essentially the cycle speed of the CPU, and it tells you the relative number of operations or cycles that can be performed on that CPU within any given span of time. So I believe it's within 1 second. Regardless, the higher the speed, the faster the individual core. But it's important to note that just because you see a very high speed doesn't mean that this CPU is necessarily faster than another CPU. You have to take into a lot of other factors like the threads, the core count, the cache. There's a bunch of different things. So just looking at, say, the cores and the clock speed of a CPU is not going to tell you everything that you need to know. We don't need to get into that too much, but I just want to be clear that if you had a single core CPU and this had a speed of like 7 gigahertz, that's not necessarily faster than a 4-core CPU that has a speed of like 2.2 gigahertz, right? Since this has 4 cores, it can do 4 things at the same time, so these CPUs would both be good at different types of tasks. Your single-core CPU would be very good at single-threaded tasks, whereas this multi-core CPU would be very good at multi-threaded tasks like video editing, rendering, etc. Anyways, that's enough information on that. Okay, so we have these 4 different cores. Now, how do our programs actually get executed on this CPU? Well, every single program that we write is bundled into something called a process. Now, this process includes things like memory allocation, which is a certain set of addresses in our computer's memory that we can use. It has things like the interpreter for the code if we need that. There's all kinds of different things that are in this process. But this process is made up of something called threads, okay? Now, up until now, we've been writing single-threaded applications, which means we have a process that's running our application, and that process contains one single thread. That makes things very simple. However, if we were to increase the number of threads that we have, we would actually be able to increase the speed of our program in certain applications. So just kind of keep that terminology in mind. We have a process. Within that process, we have different threads. Those threads share things in the process like memory, so random access memory where we have different variables, functions, etc. But those threads are independently executing, which I'm going to talk about now. So on our CPU cores, what these are capable of doing is executing different threads. What happens is one of our CPU cores will have a thread that is essentially being passed to it and saying, hey, I have some operation within the thread that I need you to perform. So that kind of means that if we have multiple threads in our application, we can actually distribute these threads and have them being executed on multiple CPU cores. So if I only have one thread, right, and everything in my code is happening in this single thread, then only one CPU core can be working on my application at a time, because all of our CPU cores are taking a single thread and working on that thread. But if I split this up into a second thread, now all of a sudden another CPU core can be working on my application at the same time in parallel. So now I can essentially 2 times the speed of my application, not necessarily precisely that, but you kind of get the idea here, by distributing it into multiple different threads and then allowing those threads to run in parallel on multiple CPU cores. So let's back up a little bit. I'm just trying to give you a bit of insight into what we're going to do in the future video. So one CPU core is capable of doing 1 clock cycle or 1 operation per any given unit of time, okay? That means that this CPU core can only work on 1 thread at a time. But since we have 4 CPU cores, that means the CPU as a whole can work on 4 threads at the exact same time in parallel. Now, what happens though if we have more than 4 threads? Well, that's almost always the case. On our computer, and you can actually go look at this, you'll see that you have thousands, probably tens of thousands of different threads. Now, this gets into how the computer actually manages and schedules these threads, but what will happen is we have something known as a thread pool, okay, where we have tons of different threads. Now, pretty much the operating system, so our OS, is very, very clever, and it will determine which threads need to be executed, and it will take those threads and it will essentially pass them to the different CPU cores and say, hey, right now you need to work on this thread, this thread, this thread, this thread, and then concurrently what will happen is we will pass different threads and kind of swap what we're working on. So any given CPU core is going to constantly be switching between tons, probably thousands of different threads and working on different operations within each of those threads. That's what allows you to run all kinds of different applications, have all kinds of different things going on at your computer at the exact same time. It's not because you have 10 million CPU cores, it's because the operating system is very good at scheduling how these threads are being executed and utilizing the full capacity of your CPU. So if you have tons of different threads, you will pass those threads in a very logical order to the different CPU cores. Those CPU cores will switch between operating on different threads concurrently, which I'm going to talk about in 1 second, and that allows you to get this feel of having, a million things happening on your computer at the exact same time. Really, what's going on is you have these individual workers. These can only do one thing at a time, but they switch between all these different tasks and keep executing them concurrently. Now, concurrently means that we're working on something at the same time, but it's not happening at the exact same unit of time. I know it's very confusing because it sounds similar to parallel, but running in parallel means literally at the exact same unit of time, you're doing something. Concurrently pretty much means you're switching between different tasks and you're working on all of them, but you can only be working on one at a time. So within one CPU core, we have concurrent operation. Within multiple CPU cores, we have parallel operation, where we work on multiple threads at the exact same time. Hopefully this is making a tiny bit of sense, but these threads that I'm discussing are known as software threads, okay? Now there's something known as hardware threads, which we're not going to get into here. Now the reason I'm even discussing that is because on modern CPUs, we have something called hyper-threading and virtualization, which essentially allows one physical CPU core to actually act as multiple logical cores, which allows it to actually perform some more operations and be more efficient. We don't need to get into that in this video. For now, just imagine that each CPU core can just execute one operation. Okay, quick recap here. We have different threads. These threads make up a process. A process is some application that's running on your computer. We can have multiple threads in a process or just one. These different threads are what gets scheduled to run on your CPU. The CPU, based on the number of cores, will go and execute all of those different threads, switching between them as it needs to so that it can actually work on all of these things at the same time. What that means for us as a programmer is that if we take our application, right, so we have app right here, and we split this into multiple threads, we can increase the speed at which we're running or executing our code depending on the application, because now we are able to utilize multiple CPU cores at the same time rather than only using one core to act on our thread, okay? So the act of multi-threading is distributing your program into multiple independent threads that can run independently of each other and then putting them on multiple CPU cores. Now, we don't actually have to be the one that's saying, hey, run this on core 1, run this on core 2, etc. Our operating system and programming language will handle that for us, but we need to be the ones that separate kind of different logical pieces of code on these different threads, so then we can take advantage of multi-threading and of parallel processing, okay? So hopefully this is making a bit of sense, but that's the basic information we need to understand about threading. Now, let's just go into a quick example of when we might use threading so that we have kind of some basis for that as we move forward. All right, so I'm going to clear the screen here. All right, so let's get into an example here where we might use multiple threads. So let's say that we have some kind of application. Now, this application can be really anything that we want, but we need to imagine that there's a few different things that this app needs to do. So when we launch the application, we need to load a few different pieces of data. For example, we may need to fetch something like the chat history for a user. We may also need to fetch maybe the user's friends. And then while all of that's going on, we want to allow the user to maybe do something like create a post, okay? So we've got kind of three main operations here. We need to fetch the chat history, fetch the friends, and then we want to allow the user to create a post. We could also be fetching those different posts. Now, if we were to take this code, or if we were to take this application and write this in a single thread, so let's imagine this is our code right here. What would happen is the following. We might start by doing something like fetch chat, okay? Now, when we fetch the chat history, what's going to happen is we need to go to some type of server, okay? And this server is going to take, a few milliseconds, a few hundred milliseconds, I don't know how long it will take, and it will return to us some kind of chat history. The point, though, is that we have another computer that we need to go to get some data, and then return that kind of to our client, right? Where the client is the application that's actually running this code. Now, while this is happening, while we're going to the server, we're going to be waiting a certain amount of time, 100 milliseconds, 200 milliseconds, a second, 2 seconds. I don't know how long it's going to take. The point, though, is that while we're waiting for this data to return, we're not doing anything, right? Nothing's happening on our CPU. We have no operations that we're performing. We're simply waiting for something to come back. However, since we have all of this code being written in a single thread, that means that I can't actually move on to the next line here. So say something like get friends, right? Until I receive the result from the network or from the server. So what happens is I start by fetching my friends. I wait maybe, say, 300 milliseconds. Then I go ahead and I fetch my friends. Now, same thing, I go to the server. The server is going to return some result to me. And maybe this time it takes 400 milliseconds. Then I have a function here like post, so I allow my user to create a post. Same thing, when they make a post, I got to go to the server, submit some post, and then it kind of returns back to me and says, hey, this was successful. So the idea here is that these first two load operations take 700 milliseconds in total before we're able to get down here to this post operation. Now that's not ideal because that means that we are hanging or we are waiting for these to be finished before we allow the user to actually be interacting with our application. So obviously this is not ideal. We have a 700 millisecond wait. This could obviously be a lot longer. Imagine it's 20 seconds, 30 seconds, whatever. And in that time, our processor isn't doing anything. We're just waiting on this network bound operation. So how would we fix this? Well, we would fix this by using multiple threads. So let's kind of clean up this example here. And let's see what happens now if we put these into 3 different threads. Okay, so let's get rid of this and go to threads. All right, so now let's say we have 3 threads. Now, one thread will be for the chat, one thread will be for the friends, and this will be for post. Now what we can do is we can take these 3 different threads and we can put them on our CPU, right? So now what we can do is we can take these 3 different threads and we can start executing them in parallel on our CPU. That means that we create this chat thread. The chat thread then goes and fetches the data here from the server. Now, it still takes, 400 milliseconds to return this data. However, we don't need to wait for this to finish before we can start executing the friends thread. Since this is in a separate thread, it can be executed on another CPU core or the same CPU core, it doesn't even matter, but we're able to now go and fetch data at the same time that we're fetching data for the chat. So now, same thing, we go to a server, we get some kind of data. Maybe this takes 300 milliseconds. Doesn't really matter how long it takes. The point is that we do both of these things at the same time. So now the total amount of time that we need to wait to get both the chat and the friends is simply the greater of the amount of time it takes to get either, which in this case is only 400 milliseconds. because again, we're in separate threads, meaning we can execute at the same time, or at least be concurrently executing. So I'm not waiting on the chat to be returned before I start executing the friends, or before I start fetching those. So now I get both those pieces of data in 400 milliseconds. And the best part of this is that the user can decide to make a post at any time they want. Since this is running in its own thread, we're not waiting on chat, or we're not waiting on friends to be returned. We can just go and do whatever we want while these different operations are happening. So this is kind of the benefit of our threads. Our CPU is smart enough to never be sitting on a thread and waiting for something to be returned. As soon as the CPU is not doing something, it's not executing an operation and we're waiting on some return data, it just goes and does something else. But that's only the case if we have this in multiple threads. The CPU is not smart enough to kind of jump throughout our program and say, okay, I'm waiting here, so I'm going to go here, then I'm going to come back and get the result. No, it's only able to schedule the execution of different threads. So us as a programmer, if we split our code into multiple different logical threads that make sense, we can drastically increase the speed of our program because we allow the CPU to move to a different operation while it's waiting for something to occur. I'm hoping that this example is making a bit of sense. In the next video, when we actually go into Go routines, we'll see an implementation on the computer that should really clarify this. But I'm just trying to illustrate to you the idea behind breaking our program into these different kind of pieces of code, right? Which are these threads that execute independently and that don't need to wait on each other before we can move on to something else. Now, obviously, in some instances, we do need to wait for a thread to finish running before we execute another one, but a lot of times we're running multiple threads at the same time, so we do all these operations concurrently, which saves us a ton of time. Now, Go routines are the implementation of concurrency in Go. They make it very simple to actually create new lightweight threads that can be ran independently of other sections of code, allowing us to implement parallel processing and concurrency and multi-threading inside of our Go programs. So everything I was talking about in the previous video, I'm now going to show you how we actually implement that here inside of Go. All right, so let's begin here by creating a function. I'm going to say function, and we'll just call this, I don't know, run or something. And inside of here, we'll do something quite simple, like fmt.println, and then we'll just say run. Now what I'm going to do is just import another module here. This is going to be called time. Let's put these on a separate line. Okay, and we're going to use this time module or time package to just wait a little bit. So we're going to say time.sleep, and then I'm going to say 2 multiplied by time dot, if we can spell this correctly, dot second. Okay, now I'm going to make a few other functions. I'm going to call this run2 and run3. We're going to say run2, run3. We're going to change this to be 4 seconds and to be 6 seconds, okay? Then what I'm going to do down here is show you how we run these functions concurrently. So the way we do that is we type go, and then the name of the function we want to run. So we just say go run. Now what this is going to do is actually run this in a new thread, okay? Well, that's kind of the way to think of it. It runs a new Go routine for this function. Then I can do the same thing here with run2, and the same thing here with run3. Now we'll see if we have an fmt down here. I'm going to say fmt.println done. And if we go and run our code, so go run and then demo.go, that we actually only get done printing out. Now the reason why we only get done here is because what happens is we have one Go routine that's running this main function. We then create 3 new Go routines that are running these. However, when we do that, that means, okay, well, we're running these independently, so we're not going to wait for those to finish. We're just going to directly go down here and print done. Then what happens is, since there's no more code being executed in this main function, our program is going to stop because the main Go routine has exited. Not sure if that makes sense, but we create 3 other Go routines, and then we immediately go down here and print done because these are running independently of this main Go routine. Then the main Go routine is finished executing, so we just end the program. So what we need to do if we want to fix this, if we just need to add a time.sleep here. So we're going to say time.sleep, and we'll sleep for 7 multiplied by time.second. So now we actually have enough time to just wait for all of these Go routines to finish executing. So now if I run my code here, and I go run demo.go, you're going to see that we get run, run2, and run3. Okay, and then we print out done. Now, I'm not sure if you guys were counting there, but that took a total of approximately 7 seconds to execute the entire code, even though if we were to sum the times or the sleeps for all of this code here, this would be 12 seconds, right? Because we have 2 seconds, 4 seconds, and 6 seconds. So by using these go routines, we're able to execute all of this code at the same time, where we sleep for 2 seconds, sleep for 4 seconds, and sleep for 6 seconds, but the total amount of time we need to sleep is only 6 seconds. Because while we're sleeping this 6 seconds, we're sleeping 4 and we're sleeping 2. I'm hoping that's making a bit of sense, but to illustrate this even further, now let's get rid of this. Okay, and we'll actually get rid of the time.sleep. And you're going to see now, if we do this, that we're going to take significantly longer. And the way to actually illustrate this better is just to have the same duration for all of them. So now we can go here and go run demo.go. Give this a second, and notice we get run 2, and then run 3, and then done. So that took a total of 6 seconds, which is the total amount of time that we had if you summed all of the sleeps. So we waited 2 seconds, printed this. Waited 2 seconds, printed this. Waited 2 seconds, and printed this. Now, if we make these go routines, you'll see that all of these will happen pretty much instantly, so at the same time. So let's run this and give it a second. And actually, I forgot we need to have our time.sleep, so we'll have time.sleep 2 times time.second, okay? Clear and run. And now you see that all of these will print at the same time. Notice that the order was not the same order in which we ran these. The reason for that is that we can't actually guarantee the order of these go routines because the sleeps are the exact same duration of time. So it's really based on how our processor is scheduling these different threads, which we don't know. We don't really know how our processor is going to schedule run 2, or run 3. We just know they're going to be in separate threads and can execute at the exact same time. So in this example, you saw that by making these go routines, now they're able to execute at the same time. We're not waiting for one of these to finish before we go on to the other one. So hopefully this is making a bit of sense now, but let's get into a more complicated example where we can see how to actually get return values from go routines and start synchronizing some of these pieces of code. So I'm going to get rid of all these functions here, which means we're going to get rid of all of this, and we'll get rid of the time.sleep. Now, as you saw before, what happened was we actually had to sleep so that we would execute all of those different go routines. But there is a way that we can wait for a go routine to finish running. In fact, there's multiple different ways to do that, which is what I'm going to show you now. So right now, let's make a function, and we'll just call this add, okay? We're going to take in x int, y int, we'll return an int, and we'll simply return x plus y. I've seen this function about 1,000,000 times. What we'll do now is we'll run this add function as a go routine. So I'll say go, add, and then something like 5 and 10. However, I probably want to get the return value from this function. So I might do something like x (= 2, and then go add. Now notice when I do this, it actually doesn't work. It says expected semicolon, found go. The reason why we're getting an error here is because when we run something as a go routine, we can't wait for the return value. Now this kind of makes sense, right? Because what happens is as soon as we start running this in a separate thread, now we are not going to wait for this to finish. We're just going to move on to the next line in the current thread, wherever we are. So we would immediately go down here, meaning that we're not going to be able to store whatever the return value is in the variable x, unless we were to wait on this line for the go routine to completely finish running, which we're not able to do with this go syntax. So what we need to do instead when we want to get return values from go routines is use something known as a channel. Now, a channel is a special way that we can pass values between different go routines, and we're allowed to send values on a channel and wait for values to be received. This allows us to implement something known as blocking code. Okay, so how do we make a channel? Well, to make a channel, we're going to say whatever we want. I'm just going to call it ch (=), and then I'm going to use this make function, and I'm going to say chan, standing for channel, and then in this case, we're going to make it an int channel. What we've just said is we're creating a channel that we can place an int on. Now what we need to do is we need to give this channel to our go routine. So I'm going to pass the channel as one of the parameters, which now means I need to accept the channel inside of this add function. So I'm going to say I have a channel, we call this ch. This is a channel of type int. So now we have a channel of type int here that we're accepting as a parameter, and that means that I can now pass a value onto this channel. So to do that, I'm going to say ch, and then I'm going to put an arrow like this, and I'm going to pass xy into the channel. Now I'm going to remove the return value here because we're no longer returning anything. We're just passing a value on the channel. So to pass something on the channel, you just do the arrow, okay? And then you have whatever value you want to pass, so long as it's the same type. So now if I want to receive a value from a channel, I put an arrow like this, and then I put ch, and I can store this in a variable. So I can do something like x (= that, and then I can print out the value of x. So now what happens if I run my code is you can see that we get the value 15, which is 5 plus 10. So let me break this down more. I just wanted to quickly show you kind of the syntax of the channel, which I know looks a little bit weird. So we cannot simply get a return value from a go routine. What we need to do instead is pass that on something known as a channel. The channel allows us to synchronize and wait for different values to be returned. So in this case, what I do is I make a channel, I then call a go routine, I pass the channel to it. I then pass a value onto that channel, and then down here, I wait for that value to be returned. So this line is what's known as blocking code. I'm not actually going to move past this line and print anything out until I receive some value from the channel. So to illustrate that, if I say time.sleep, and then I sleep maybe 5 times time.second like that, you'll see here that it's going to take us 5 seconds to actually print out what the value is, because we are waiting, we are blocking until we get a value on the channel. So you can see here, 1, 2, 3, 4, 5, and there you go. We get 15 being returned to us, which means if I scheduled another go routine, so I said go, and then I ran something here, that wouldn't run until after this code was finished. Hopefully this is making a bit of sense, but this operation where you're waiting for something to be received on a channel is a blocking operation. Now let's see what happens if I remove this and I just schedule the go routine here and I do something like fmt.println and then done. Well, if I go here and run, you notice that we just get done. The reason we just get done is because we didn't wait for the value on the channel, so we just immediately went here and printed out done. Now let's look at an example where we do the opposite. So we have x colon equal to, we get the value from the channel and then we print out x, but we don't actually send this value on the channel. So if I go here and I comment this out, okay, now if I go and run my code, you'll see that this actually runs for 5 seconds, and then it's going to give us something known as a deadlock, which occurs right here. It says fatal error, all go routines are asleep, deadlock. Now a deadlock occurs when no threads are under execution. So the reason we're getting this deadlock here is because we're waiting for some value to be passed on the channel in this go routine, which means we're blocking, we're waiting, we're just stalling here, and nothing gets returned. So as soon as we have no go routines in our program that are executing, nothing's happening in any of them, we get a deadlock, which means we're deadlocked between the different threads. One thread is waiting for another thread, that thread's waiting for the same thread, and well, we can't do anything. In this situation, we just have one thread that's waiting for one thread to return something. It never returns something to us, so this thread is never able to continue to execute, so we get a deadlock. So you have to be careful when you're writing these types of programs that you don't implement deadlocks, because the compiler is not actually able to catch that for you. In this case, this was a runtime error where no thread was under execution, so we got that deadlock error. Okay. Now let's look at a few more advanced examples of channels and using multiple channels. So let's say we actually want to execute multiple add operations here, okay? So we want to have the go routine for add running a bunch of times. Now let's get rid of the sleep here so we don't have to wait anymore. And we can get rid of the time package for right now. So let's go like 8 plus 11, 0, 5 plus -5. Okay, that's fine. And now let's see if we can get the value from the channel. So we'll say x colon equal to, and then we're going to put here the channel, and we're going to say fmt.println x, and then I'm also going to go in here, and say fmt.println, and we're going to print x plus y. Okay, so we're going to calculate it, print it out, then we're going to pass the value onto the channel. So if you want, go ahead and pause the video here and take a guess at what you think the output of this code is going to be. I'm going to go ahead and run it, and you're going to see that we simply get 5 and 5. Now, that is kind of a weird thing to be able to predict, right? Why is it that we're getting 5 and 5? First of all, the first go routine we ran was 5 plus 10. So even if we're only going to get one value, you'd think that's going to be 15. But no, what happens here is we run all these 4 go routines pretty much at the exact same time in separate threads. We come up here, we print something, and then we pass a value on the channel. Then we have this line right here where we wait for a value to be passed on the channel. This line only waits for one single value to hit the channel. As soon as a value hits the channel, we continue and then we print this, which means what happens is we get one value, so whatever the first value is coincidentally here to be returned, we print that out, and then we finish the main go routine, which means we don't wait for any of these other threads to execute, meaning we don't get any more print statements and no more computation occurs. So when we do this line here, when we wait, we're waiting for a single value on the channel. So each send is associated with one single receive, okay? Now, if I wanted to wait for multiple go routines to return, what I need to do is have this 4 times. So I would have to say x is equal to channel like that, and I can just keep doing this, okay? So now if I put this 4 times, you'll see that we'll wait for all 4 of those values. So we get 15, 19, 0, 5. And if I run this again, you'll see that we probably get it in a different order. We have no idea what the order is going to be because, again, we don't know how our threads are going to be scheduled on the CPU. But now we're waiting for all 4 return values from our channel, but we have no idea in which order we're getting these different values or which call actually returned that value to us. So in this situation, we could use multiple channels, but I'm just trying to show you kind of how the channel works here. Now, let's say we do this, and we kind of switch this up, and we just say x : equals to this, and then let's take this, paste this here, okay? And let's do these kind of in between the different go routines. So now get a guess at what you think the output is going to be. Well, when I run this, notice that I actually get everything happening in the order in which I scheduled these go routines. The reason why we get it in the order is because we schedule this go routine, it starts executing. It returns a value to the channel. We immediately set x to that value, and we wait for it to get returned, right? So we don't actually start this go routine until the value from the first go routine is returned. Then we do the same thing here. We run this go routine, we wait for a value to be returned, then we schedule the second one. So in this case, we're actually kind of doing this synchronously in order, not concurrently, like we did before when we scheduled all 4 and then waited for the values to be returned. Now let's do a quick example where we use multiple channels. So we can actually do the same thing we did here. Just make a channel 2 and say make channel int. And by the way, for your channel, you could have like a slice on the channel. You can do all kinds of different types. You don't have to just do an int. I'm just doing simple ones for right now. Okay, now let's run 2 go routines. Let's run go add 10, 5, and then channel, and go add 20, 15, and channel 2. All right, now we have the ability to wait for either of these values. So I can do something like x : equals to, and then channel, and then y : equals to, and then if I can type this correctly, channel 2. Then I can print out x and y like that. All right, so this will work fine. What we're going to do is wait for a value to be passed on the first channel, and then wait for a value to be passed on the second channel, which means we're going to get the first value first and then the second value second. However, we don't necessarily know which go routine is going to execute first. So that's fine for right now, but let's execute and just make sure this works. And notice that we get our values, 15 and 35. It was actually coincidental that this second go routine ran before the first go routine, but anyways, that doesn't really matter. Now what I want to do is I want to add a dynamic delay here. So I just want to say delay int, and I want to say time.sleep delay times time.second. We need to import time here. And I actually need to make this a time.duration so that these are the same types and I can multiply them by each other. Anyways, that's what we're doing here. So we say time.sleep, and we're going to wait some dynamic duration. And now I'm going to pass in 4 seconds here and 2 seconds here. So what you're going to see here when we run this is we first get the value for channel 2, which is 35. We then get it for 15. However, we're not able to actually print out this 35, right, until we've got the 15. So the way that I've done this here is forcing me to wait the full 4 seconds before I'm able to receive the value for Y, or for channel 2. Now again, in this instance, this is fine, but sometimes what you want to do is be waiting for either channel 1 or channel 2 to return a value and process them in the order in which they're returned. Meaning what I would want to do is print out the value of channel Y or process that value before I'm waiting for channel X. So just imagine the scenario, right, where you have a bunch of go routines. You don't know in what order they're going to execute, but as soon as something gets returned from them on the channel, you want to immediately handle that. The way that I'm showing you right now, you have no way of doing that because you don't know which one you should be waiting for first or second. However, there is a new piece of code we can use known as a select statement that allows us to actually handle any different channel that's being passed. So let me show you what I mean by this. I can say select, and then I can write a case. Now for this case, I'm going to say receive a value, so x : equal to, and then receive a value from channel. Then I'm going to put a colon here, and then what I can do is fmt dot print line, and then print x. Then I can write another case, and I can say y : equal to, and receive a value from channel 2. And then I can say fmt dot print line, and then print out not x, but y. Then we can get rid of that print, and we can get rid of the print inside of here. So what I've just done is written this select statement. The way the select statement works is it waits for either of these channels to have a value on them. So either this channel or channel 2. It doesn't know which one it's going to be, but as soon as either of these channel gets a value, it goes into the case where that value was received and then handles whatever the output is. So in this case, you'll see that in 2 seconds, we will handle the output for y, and then we'll just move on. So whatever value we got first, we handle, and then we just continue with the program. Now, I might want to be waiting for both of the values to come in, which I'll show you how to do in 1 second, but the select is quite useful because when you don't know which is going to be returned first, you can wait for all of them and just process whatever one comes in. So in this case, y came in first, so we process y. If x had come in first, we would have processed x. Now, if I want to make sure I get both of the different values here, what I can do is say for underscore colon equal to, or something like, actually, yeah, let's do this. For I colon equal to 0, I less than 2, I plus plus, and then I can put the select statement inside of a for loop. And what's going to happen now is I run the select statement twice. So as soon as I get my first value, I handle it, whether it's x or y. Then I wait for my second value, and whether that's x or y, I handle that. Again, not knowing what order this is going to be returned in. So now when I run this code, you'll see that we get 35, and then immediately we process 15 as soon as we get that. Now, if we change these delays to be the same, and we run, you'll see that whatever order it comes in, we process that in that order. So just coincidentally, it was 35 and 15. Let's see if it goes to 15 and 35. And it does. You can see that it kind of switches around, and we process in whatever order that is. Okay, so that is a select statement. Quite useful. Definitely kind of remember this and see how this works, because a lot of times, again, you have multiple go routines. You don't know which one's going to return first. So you select on those cases, and then you can handle in any order in which they are returned. All right. So that kind of wraps up channels and select. Now I quickly want to talk to you about directional channels, buffered channels, then we have a few more advanced examples to go into. Okay, so right now we have just a general channel. Now that means that we can actually wait for a value inside of this go routine. So it's possible that we have go routines waiting on other go routines, and we're passing channels to those routines so that we can synchronize the execution of code. So what I can do in here is I can do something like wait for a value. This is perfectly valid. That means that now inside of this go routine, I'd be waiting for something to be passed on the channel before I start executing it. And it's possible a different go routine will be the one that's actually interacting with this channel and passing something to me. So I can always do this, that's perfectly fine, when I have a bidirectional channel. But what I can do is accept inside of here a directional channel. Now to accept a directional channel, I need to just specify the direction. So in this case, if I put my arrow like this, what I've done now is made this a receive-only channel. So if I highlight over this, it says invalid operation, cannot send to receive-only channel. So if I want to make this a send-only channel, I put it on the other side, and now I'm specifying, hey, I can send to the channel, but I cannot receive. So now if I go here, and I attempt to receive, you see we get the error, and it says invalid operation cannot receive from send-only channel. So just something you can do inside of the parameters. You can specify the direction of the channel, which makes your code a little bit more clean and kind of easier to work with and understand if someone else is reading it. Okay, so that is a directional channel. But now let's talk about a buffered channel. So to talk about the buffered channel, I'm just going to clear the screen and go into a new example. I'll be right back. All right, so I've just cleared the screen. Let's get into an example of a buffered channel. So first of all, let's see what happens when we make a normal channel. So channel is equal to make, and we can just do a channel with a Boolean. Now, let's say we're going to send something to this channel. So I'll say, okay, channel, and send something like true. And then I'm going to receive the value from the channel here, and then fmt.println done. Okay. So let's go here and clear and see what we get. And notice that we actually get an error here. It says all go routines are deadlocked. Now, the reason we're getting this error here is because of how the channel functions. Whenever we have a send on a channel, this is actually a blocking operation that waits for the channel to receive this value. I know this seems a bit strange, but every single send that we have is waiting for a value to be received. So when I do this send operation here, we don't actually move on to the next line. We don't continue in this go routine until we see this receive block in another go routine or just somewhere, right, until it appears. So this is blocking until we receive. And same with this receive, it's blocking until a value is sent onto the channel. So that means that as soon as I send a value onto the channel here, immediately I start waiting on this line for it to be received. But since the receive is on the next line, I can never reach that receive, which is why I get a deadlock. So I've implemented a deadlock with just a single go routine here, because I send, that I then wait, but I never have anything that receives because that's on the next line, so I'm not able to continue in the program. That's what happens when you have an unbuffered channel. Unbuffered channel is a channel that can have one value on it at a time. Now, even if I do receive, so I go function, just go R here, okay, we'll take in a channel, we'll say channel, chan, bool, okay, and all I do in here is just receive, right? Now, as long as I schedule this go routine first, so I say go R, and then I pass the channel, then when I send, it will receive, and then this should be fine. All right, so now we have this example. Let's see what happens, and notice that this is fine because now we are receiving. However, let's see what happens if we send another value on the channel. Okay, so I send true, and you'll see here that we get a deadlock because the same thing happens. We only had one receive for the send, okay? So this kind of got matched with this function right here. Then we had another send that was waiting for the corresponding receive. The receive never occurred, so this blocked. If I ran another go routine that was receiving, then we'd be fine. So if I run this here, you can see that now it's okay because we have corresponding receives for every single send. The point of me showing this to you is that we can avoid this when we use a buffered channel. When we use a buffered channel, we'll wait for a certain number of, values to be added onto the channel before we start having a blocking operation. So what I can do here when I make the channel is I can specify size. I can specify size, say like 2. Now what I've done is created a buffered channel that can receive 2 different values on it. All right, so now that we have this buffered channel, let's look at the same example and I'll kind of explain how this works. So let's send a value to the channel, like true, and then let's try to receive a value from the channel. So channel, receive, nope, not like that, other way around, channel like that. Okay, so now let's run the code and notice this is actually completely fine. Now the reason this works fine is because a buffered channel works differently than a normal channel. With the buffered channel, we only block when we're trying to send data to the channel and the channel is full. So to illustrate that to you, if I place 2 values here, okay, and then I clear and run, you see that this still continues to work. Now this still works because at this point when I add the second value, the channel becomes full, but I'm not trying to pass another value onto the channel. It had room. However, if I go here and now I attempt to add another value onto the channel, you'll see that we get a deadlock. The reason we get a deadlock is because this line blocks and waits for a corresponding receive so that we can kind of empty the channel, right? And have enough room on the channel to be able to send this next value. So whenever the buffered channel is full, then we're going to be blocking when we're trying to send. If it's not full, then we'll just allow ourselves to continue to add values to the channel. So if I take my receive and I put this here and I clear and run, you see that now everything's fine because what happens is I have 2 values that I pass onto the channel. I then receive one of those values, which clears that off the channel. And then I send another value. And at this point, it's fine because there's enough room on the channel for me to pass that there. Okay. So that's when we get that blocking code. Now, what happens if we try to receive a value from an empty channel? Well, if I try to receive a value from an empty channel, I get a deadlock. The reason I'm getting a deadlock here is because this will block as well. So whenever I'm trying to receive a value from an empty channel, this is blocking code, meaning I'm waiting for a value to be added onto this channel. Since a value never gets added, I get a deadlock, okay? So when you use the buffered channel, all that's happening is your blocking code now changes so that only on an empty receive, you're blocking, or on a full send to the channel, you're going to have blocking code, okay? Hopefully that's making a little bit of sense, but that is the buffered channel. All right, so now that we've looked at a buffered channel, I want to talk to you about something known as a lock or a mutex. So let me set up a quick example here, and I'll show you how that works. All right, so I've set up another example here where what I'm doing is attempting to count to 100 using 100 different Go routines. So I have this counter struct, very simple, just has a value inside of it. I then have this count function, which takes a pointer to the counter struct just so that we can directly modify the field. Then we say counter.value ++, so we just increment it by 1, and we print out whatever the value of the counter is. I then say counter : counter at 0, so we're just setting it to be 0, and then we're looping through 0 to 100, and we are creating 100 Go routines that are going to allow us to count to 100. Now, what I want to show you here is that when I run this code, the output I get is a little bit strange, okay? So I've go run demo.go, and you'll notice that kind of as we go through here, I get all kinds of different counts that are all kind of slightly random. And it's possible I could actually have repeated values inside of here. It's just kind of strange how this works, right? So you can see that we go 1, 22, 3, 28, 5, 79, 93, because we don't know the order in which these different threads are going to be executing. And what happens is they're all kind of accessing the value field of my counter struct at the exact same time. Now, this is a big issue in multi-threaded programs where you have multiple threads accessing the same memory address location at the same time. When that occurs, then threads can be changing and modifying things and can result in some really weird behavior, where thread 1 goes and changes the value to 1, thread 2 immediately changes it to 0. And what that means is you get very weird kind of resulting values here, and you can see at the end of our program, I'm printing out 8, right? Like, does that make any sense at all? Not really. So how do we fix this? Well, the way we fix this is by using something known as a mutex or a lock. Now, a lock is something that we can acquire and release on some resource or value. So what we're going to do here is implement a mutex. What this mutex, it's kind of just referred to as a lock, by the way, so mutex and lock are pretty much synonymous. What the mutex will do is block until we have released the lock from another piece of code. I know it seems a bit weird, but inside of count, what we'll do is we'll say, okay, I want to wait for my lock to be available. As soon as the lock is available, I'm going to lock that lock and say, hey, I'm working on the value right now, so no one else can work on this. Now, as soon as I'm finished working on this, I'm going to release the lock and then allow the other thread to go and work on it. So we're essentially just forcing the threads to wait for the other threads to execute or work on this field or this resource before they're able to do that. So the way that we do this is we import a new package called sync, okay? Now, inside of our counter struct, I'm going to create a lock. So I'm going to say lock is equal to sync.mutex, okay? So this is the type here for our lock. Now, for our counter struct, I'm just going to initialize this with nothing, so we have the default value of 0, and we have a lock. Now, inside of my counter, or inside of my count function, I'm going to acquire the lock. So to acquire the lock, I'm going to say lock dot, and then I believe this is actually going to be lock. Actually, sorry, this needs to be counter.lock. Now, what this function does is it waits for me to be able to lock the lock. So if the lock is already locked, I can't do that. I need to wait for it to be unlocked. Then I'm able to lock it. Then I'm going to defer the operation, which is counter.lock and then unlock. Now, the reason I want to defer this is to make sure that if anything happens in my thread that kind of breaks the code, etc., that I will always do this operation, okay? So this is kind of an error handling strategy, and I'm also doing it directly under counter.lock so that it's clear that, hey, I'm locking, and then at the end of the function, I'm going to unlock. All right, so I'm deferring that operation. Then I have counter.value++, and then I'm printing out the value of counter. So now what you'll see is that when I print out all of the different counts, we will go directly from 0 to 100 or from 1 to 100 because we know that we are going to always have to acquire the lock before we're able to perform an operation on this value. Okay, so let's clear and run this. And now you'll see that we'll get from 1 to 100, okay? Now, what really happens here is we run the first go routine, it acquires the lock. Then it changes the value and it releases the lock. Now, while it's doing that, right, while it's locking, unlocking, and changing the value, all of these other go routines are being ran, right? So maybe 100 go routines are running and they're all attempting to acquire the lock. So as soon as the first one acquires the lock and then releases it, that then allows the second go routine to acquire the lock and then release it. So it's going to go in order because of the fact that we have this kind of locking mechanism occurring here. And it actually doesn't even matter if go routine 1 or 7 or 10 acquires the lock because all we're doing is adding 1 to the count value. Now, since they're all going one at a time, they're not mutating it at the same time. That's what allows us to get this clean count going from 1 to 100. I'm hoping that makes a little bit of sense. But that's kind of the basics on using a mutex. So whenever you have some shared resource, in this case, we have the counter struct, you need to make sure you're locking the usage of that resource so that multiple threads aren't accessing it and modifying it at the same time. Okay. Now, one thing I want to show you here is that we have this time.sleep, right? Now, the reason I implemented this time.sleep is because I need enough time for all of my go routines to run. If I didn't have this, then immediately the program would just end. But that's not ideal, and I don't really want to wait for 2 seconds when maybe this code can be executed in 1 second, a millisecond, etc. So how do I actually wait for all these go routines to finish running? Well, there's many different ways that I can do that. One of the ways that I'll do that is by using a channel, okay? So what I can actually say here is ch colon equals to make channel, and we can just pass a Boolean, okay? Now what we'll do is we'll pass this channel to our count function, and we'll now accept the channel, so ch chan bool like that, and we can say this is a receive only channel, or sorry, I believe it's going to be a send only channel. Now, at the end here, we'll simply send some value to the channel. So we'll say channel, and we'll send the value true. Now that I've done that, what I need to do is wait for all of these different receives on the channel. Remember, every single send needs a corresponding receive. So I'll create another for loop, say for I colon equal 0, I less than 100, and then I plus plus, and then I will say receive the value from the channel, okay? Now, it doesn't really matter in which order I get these values, but I'm saying I'm going to have 100 receives for the 100 sends, which means I wait for every single go routine to finish before I finish executing this code, okay? Because I have 100 blocking operations. Every single time I get a send, I then have the corresponding receive, and I kind of go back and forth, back and forth, back and forth, allowing me to wait for every single one of those to execute. So I'm going to clear and run, and we got an issue here. Time is imported and not used. Okay, so let's get rid of time. Let's clear, make this a little bit larger, and run. And you can see here that we get all of the different values, and we didn't have to have that time.sleep. Okay, so that's one way that you can wait for all of these different values to be returned. Now, another way is to use something known as a wait group. Now, a wait group is a kind of special object that exists here inside of Go that kind of does exactly what I just showed you and avoids you having to use this channel when you don't actually want to return a value. So what I'm going to do here is create a wait group. So to make the wait group, I'm going to say wg is colon equal to, and then this is going to be sync dot wait group like that. Then I'm going to initialize that with a set of curly braces, actually, because I believe this is a struct. It is a struct. Okay, perfect. So for the wait group, I'm going to say wg dot add, and I'm going to add 100. Now what that means is that I'm adding 100 go routines that I want to wait for. So all this is going to do is give me some kind of count where I can then decrease this, and as soon as this wait group is at 0, then I'm finished with the wait group, okay? So I have wg, my wait group dot add 100, and now what I'm going to do is pass a reference to my wait group, so ampersand wg there, and now rather than my channel, I'm going to take in a wait group, so wg wait group like that, but this needs to be a pointer to the wait group, okay? Then I'm going to say wg dot done. It's going to automatically dereference that for me because it's a struct. And now rather than using my channel, I'm using the wait group. And then down here, I'm going to say wg dot, and I believe it's not done. I think it's actually just wait. Okay, so now what I've done is I've said, all right, I'm going to add 100 go routines that I want to wait for. And then I'm going to call this done method. And every time I call that done method on the wait group, it's going to decrease the number here. As soon as that number is 0, then this will no longer be blocking, and it will allow me to continue. So now if I run the code, you can see that we get the exact same thing, and we don't need to have that time.sleep. Now there's a bunch of different ways I could have done this. First of all, rather than wg.add 100, I could have gone here and said wg.add and then added 1. I just need to make sure that I add this before I run the go routine, because if I do it while I'm running the go routine, then it's possible that wg.wait will actually not need to wait because it will be 0 as soon as we kind of get past this for loop. I know this seems a bit weird, but what can happen is if we don't add this before we run the go routines, it's possible that we won't have that kind of equal to 1, 2, 3, whatever the number is when we reach this line of code, which will then mean we're no longer blocking, which we want to be doing because we're waiting for all of these go routines to finish executing. So let's clear and run. And again, you can see that that's working completely fine. Okay, so I think with that said, I'm going to wrap up the video here. I know there was a lot, and this is probably the most complicated video that we've had in this entire course. The point here was to give you a bit of insight into what happens when you are distributing your applications and creating multi-threaded programs. This is something that you'll do a lot more if you're looking into backend, right? So if you're going to be a backend developer, you're looking at performance, you're doing low-level machines, working on embedded systems, doing any kind of hardware stuff, you're going to be very, very concerned with how you can distribute your applications, how you run multiple threads, how you synchronize those threads, etc. So if that's something you're interested in, then definitely look more into Go, because there's a ton of other features related to multi-threading that I haven't even shown you, and that would take really a whole other course to completely go through. At this point, though, you should be comfortable running multiple threads in Go routines, have some sense of what channels are, how you can pass values between different threads, and how you can use things like the wait group and the locks to synchronize the execution of code. Anyways, I'm going to wrap it up here. I hope you found this helpful, and I look forward to seeing you in another one.